than a century, copper has quietly powered the modern world. Every major electrical grid, every data center, every factory, and nearly every computer has relied on copper to move electricity and information from one place to another. It became so essential that most people never stopped to question it. Copper was simply the material everything depended on. But today, something unexpected is happening. As artificial intelligence grows at an incredible pace, the technology that carried us into the digital age is beginning to show its limits. AI systems are becoming so powerful that moving data between thousands of processors has become almost as difficult as performing the calculations themselves. In many of the world's largest AI data centers, chips spend valuable time waiting for information instead of processing it. The processors are getting faster every year, but the connections between them are struggling to keep up. That has created one of the biggest engineering challenges of the AI era. Now, researchers and technology companies around the world are racing to solve it, and one country has been making an unusually large number of breakthroughs in exactly this area: China. Over the past few years, Chinese researchers have announced advances in optical networking, air-filled fiber, glass-based communication systems, photonic chips, and ultra-high-speed data transmission. While each announcement may seem unrelated on its own, together they point towards something much larger. Instead of asking how to make copper better, they're asking a completely different question. What if the future doesn't need copper at all? It sounds almost impossible. Copper has been one of civilization's most important industrial materials for generations. From power plants to smartphones, from electric vehicles to internet cables, it exists almost everywhere. Replacing it would require rethinking some of the most important technologies on Earth. Yet AI may be forcing exactly that transformation. The reason is surprisingly simple. Artificial intelligence doesn't just need faster processors. It needs those processors to communicate with each other almost instantly. Imagine trying to have a conversation with 10,000 people at the same time. Even if everyone could think incredibly fast, the discussion would still slow down if messages couldn't move quickly between them. The same thing happens inside AI supercomputers. Modern systems may contain thousands or even tens of thousands of advanced processors, working together as one enormous machine. Every second, those processors exchange enormous amounts of information. If the communication network can't keep up, the entire system becomes less efficient. For years, engineers have improved copper cables by making them faster, reducing electrical interference, and designing increasingly advanced connection technologies. But every improvement also introduces new challenges. Electrical signals generate heat. Higher speeds consume more power. Longer distances weaken the signal, requiring additional equipment to restore it before the information can continue traveling. As AI systems become larger, these problems grow exponentially. That's why many engineers now believe the next revolution won't come from faster processors alone. It will come from changing the way data moves. Instead of relying entirely on electricity flowing through copper, future systems may increasingly send information as pulses of light. Unlike electrical signals, light can travel enormous distances with extremely low loss. Optical communication also produces less heat and can carry significantly more information at the same time. For decades, fiber optic cables have already connected cities and continents using light instead of electricity. Now, researchers want to bring that same concept inside AI computers themselves. Rather than connecting processors with copper traces and electrical cables, future AI systems could increasingly use optical connections that move information using photons instead of electrons. That idea has become one of the hottest areas of research in modern computing, and this is where China's recent announcements begin to make more sense. Over the past several years, Chinese universities, telecommunications companies, and semiconductor researchers have repeatedly demonstrated new technologies involving optical communication. Some projects focused on photonic processors, others explored glass-based chips, some demonstrated record-breaking fiber transmission speeds, while others introduced entirely new networking techniques designed specifically for artificial intelligence workloads. Recently, Chinese researchers also reported transmitting data through air-filled optical fiber at extremely high speeds across long distances without traditional repeaters. While the technical details differ from project to project, the underlying direction remains remarkably consistent. Move more information, use less energy, reduce heat, eliminate bottlenecks. If these technologies continue improving, they could reshape far more than just data centers. Modern AI already influences healthcare, autonomous vehicles, robotics, scientific research, financial systems, manufacturing, logistics, and national infrastructure. Every improvement in computing efficiency has ripple effects throughout the global economy. That's why replacing even part of today's copper infrastructure would represent much more than an engineering milestone. It would represent a fundamental shift in how computers are built. Of course, this doesn't mean copper is about to disappear tomorrow. It remains one of the most reliable, affordable, and widely used industrial materials on Earth. Millions of miles of electrical wiring cannot simply be replaced overnight, but history shows that foundational technologies often remain dominant until a new generation quietly becomes good enough to solve problems the old one never could. Steam eventually gave way to electricity. Vacuum tubes gave way to transistors. Hard drives began sharing space with flash memory. And now, some engineers believe another transition may already be starting, not because copper suddenly became bad, but because artificial intelligence has created demands that copper was never originally designed to meet. If that's true, then what we're witnessing isn't simply another chip breakthrough. It may be the beginning of one of the biggest infrastructure changes the computing industry has seen in decades. And if China succeeds in leading that transition, the consequences could extend far beyond faster computers. To understand why so many researchers are looking beyond copper, it's important to understand just how dramatically artificial intelligence has changed the demands placed on modern computing. Only a few years ago, the world's largest data centers were designed primarily for cloud storage, video streaming, web applications, and online services. Those workloads certainly required fast hardware, but they were relatively predictable. Servers processed requests, sent responses, and repeated the cycle millions of times every day. Artificial intelligence changed the rules. Training a modern AI model requires thousands of processors working together as a single machine. Each processor constantly exchanges enormous amounts of information with every other processor in the system. Instead of sending occasional bursts of data, these networks operate almost continuously, moving information back and forth at incredible speeds. The challenge isn't performing the calculations anymore. The challenge is delivering the data fast enough. Imagine building the world's fastest sports car, but forcing it to drive through city traffic every day. No matter how powerful the engine becomes, the traffic limits its performance. That's essentially what's happening inside many AI clusters today. Modern processors can complete calculations at astonishing speeds, but if they have to wait for data to arrive, expensive computing power sits idle. Even a tiny delay becomes significant when multiplied across thousands of processors working simultaneously. Engineers often describe this as a communication bottleneck. It's one of the biggest reasons why building larger AI systems becomes increasingly expensive. Adding more processors doesn't automatically produce proportional performance gains. As systems grow, communication between processors becomes more complicated. More hardware means more cables. More cables mean more electrical interference. Higher data rates generate additional heat. More heat requires larger cooling systems, increasing electricity consumption and operating costs. Eventually, engineers reach a point where improving processors alone no longer delivers the expected performance. The network itself becomes the limiting factor. That's why some of the world's biggest technology companies are investing enormous resources into solving data movement instead of focusing exclusively on processing power. This is exactly where optical communication begins to stand out. Unlike traditional copper connections that transmit electrical signals, optical systems use pulses of light traveling through glass fibers or specialized photonic pathways. Light offers several important advantages. First, it can carry significantly larger amounts of information over long distances with minimal signal loss. Second, optical communication produces far less electrical interference than copper, making it easier to maintain signal quality as bandwidth increases. Third, because light doesn't generate electrical resistance in the same way as copper conductors, many optical systems can improve energy efficiency, especially when moving vast amounts of information between computing clusters. These advantages become increasingly valuable as AI infrastructure continues expanding. This helps explain why recent announcements from China have attracted so much attention. Rather than focusing only on designing faster processors, Chinese researchers have repeatedly introduced technologies aimed at improving the movement of information itself. Some projects explored advanced photonic chips capable of handling optical signals directly. Others focused on ultra-low-loss optical fibers capable of transmitting enormous amounts of information across impressive distances. Several research groups demonstrated new forms of integrated optical networking designed specifically for artificial intelligence workloads. Although these projects differ technically, they all pursue the same objective: remove communication bottlenecks before they become the biggest obstacle to AI progress. One particularly interesting direction involves bringing optical communication much closer to the processors themselves. Today, optical fibers already connect buildings, cities, and even continents. Inside computers, however, electrical copper traces still perform much of the communication between processors, memory, and networking hardware. Future systems may increasingly blur that distinction. Instead of converting information back and forth between electrical and optical signals multiple times, researchers hope to move light much deeper into computing systems. Some long-term visions even imagine optical communication operating directly between processors inside advanced AI servers. While that future remains under active development, progress is accelerating remarkably quickly. China has invested heavily in photonics research, semiconductor manufacturing, telecommunications infrastructure, and artificial intelligence over the past decade. These investments have created an ecosystem where universities, state laboratories, technology companies, and manufacturing firms often work on complementary parts of the same technological challenge. One team develops better optical materials, another improves photonic chips, another designs networking equipment, another optimizes AI software capable of taking advantage of faster communication. Together, these advances create momentum that individual breakthroughs alone cannot fully explain. This also helps explain why so many recent headlines appear connected. Glass AI chips, photonic processors, air-filled fiber, optical networking. High-speed AI interconnects. They aren't isolated inventions competing against one another. They're different pieces of a much larger puzzle. If enough of those pieces come together successfully, future AI systems could look fundamentally different from today's architectures. Instead of relying primarily on electrical pathways built around copper, much of the communication layer could gradually shift toward optical technologies. That doesn't necessarily eliminate copper completely. Power delivery will still require traditional electrical conductors. Many electronic components will continue depending on conventional circuit designs for years to come. But the role of copper in moving enormous quantities of digital information may begin changing. And that possibility has significant implications beyond engineering. Data centers consume enormous amounts of electricity. Artificial intelligence is increasing that demand every year. If faster optical communication allows AI systems to perform more work using less energy, the economic impact could be substantial. Lower operating costs, reduced cooling requirements, higher computing efficiency, better scalability. Those improvements matter not only for technology companies, but also for governments, research institutions, healthcare providers, manufacturers, financial firms, and virtually every industry beginning to adopt artificial intelligence. That's why replacing even part of today's copper infrastructure isn't simply about building faster computers. It's about enabling the next generation of AI itself. And if China's current pace of innovation continues, the country could play a major role in defining what that future looks like. The most interesting part of this story isn't that China is researching optical communication. It's that the entire technology industry is slowly reaching the same conclusion. For decades, progress in computing followed a familiar pattern. Engineers built faster processors, added more memory, improved manufacturing techniques, and shrank transistors. Each new generation delivered more performance without dramatically changing the overall architecture of computers. Artificial intelligence has disrupted that pattern. Today, simply building a faster processor is no longer enough. The real challenge is making thousands of processors behave like one giant computer. That sounds simple in theory, but it's incredibly difficult in practice. Imagine an orchestra with 10,000 musicians. Even if every musician is exceptionally talented, the performance falls apart if they can't hear the conductor or stay synchronized with one another. Timing becomes just as important as individual skill. Large AI clusters operate in much the same way. Every processor performs calculations independently, but they must constantly exchange information with the rest of the system. If synchronization slows down, overall performance drops dramatically. That's why engineers increasingly describe AI infrastructure as a communication problem rather than a computing problem. This shift is changing the priorities of the semiconductor industry. Instead of asking which company builds the fastest processor, engineers are asking a different question. Which company builds the fastest system? That's an important distinction. A complete AI system isn't just made of processors. It includes networking hardware, memory, storage, power delivery, cooling systems, advanced packaging, software, scheduling algorithms, optical communication, and increasingly, every one of those pieces must be optimized together. China appears to understand this very well. Rather than focusing exclusively on one breakthrough technology, Chinese companies and research institutions have spent years developing multiple pieces of the same ecosystem. We've already seen reports involving domestic AI accelerators designed to reduce dependence on imported hardware. We've covered memory manufacturers expanding production to challenge long-established industry leaders. There have been breakthroughs involving glass substrates capable of improving chip packaging. Chinese researchers demonstrated photonic processors that move information using light. There were advances in air-filled optical fiber capable of carrying astonishing amounts of data. And more recently, developments in AI networking technologies designed to reduce communication delays inside massive computing clusters. Individually, each story attracted attention. Together, they tell a much larger story. They're all solving different parts of the same challenge, building the infrastructure required for the next generation of artificial intelligence. That's also why many analysts believe the future AI race won't be won by whichever company builds the single fastest chip. Instead, it may be won by whoever integrates every component most efficiently. This is already becoming visible inside modern hyperscale data centers. Companies no longer purchase processors in isolation. They invest in complete platforms. Networking equipment must match processor performance. Memory bandwidth must keep pace with both. Storage systems must deliver information without delay. Power systems must support enormous energy demands. Cooling infrastructure must remove incredible amounts of heat. Software must coordinate every component with near-perfect efficiency. If even one layer falls behind, the entire system slows down. This systems-level thinking explains why optical communication has become so important. Replacing portions of copper infrastructure isn't only about transmitting data faster. It's about allowing every other component inside the AI ecosystem to perform closer to its full potential. Imagine spending hundreds of millions of dollars building one of the world's largest AI clusters, only to discover that processors spend a significant portion of their time waiting for information. That idle time represents lost performance, wasted electricity, and lower returns on enormous investments. Now imagine reducing those delays across tens of thousands of processors. Suddenly, the same hardware accomplishes more work. Training finishes sooner. Inference becomes more responsive. Operating costs decline. Energy efficiency improves. These benefits extend far beyond technology companies. Healthcare researchers could analyze larger medical datasets. Climate scientists could run more detailed simulations. Manufacturers could optimize production lines using increasingly sophisticated AI systems. Financial institutions could process larger volumes of information in real time. Autonomous vehicles could improve decision-making through more powerful training infrastructure. The ripple effects become enormous. This is one reason governments have begun treating artificial intelligence as strategic infrastructure rather than simply another software industry. Countries are investing not only in AI models, but also in the factories, supply chains, communication systems, and semiconductor technologies required to sustain long-term progress. China has been particularly active in this approach. Its investments span semiconductor manufacturing, optical communications, telecommunications equipment, artificial intelligence research, advanced materials, and industrial automation. Whether every individual project succeeds remains uncertain. Research always involves setbacks. Not every breakthrough reaches commercial production. Some technologies require years before becoming economically practical. Others may never leave the laboratory, but the overall direction is becoming increasingly clear. The industry is preparing for an era where moving information becomes just as important as processing it. And that's exactly where optical technologies could reshape the landscape. Instead of forcing electrical signals through increasingly complex copper pathways, future AI systems may rely more heavily on photons carrying enormous amounts of information with lower energy consumption and reduced heat generation. That transition won't happen overnight. Data centers represent trillions of dollars in existing infrastructure. Copper remains affordable, reliable, and deeply integrated into modern electronics. Replacing every cable, connector, and circuit would take many years. But technological transitions rarely happen all at once. They begin in specialized applications, where the advantages are greatest. Then costs fall, manufacturing improves, adoption spreads. We've seen this pattern before with solid-state storage, cloud computing, smartphones, and electric vehicles. Optical communication inside AI infrastructure may follow a remarkably similar path. If that happens, today's research announcements may eventually be remembered as the first signs of one of computing's biggest architectural changes since the arrival of the internet itself. So, does this really mean copper is finished? Not even close. Despite the excitement surrounding photonic communication and optical networking, copper remains one of the most important engineering materials ever discovered. It's inexpensive, durable, highly conductive, and supported by more than a century of manufacturing experience. Nearly every power grid, industrial machine, consumer electronic device, and data center still depends on it in some way. The future isn't likely to be a world without copper. It's far more likely to be a world where copper and optical technologies each handle the jobs they perform best. Electricity will continue flowing through copper, but information may increasingly travel through light. That distinction is becoming more important every year. Inside tomorrow's AI data centers, electrical power still needs to reach processors, memory modules, storage devices, cooling systems, and networking equipment. Copper remains exceptionally well suited for delivering power efficiently. The challenge isn't electricity. The challenge is information. Artificial intelligence has created computing systems that move unimaginable amounts of data every second. Every new generation of larger AI models increases that demand even further. Some experts already compare modern AI infrastructure to building highways. When traffic was relatively light, ordinary roads worked perfectly. As cities grew, those roads became congested. Eventually, engineers built multi-lane highways, bridges, tunnels, and entirely new transportation systems. Artificial intelligence is experiencing a remarkably similar transition. The processors themselves continue improving, but the highways carrying information between those processors must improve as well. That's why networking companies have become some of the most important players in the AI industry. It's also why semiconductor companies increasingly discuss entire computing platforms instead of individual chips. The future belongs to complete systems. Systems where processors, networking, memory, storage, cooling, software, and communication all work together with extraordinary efficiency. China appears determined to compete across every one of those layers. We've already seen domestic progress in memory manufacturing, advanced packaging, optical communication, AI accelerators, photonic research, glass-based technologies, ultra-fast networking. Each announcement may appear independent, but together they reveal a much broader strategy. Rather than relying on isolated breakthroughs, China is steadily building an entire ecosystem capable of supporting increasingly advanced artificial intelligence. Whether that ecosystem ultimately becomes the world's most powerful remains impossible to predict. Technology evolves rapidly. Companies in the United States, Europe, Japan, South Korea, and Taiwan continue making remarkable advances of their own. Competition remains intense, and many of today's experimental technologies still require years of engineering before reaching widespread commercial deployment. That's why it's important to separate exciting research from immediate reality. Not every laboratory breakthrough transforms the market overnight. Engineering challenges remain. Manufacturing must scale, costs must fall, software must adapt, industry standards must evolve, customers must be willing to invest. Those transitions take time, but history shows something equally important. Major technological revolutions often begin quietly. Few people recognize the importance of the first semiconductor. Very few imagined smartphones would replace cameras, music players, GPS devices, maps, calculators, and personal computers for billions of people. Cloud computing seemed unnecessary to many businesses before becoming essential. Artificial intelligence followed a similar path. For years, it remained largely inside research laboratories. Then, suddenly, it became part of everyday life. Optical communication inside AI infrastructure could follow that same pattern. At first, only the largest research centers and hyperscale cloud providers may deploy these technologies. Over time, manufacturing improves, costs decline, reliability increases. Eventually, techniques that once seemed futuristic become ordinary engineering. If that happens, future generations may look back at today's developments the same way we now look at the early internet. Not as isolated inventions, but as the beginning of an entirely new technological foundation. Perhaps that's the most fascinating part of this story. This isn't really about copper, it's about how artificial intelligence is forcing humanity to rethink decades of engineering assumptions. For over 100 years, moving electricity and moving information often relied on many of the same materials. AI is changing that. Instead of asking how to build slightly better cables, engineers are asking whether information should travel in an entirely different way. That's an enormous shift in thinking, and if countries like China continue advancing optical networking, photonic communication, and next-generation AI infrastructure, the competition may no longer revolve around building faster processors alone. It may revolve around building smarter systems, systems that waste less energy, generate less heat, move more information, and allow artificial intelligence to scale far beyond today's limitations. Whether that future arrives in 5 years or 15, one thing already seems clear. The race is no longer only about chips. It's about everything connecting those chips together. Because in tomorrow's AI world, the fastest processor won't necessarily win. The processor that waits the least will. And if light eventually replaces copper for many of those critical connections, we may be witnessing one of the biggest infrastructure transitions in modern computing history. The age of artificial intelligence isn't simply creating faster computers, it's creating entirely new ways for computers to communicate, and that could change everything. If you enjoyed today's video, don't forget to like, subscribe, and turn on notifications. Every day we break down the biggest technology breakthroughs shaping China's future, from AI, semiconductors, photonics, robotics, energy, and advanced manufacturing to the innovations that could redefine industries around the world. Let us know in the comments, do you think optical communication will eventually replace copper inside AI systems, or will copper remain the backbone of computing for decades to come? Thanks for watching, and we'll see you in the next video. Turn off a computer, and something strange happens. The files on the SSD remain exactly where they were, but everything held inside RAM disappears. Open documents, active calculations, temporary AI data, the precise state of every running program, all of it vanishes the moment electrical power is removed. That is the basic compromise inside nearly every modern computer. Fast memory forgets. Memory that remembers is slower. But researchers at Fudan University in Shanghai have built a device that appears to challenge that division. Their experimental flash memory stored information without continuous power, survived more than 5.5 million write cycles, and completed a programming operation in just 400 picoseconds. A picosecond is 1/trillionth of a second. At that speed, the device can theoretically complete 2.5 billion programming events in 1 second. Compared with conventional flash memory, whose programming time is often measured in tens of microseconds, the difference can approach 100,000 times. And the researchers say their device can program faster than SRAM built with the same channel length. That sounds like the beginning of universal memory. One technology combining the speed of working memory with the persistence of storage. But this is not yet a commercial RAM replacement. It is not a terabyte SSD. And the 400 picosecond result came from a tiny experimental device under carefully controlled conditions. The real breakthrough is more fundamental. For decades, engineers assumed that flash memory could not cross the 1 nanosecond barrier because its method of storing charge was simply too slow. Fudan's team crossed it. Then, months later, the same researchers integrated their two-dimensional memory technology with conventional silicon electronics and created a functional flash chip. The first experiment proved the physics. The second showed a possible path toward actual hardware. Together, they raise a much larger question. What happens if computers no longer have to choose between speed and memory that survives when the power goes out? The chalkboard and the stone tablet. A computer's memory system is not one single pool. It is a hierarchy. At the top are tiny registers inside the processor. They are extraordinarily fast, but there are very few of them. Below that is cache, followed by system RAM. These layers hold data close to the processor so calculations can happen quickly. Farther away sits persistent storage, SSDs and hard drives. Storage provides far more capacity, but the processor must wait longer to reach it. The arrangement exists because no single memory technology delivers every desirable property at once. SRAM is extremely fast, but it takes a large amount of silicon area and loses information without power. DRAM is denser and cheaper, but it must constantly refresh its electrical charge and also forgets when powered down. NAND flash stores enormous quantities of data and remembers without electricity, but writing to it is dramatically slower. Think of RAM as a chalkboard. Writing is immediate, erasing is easy, but when the lights go out and the room is cleaned, the information disappears. Flash memory is closer to carving a message into a stone tablet. The inscription remains. The problem is that carving takes time. Fudan's POX device is an attempt to write on the stone tablet at chalkboard speed. Why normal flash is slow. Flash memory stores information by trapping electrical charge inside an insulated layer. The presence or absence of that charge changes how the memory cell behaves electrically, allowing the device to represent zeros and ones. The charge must cross an energy barrier to enter the storage region. In conventional flash, this commonly happens through tunneling or hot carrier injection. Both methods work. Neither is naturally instantaneous. In Fowler-Nordheim tunneling, a strong electric field encourages electrons to pass through an insulating barrier that they would not normally cross. The effect is reliable, but moving enough charge takes time and often requires relatively high voltage. Hot carrier injection takes another route. Electrons accelerate along the memory channel. Some gain enough energy to jump into the storage layer. The faster and more efficiently those carriers are accelerated, the faster the memory can be programmed. Silicon places practical limits on that acceleration. The electric field is not distributed perfectly, and only a small percentage of carriers become energetic enough to cross the barrier. Engineers have improved flash memory for decades through better materials, thinner structures, and more sophisticated control. But the underlying mechanism remains slow compared with volatile memory. The accepted assumption was simple. Flash could become denser, it could become cheaper, it could consume less standby power. But sub-nanosecond programming was beyond its natural limit. The Fudan researchers attacked that limit by changing the channel material itself. The graphene channel. The experimental memory uses graphene as its channel. Graphene is a sheet of carbon only one atom thick. Its electrons behave differently from those moving through ordinary silicon. Under the right conditions, they can travel with very high mobility and experience unusual energy relationships associated with what physicists call a Dirac material. The important feature here is not simply that graphene is thin, it is how that thinness changes the electric field inside the device. In a conventional silicon channel, the horizontal electric field used to accelerate carriers is distributed across a thicker body. In the two-dimensional channel, the field becomes more concentrated. The carriers accelerate more effectively. More of them reach the high-energy state needed to enter the storage layer. The researchers call this two-dimensional enhanced hot carrier injection. Imagine two ramps reaching the same wall. The first ramp is long and shallow. A rolling ball gains speed gradually, but friction removes much of the energy before it reaches the top. The second ramp is shorter and steeper. The ball accelerates more aggressively and reaches the barrier with far greater energy. The graphene channel creates something closer to the second ramp. The result was a much larger injection current than the researchers observed in a comparable silicon system. More charge entered the storage region in less time. That is what enabled the 400 picosecond programming pulse. What 400 picoseconds means? 400 picoseconds equals 0.4 nanoseconds. Light travels only about 12 centimeters in that amount of time. A modern processor running at 5 GHz completes one clock cycle every 200 picoseconds. So the POX programming operation occurred within roughly 2 processor clock cycles at that frequency. That is an astonishing figure for non-volatile flash memory. Conventional silicon flash can require 10 to 100 microseconds to program a cell. 10 microseconds divided by 400 picoseconds is 25,000. 100 microseconds divided by 400 picoseconds is 250,000. That is why describing the breakthrough as approximately 100,000 times faster is reasonable. But it is not one fixed multiplier for every existing flash technology. The comparison depends on the specific device, operating conditions, and definition of programming time. The researchers tested a graphene device with a channel length of 0.2 micrometers and a programming voltage of around 5 volts. They repeated the short pulse measurement and observed a stable memory response. They also demonstrated a related device using tungsten diselenide, another two-dimensional material, which achieved 1 nanosecond programming through hot hole injection. This suggests the mechanism is not limited to one isolated graphene sample. Different two-dimensional materials may support different versions of the same general approach. Never forgets needs context. The device does not literally remember forever. No physical storage medium does. Never forgets means the information remains when electrical power is removed. That makes it non-volatile. SRAM and DRAM require continuous power to preserve their states. Remove the voltage and the stored information disappears almost immediately. Flash traps charge inside an insulated region, allowing the state to survive. The Fudan device maintained a measurable non-volatile memory window, after programming and demonstrated endurance beyond 5.5 million cycles. That is important because speed alone would not make a useful memory. A device that writes in 400 picoseconds but fails after a few operations is a laboratory curiosity. A device that performs millions of cycles begins to look more credible. However, endurance testing on a small research device is not the same as proving reliability across billions of cells operating for years inside consumer hardware. Commercial memory must survive temperature changes, manufacturing variations, electrical noise, and repeated operation across a complete chip. The prototype established that the mechanism can be fast and repeatable. It did not complete the industrial journey. Why AI cares about this? Modern processors are becoming faster than the systems feeding them. This is known as the memory wall. An AI accelerator may contain thousands of arithmetic units capable of performing enormous numbers of calculations. But those units need model weights, activations, and intermediate results. If data arrives too slowly, the accelerator waits. The chip may be powerful enough to perform the operation. The memory system prevents it from starting. Moving data also consumes energy. In many AI workloads, transporting values between storage, DRAM, and the processor can use more energy than the calculation itself. That is why high-bandwidth memory has become so valuable. It places large amounts of fast memory extremely close to AI processors. But HBM is expensive, complicated to package, and still volatile. Every time a system starts, model data must be loaded from persistent storage into fast memory. Imagine a library that burns every book each night and reconstructs the collection every morning from a warehouse. The readers eventually receive the information. The rebuilding process wastes time and energy. A fast, non-volatile memory could preserve important data close to the processor even after shutdown. AI models might start more quickly. Edge devices could retain local model states without constantly refreshing memory. Computers could reduce the amount of data copied repeatedly between storage and working memory. This is the larger promise behind ultra-fast persistent memory. Could it replace RAM? Not today. The prototype demonstrated exceptional programming speed in an individual memory structure. A complete RAM system requires much more. Billions of cells must be arranged into dense arrays. Every cell must be selected without accidentally disturbing its neighbors. Read and write circuits must operate quickly. Manufacturing yield must be high. The chip must fit existing processor and memory interfaces. Cost per bit must compete with technologies produced in enormous factories. Latency also includes more than the programming pulse. A real computer must send an address, select the correct cell, move signals through wires, sense the stored state, correct errors, and transfer the result to the processor. A 400 picosecond device operation does not mean a future memory module will automatically deliver 400 picosecond system latency. The difference resembles a car engine capable of reaching a certain rotational speed. That number matters. But the speed of the complete vehicle also depends on the transmission, tires, aerodynamics, and road. The experimental device proved the engine. The researchers still needed to build more of the car, and that is exactly what they attempted next. The second breakthrough. Later in 2025, the Fudan team reported a full-featured two-dimensional NOR flash memory chip integrated with conventional silicon CMOS electronics. This was a major step beyond the original device demonstration. The new chip used the two-dimensional material as the memory core while mature silicon circuitry handled instruction control and system operation. The researchers called the integration method ATOM2CHIP. The chip supported random access, 8-bit instruction operations, and 32-bit parallel operation. Full chip testing produced a reported memory cell yield of 94.34%. Its integrated memory cells operated in 20 nanoseconds and consumed as little as 0.644 picojoules per bit. 20 nanoseconds is far slower than the original 400 picosecond pulse. That does not mean the later chip failed. It means integration introduces real-world overhead. The signal must pass through control circuits. Cells must be addressed. Operations must occur across an array rather than one optimized test device. The integrated chip sacrificed record-setting speed in exchange for functionality. That is often how new technology develops. The first prototype demonstrates an extreme physical result. The first system trades some of that result for reliability, control, and manufacturability. 20 nanoseconds is still fast for non-volatile flash memory. More importantly, the researchers showed that the two-dimensional memory could communicate with a conventional CMOS platform. Why integration is so difficult? Two-dimensional materials can be only one or a few atoms thick. That creates remarkable electrical properties. It also makes manufacturing difficult. A conventional silicon chip surface may look perfectly smooth to the human eye. At atomic scale, it resembles rough terrain. Different structures rise from the surface. Metal lines, insulating regions, and contacts create tiny height variations. Placing an atomically thin layer directly across that surface is like stretching plastic film over an entire city. From an airplane, the land looks flat. At street level, buildings, bridges, and towers make a smooth covering impossible. The film can wrinkle, tear, lose electrical performance, or fail to contact the correct region. The Fudan team's solution was modular. They manufactured the two-dimensional memory section and conventional CMOS control circuitry separately, then connected them through dense vertical interconnects. This allowed the new material to preserve its performance without requiring the entire silicon surface to become atomically flat. The approach also avoids rebuilding every part of the computer from experimental materials. Conventional CMOS remains excellent at logic. The two-dimensional layer performs the memory function, where its unusual physics provides the greatest advantage. This hybrid strategy may be more realistic than attempting to replace silicon completely. NOR flash versus the SSD in your computer. The integrated chip was a form of NOR flash. That distinction matters. Most large SSDs use NAND flash. NAND is optimized for extremely high density and low cost per bit. It arranges cells in long strings and reads or writes data in larger blocks. NOR flash offers direct random access and is commonly used for firmware and code storage, where rapid, precise access matters more than maximum capacity. The Fudan device therefore should not be imagined as an immediate replacement for a multi-terabyte NAND SSD. Its potential may first appear in applications requiring fast, persistent access, processor boot code, AI accelerator configuration, embedded systems, automotive electronics, edge computing devices, persistent cache, memory placed close to specialized processors. These markets may tolerate higher cost per bit if the technology reduces startup time and energy consumption. Only after manufacturing improves could the concept challenge larger portions of the memory hierarchy. The dream of universal memory. Engineers have pursued universal memory for decades. The ideal technology would combine 5 properties: SRAM-like speed, DRAM-like density, flash-like persistence, low energy consumption, and nearly unlimited endurance. No existing memory provides all 5. Phase change memory retains data and can be fast, but heat and material changes create challenges. Magnetic memory offers strong endurance, but scaling and density remain difficult. Resistive memory can switch quickly, yet device-to-device variation complicates large arrays. Ferroelectric memory is promising, but integration and long-term reliability remain active engineering problems. POX adds another candidate. Its unusual advantage is that it remains a charge storage device related to flash, but changes the injection mechanism using two-dimensional materials. That connection to familiar flash principles could help engineers understand and adapt the technology. Still, universal is an extremely demanding word. A memory can be fast but too expensive, persistent but insufficiently dense, efficient but difficult to manufacture. The winner will not be determined by one record. It will be determined by which technology can survive a factory. What still has to happen? The first challenge is scale. The research team must move from small arrays to millions and eventually billions of memory cells. Yield becomes harder as the array grows. A 94% yield sounds strong for an early research chip. For mass production, even a small defective percentage can become unacceptable when billions of cells are involved. The second challenge is uniformity. Atomically thin materials must behave consistently across large wafers. A small difference in thickness, contamination, or contact resistance can change device performance. The third challenge is density. The memory must store enough bits per unit area to justify its cost. The fourth challenge is voltage. The prototype used programming voltages around 5 volts. Future systems may need lower operating voltage to reduce power and simplify integration. The fifth challenge is economics. Graphene and other two-dimensional materials must be deposited, patterned, and connected using processes compatible with high-volume semiconductor manufacturing. A technology can outperform existing memory and still lose if each chip costs 10 times more. The final challenge is time. The researchers have discussed expanding toward much larger integration within several years. That is ambitious. Even successful semiconductor technologies can require a decade or more to move from laboratory demonstration to widespread commercial use. My take. My view is that the most important result is not the 100,000 times headline. The speed is spectacular. But research laboratories produce spectacular isolated numbers regularly. What makes this story different is the sequence. First, the team demonstrated a 400 picosecond non-volatile flash device. Then it built a functional hybrid chip around the same broader two-dimensional memory concept. The system was slower than the record prototype, but it could execute instructions, perform parallel operations, and access memory randomly. That is progress in the correct direction. The first result said, the physical speed limit can be broken. The second said, the device can begin participating in a real circuit. China has not eliminated RAM, it has not produced a commercial universal memory chip, and no laptop shipping today contains POX memory. But the traditional boundary between fast volatile memory and slow persistent storage looks less permanent than it did before. For most of computing history, the rule was simple. Anything fast enough to serve the processor forgot when power disappeared. Anything that remembered was forced into a slower tier. The Fudan experiments show that this rule is not fundamental. It is a consequence of the materials and device structures we currently use. Change the material, reshape the electric field, accelerate the carriers differently, and flash memory can enter a speed range that once appeared impossible. The hardest work begins now: scaling, manufacturing, reducing voltage, improving yield, and proving that the technology can remain reliable outside a research laboratory. But every commercial memory technology began with a device that looked too small, too unusual, or too expensive to matter. The question is whether POX follows the same path or remains a brilliant record in a scientific paper. So what do you think? Could ultra-fast non-volatile memory eventually replace both RAM and flash with one universal technology? Or will manufacturing cost and scaling challenges keep the computer's memory hierarchy intact? Let me know your view in the comments. And if you want more grounded stories about the chips, materials, and hidden engineering breakthroughs reshaping computing, subscribe to Eastern Engine, because the next revolution in memory may not be a drive with more capacity, it may be a chip that refuses to forget. Huawei may be building something no other Chinese technology company has ever controlled at this scale. The processor, the memory, the storage, the software, and perhaps even the factories that produce the most important chips inside its devices. And that matters because Apple, despite designing some of the world's most advanced consumer processors, still depends on outside companies for the memory and flash storage inside every iPhone, iPad, and Mac. Huawei appears determined to reduce that kind of dependence as far as possible. The latest reports focus on DRAM, the fast-working memory used by smartphones, computers, servers, vehicles, and nearly every modern electronic system. Huawei has not confirmed that it owns or operates a DRAM manufacturing network. In fact, it has denied claims that it controls a hidden group of semiconductor factories. But analysts, industry publications, corporate connections, and earlier satellite investigations have continued pointing toward a much deeper relationship between Huawei and several Chinese chip companies than official ownership records suggest. One name now receiving major attention is Suisher, a Shenzhen memory company that has been linked to a planned 12-inch DRAM facility. Reports describe a production target of roughly 140,000 wafers every month, although that figure remains unconfirmed. If the facility reaches anything close to that scale, it would not be a laboratory experiment. It would be industrial capacity designed to supply large volumes of memory for Chinese phones, computers, servers, networking equipment, and other products. That is where this story becomes much bigger than another new semiconductor factory. Huawei already develops its own Kirin processors through HiSilicon. It sells enterprise solid-state drives and storage systems, and it has spent years developing proprietary SSD controllers, storage software, and flash management technology. Huawei also builds phones, computers, networking equipment, cloud infrastructure, vehicle systems, and data center hardware. Adding a reliable domestic source of DRAM could connect those separate pieces into one unusually integrated technology platform. Apple is often described as the master of vertical integration. It designs the iPhone, the operating system, the processor architecture, many supporting chips, and the services surrounding the device. That control creates excellent performance because Apple can optimize hardware and software together. But Apple does not manufacture its own leading-edge processors. TSMC produces them. Apple does not fabricate its own DRAM. Suppliers such as Samsung, SK Hynix, and Micron provide memory. Apple also relies on outside companies for NAND flash and many other essential components. Huawei's ambition appears different. It is not merely trying to design the best phone processor or create a polished operating system. It is trying to build a supply chain that can continue functioning even when foreign governments restrict access to crucial technologies. In that environment, owning more of the stack is not only about performance or profit, it becomes a form of strategic protection. The United States placed Huawei on the Entity List in 2019, sharply limiting its access to American technology. Later export rules also restricted foreign-made chips produced with certain American software or equipment. Those measures disrupted Huawei's smartphone business. weakened its access to advanced processors, and forced the company to search for alternatives across nearly every level of semiconductor development. For several years, many observers believed the restrictions had permanently stopped Huawei's momentum. Its global phone shipments collapsed, Google services disappeared from new international devices, and advanced chip supplies became difficult to secure. Then Huawei returned with new premium smartphones powered by domestically produced Kirin chips. Those processors did not immediately match the most advanced Apple or Qualcomm products, but their existence demonstrated that China's semiconductor network had progressed further than many outside analysts expected. Now the next stage may be memory. This timing is important because memory has become a geopolitical product, not merely a commodity. Washington is debating how Chinese DRAM should be treated, while Beijing is encouraging domestic substitution across strategic supply chains. A Huawei-linked memory project would therefore serve two goals at once: supplying commercial products and insulating critical Chinese hardware from future restrictions imposed unilaterally abroad. A processor receives most of the attention because it performs the calculations and carries the recognizable brand name, but a processor without memory cannot do useful work. DRAM temporarily holds the information that the processor needs immediately. Faster memory can improve responsiveness, multitasking, gaming, professional software, and the efficiency of large computing systems. When memory is scarce, expensive, or restricted, even a powerful processor can become difficult to deploy at scale. Huawei currently has to obtain memory through suppliers and partners, just like most technology companies. China's strongest established DRAM producer is CXMT, which has expanded rapidly and is now at the center of political pressure in Washington. American lawmakers have discussed tighter restrictions on Chinese memory chips, especially as reports suggest major global companies have evaluated Chinese components. That pressure gives Huawei another reason to support an alternative source. If Shueisha can produce usable DRAM in large quantities, Huawei could gain a second domestic pathway. It could potentially shape memory specifications around its own processors, storage systems, phones, servers, and networking products. It could coordinate product development earlier, test components more closely, and reduce the risk that a foreign supplier suddenly becomes unavailable because of sanctions or licensing decisions. However, building DRAM is extremely difficult. Memory chips may look repetitive compared with complex processors, but manufacturing them economically requires enormous precision, strong yields, advanced materials, reliable equipment, and years of process knowledge. A factory can technically produce working chips and still lose money if too many wafers contain defects. Samsung, SK Hynix, and Micron have spent decades improving production and spreading their research costs across huge global businesses. The reported Shueisha facility is associated with 28nm DRAM technology. That sounds old when compared with the small node numbers used to market processors, but memory processes cannot be compared directly with logic processes. Mature equipment can still produce valuable memory for industrial devices, networking systems, automobiles, consumer electronics, and many other products. The first objective may not be defeating the latest Samsung memory chip. It may be creating dependable capacity using tools China can obtain, maintain, and eventually replace domestically. This strategy would follow a familiar pattern. Start with products that are possible today. Use domestic demand to keep factories busy. Improve yields through repeated production. Train engineers. Localize more equipment and materials. Then move toward higher density, lower power consumption, and more advanced memory generations. Huawei has the scale to support that process. According to its official 2025 annual report, the company generated 880.9 billion yuan in revenue and invested 192.3 billion yuan in research and development. That means more than 1/5 of annual revenue went back into research. Huawei also reported that approximately 114,000 employees worked in research and development by the end of 2025. Few companies anywhere can sustain that level of engineering investment. The money does not guarantee success, but it changes the odds. A smaller company might abandon a difficult semiconductor project after several years of losses. Huawei can spread the cost across telecommunications, consumer devices, enterprise storage, computing, automotive technology, energy products, and services. It can also become the customer for its own components, giving new factories demand before they are competitive in the open market. That internal demand is one of the biggest advantages of vertical integration. Imagine Huawei developing a new processor for a future phone. If it also influences the DRAM, storage controller, SSD firmware, operating system, and device design, engineers can optimize the entire system instead of waiting for standardized components from unrelated suppliers. They might reduce power consumption, improve data transfer, change packaging, or prioritize features designed specifically for Huawei products. Samsung is the clearest example of this model. Samsung designs processors, manufactures chips, produces DRAM and NAND flash, builds displays, assembles phones, sells appliances, and operates enormous factories. It does not control every component in every product, but its manufacturing depth gives it options that most competitors lack. Huawei appears to be moving toward a Chinese version of that broad industrial structure, although it remains far behind Samsung in advanced memory production and global manufacturing experience. The comparison with Apple is more complicated. Apple's business model does not require owning chip factories. It uses its purchasing power to secure leading production from specialized suppliers, while concentrating its resources on design, software, product integration, and services. That model has been extraordinarily successful. Apple can access TSMC's newest manufacturing without carrying the cost and risk of operating fabrication plants itself. But Apple's model depends on an international supply chain remaining available. Apple can negotiate with suppliers, diversify orders, and reserve enormous amounts of production, but it cannot directly command a memory factory it does not own. Huawei has experienced what happens when political decisions suddenly break those relationships. Therefore, Huawei may accept higher costs and less advanced technology today in exchange for greater control tomorrow. This does not mean Huawei is already independent. It still depends on outside companies, imported equipment, specialized materials, manufacturing partners, and technologies that China has not fully replaced. Even its domestically produced advanced processors have been associated with SMIC rather than factories openly owned by Huawei. Semiconductor manufacturing equipment remains a major weakness because the most advanced lithography, inspection, deposition, and testing systems are concentrated among a small number of foreign suppliers. There are also serious questions about the reported network of 11 fabs. Industry reports have described factories connected to Huawei through employees, financing, customers, technology transfers, or local government support. Yet indirect relationships are not the same as legal ownership or operational control. Huawei denies operating a secret fab network, and public evidence does not allow outsiders to verify every claim. Any responsible interpretation must separate confirmed Huawei products from alleged manufacturing connections. What is confirmed is Huawei's direction. The company openly develops processors, computing systems, enterprise SSDs, storage controllers, networking chips, operating systems, and full hardware platforms. In May 2026, Huawei presented a new semiconductor design strategy built around advanced packaging, architecture, software, and system-level coordination, rather than relying only on smaller transistors. Huawei also said future Kirin chips would use its logic folding architecture to improve performance through greater integration. That approach reveals how Huawei intends to compete while access to the most advanced manufacturing remains limited. Instead of waiting until Chinese factories can copy every part of the global supply chain, Huawei is redesigning products around the capabilities it has. Multiple chiplets can be connected through advanced packaging. Software can schedule workloads more efficiently. Larger systems can combine many processors. Memory, storage, networking, and computation can be coordinated as one platform. DRAM fits naturally into that strategy. Memory bandwidth and latency can become bottlenecks when processors are combined into larger systems. A company that controls the processor architecture but depends entirely on external memory roadmaps has less freedom. A company that can influence both sides can experiment with packaging, interfaces, capacity, and power targets designed around its own products. The same logic applies to storage. Huawei already sells Ocean Disk Enterprise SSDs and Ocean Store all-flash systems. Its public materials describe proprietary SSD controller technology and end-to-end storage development. Yet selling an SSD does not necessarily mean fabricating every NAND memory cell inside it. The strategic goal is not instantly owning every atom of the device. It is steadily gaining control over the most important designs, controllers, software layers, suppliers, and production routes. For China, Huawei's expansion could also support a wider domestic ecosystem. A DRAM facility needs wafer equipment, photoresists, gases, chemicals, masks, testing tools, packaging services, and trained engineers. Even if early chips trail foreign competitors, each production run creates experience for local suppliers. That industrial learning can spill into other companies and make future restrictions less effective. For foreign competitors, the immediate threat may not be Huawei taking global market share with the world's fastest DRAM. The bigger threat is Huawei becoming harder to pressure. Sanctions work most effectively when a target depends on something only outsiders can provide. Every domestic processor, memory chip, controller, production tool, and software platform removes one potential point of leverage. This could reshape competition inside China first. Huawei could favor its own components, direct large orders toward affiliated suppliers, and bundle processors, memory, storage, networking, and software into complete systems. Chinese customers seeking stable domestic supply may accept lower efficiency or higher prices, especially in government, telecommunications, infrastructure, and strategically important industries. Over time, scale could reduce those disadvantages. More orders can finance better equipment. Higher production volumes can improve yields. Larger engineering teams can solve defects faster. Suppliers can justify developing specialized materials. What begins as an expensive sanctions workaround can eventually become a competitive industrial base. Still, the path is not guaranteed. Memory markets are brutally cyclical. Prices can collapse when too much capacity enters the market. Established producers can lower prices, accelerate investment, and use their technological lead to squeeze new competitors. Huawei and Shueisha would need to prove not only that they can manufacture DRAM, but that they can do so reliably, efficiently, and repeatedly across multiple generations. There is another risk: stronger American restrictions. If Washington concludes that Huawei is using related companies to obtain restricted tools or technology, more firms could be added to export blacklists. Shueisha has already faced American scrutiny. Expanded controls could make equipment maintenance, software updates, spare parts, and future factory expansion more difficult. But restrictions can produce two opposite effects. In the short term, they can slow production and raise costs. In the long term, they can convince a large country that dependence itself is unacceptable. Huawei's current semiconductor strategy is a direct result of being cut away from suppliers it once treated as normal business partners. The more pressure increases, the more resources China may direct toward replacing every vulnerable component. That is why the real story is not whether one rumored factory immediately beats Samsung or Micron. The real story is whether Huawei can connect enough domestic capabilities to create a self-reinforcing technology system. Huawei processors generating demand for Chinese fabs, Chinese memory supporting Huawei devices, Huawei storage products creating demand for controllers and NAND, and domestic equipment companies learning from every new production line. Apple's ecosystem is powerful because millions of customers, developers, devices, services, and custom chips reinforce one another. Huawei is attempting to build a different kind of ecosystem, based not only on software and consumer loyalty, but on industrial survival. It wants the device, the operating system, the processor, the networking, the storage, the memory, the packaging, and eventually more of the machinery beneath them. In my opinion, Huawei is still years away from true semiconductor independence, and some claims about its hidden factories may be exaggerated. But dismissing the strategy because its first products are behind would repeat the mistake many observers made before Huawei's smartphone comeback. The company does not need to lead immediately. It needs to keep producing, learning, improving, and removing one dependency at a time. If Huawei eventually controls reliable supplies of CPUs, DRAM, SSD technology, and advanced packaging, America will face a much harder target than the company it sanctioned in 2019. Apple may continue building faster and more profitable devices, but Huawei could possess something increasingly valuable in a divided world: the ability to keep building when outside suppliers are ordered to stop. So what do you think? Is Huawei creating the next Samsung-style semiconductor empire, or will manufacturing limits prevent it from closing the gap with Apple and the world's leading chip makers? Tell us your opinion in the comments. And for more stories about China's processors, memory, storage, manufacturing, and the global technology race, subscribe to the Eastern Engine channel. His name is Dong Hui. He is 39 years old. 6 years ago, a car accident left him paralyzed from the neck down. He couldn't move his fingers. He couldn't write. Something as ordinary as holding a pen had become completely impossible, and every specialist he'd seen told him the same thing in different words: this is permanent. Then surgeons placed a coin-sized chip between his skull and his brain. 11 months later, sitting in the courtyard of his home in China's Henan province, Dong Hui picked up a pen. Slowly, carefully, deliberately, he wrote his name. Then he wrote, "Thank you." Then he wrote the date. He later told journalists he was so overwhelmed that he missed a stroke in his own name. "I couldn't believe I was able to write again. I was so excited." That chip, the one that gave Dong Hui back his hands, just became the first invasive brain-computer interface in history to receive full commercial approval anywhere on Earth. Not a trial permit, not a research exemption, a product license. Available to real patients, covered by China's national health insurance. In production right now, scaling to meet demand. And here's the part that changes the entire story. While that was happening, Elon Musk's Neuralink, the most famous, most funded, most publicized brain chip project in the world, still has 21 people in an experimental trial. No commercial approval, no product license, no insurance coverage, anywhere. The race that everyone assumed Elon Musk would win, someone just crossed the finish line. And it wasn't him. To understand what just happened, you need to understand how this competition looked from the outside for the past several years. Neuralink was the story. Full stop. Elon Musk announced it, hyped it, described a future where paralyzed people would walk again, where blind people would see again, where the entire interface between human consciousness and computing would be reinvented. He is the most followed person on the planet. Every announcement got global coverage. Every trial update was front-page news. The assumption baked into almost every article written about brain-computer interfaces was simple. Neuralink leads, everyone else follows. Meanwhile, in Shanghai, a startup called Neurical Technology was quietly doing something different. No celebrity CEO, no viral announcements, no promises about controlling computers with your thoughts or uploading your memories. Just a research team, a partnership with Tsinghua University, one of China's most prestigious technical institutions, and a singular focus on getting one specific device approved for one specific group of patients. The device was called Neo. It's roughly the size of a coin. It takes about 90 minutes to implant. It sits between the skull and the outer protective membrane of the brain, called the dura mater, with 8 sensors pressing gently against that membrane, without ever penetrating the brain tissue itself. Wireless signals travel from the implant to an external processor, which translates the brain's electrical activity into commands for a robotic glove, allowing patients with severe hand paralysis to perform basic grasping movements they hadn't been able to do in years. In March 2026, China's National Medical Products Administration gave it full commercial clearance. 36 clinical trials, 32 of them completed in a compressed window in 2025 alone. And then, approved. Not for trials, for hospitals, for patients, for production. The first invasive brain implant ever cleared for sale anywhere in the world. Here's the counterintuitive part of this story. Neo is not the most powerful brain chip ever built. It almost certainly isn't. Neuralink's N1 chip penetrates the brain's outer cortex directly, accessing neural signals closer to their source and potentially enabling finer, more precise control. Neuralink's long-term ambitions, restoring sight, enabling full-body movement, eventually merging human consciousness with computing, are technically more audacious than anything Neo currently does. So how did the less aggressive device win the regulatory race? Because less aggressive and commercially viable are not opposites. They're often the same thing. Neo's design is epidural. It sits on top of the brain's protective membrane, rather than inside the brain tissue itself. A researcher at the University of Technology, Sydney, speaking to MIT Technology Review, explained why that distinction matters enormously in a regulatory context. An epidural approach carries significantly lower risk of bleeding and lower risk of signal loss over time than electrodes that penetrate the cortex. When a regulator is evaluating a device for broad commercial use, not just in a handful of carefully selected trial participants, but in real hospitals with real patients who have varying health conditions, risk profile is everything. Neo didn't win because it outperformed Neuralink. It won because it was designed to be approvable, not just impressive. And Neurical had something else that Neuralink doesn't: state-level strategic backing with matching urgency. China has listed brain-computer interface technology as one of 6 national strategic priorities, alongside quantum computing and humanoid robotics. That designation isn't symbolic. It comes with coordinated funding, expedited regulatory pathways, and the kind of institutional alignment between researchers, companies, and government that compresses the timeline from lab to clinic in ways that are genuinely difficult to replicate in a system where commercial interests, regulatory bodies, and research institutions operate independently. Neurical ran 32 of its 36 trials in a matter of months in 2025. That pace of clinical validation reflects a system operating in a different gear from what Neuralink has been navigating. The facts and the regulatory milestones are important, but there's a human being at the center of this story, and he deserves more than a footnote. Everything you do online is being watched: your provider, advertisers, even governments. NordVPN encrypts your connection, hides your location, and unlocks the open internet from anywhere. Grab the deal, link in the description. Dong Hui was paralyzed in 2018, 6 years of his life spent unable to use his hands. Then he saw something on television, a news report about another paralyzed man in China who had regained some movement through a brain-computer interface trial. He signed up for Neuralink program in October 2023, 1 month after watching that report. The implant went in. The rehabilitation process began. Slowly, painstakingly, his brain learned to communicate with the device, and the device learned to interpret his brain. 11 months later, he wrote his name in his own courtyard. He also told journalists he hadn't expected it to work. He'd spent 6 years being told his condition was permanent. The moment he picked up that pen was the moment 6 years of that certainty collapsed. This is what Neo actually is. Underneath all the regulatory language and competitive framing, it is a device that gave a man back the ability to write his own name, and it is now approved for use in a country of 1.4 billion people, covered by the National Health Insurance System, with more patients entering the program as production scales. The numbers behind that aren't just impressive, they're staggering. Hundreds of thousands of people in China live with the kind of spinal cord injury Neo is designed to treat. Here's the pattern that keeps appearing in technology, and it's directly relevant to everything covered on this channel. A technology is invented, usually in a Western lab, usually by researchers with enormous resources and high ambitions. For years, everyone watches that original team. They assume the leader stays the leader. They write articles about when the technology will mature, when it will become commercial, when it will change the world. All the attention stays focused on the most famous version of the thing, and then something else happens somewhere else. Quietly, methodically, without the celebrity or the headlines. A different team, with different priorities, in a different system, makes different design choices. And while everyone is watching the famous version, the less famous version crosses a threshold that matters. It happened with glass chips. The semiconductor industry was fixated on transistors and lithography while the substrate layer changed underneath everyone. It happened with diamond cooling. NVIDIA's CEO was flying to China while most of the world was still debating whether diamond was even practical. And now it's happening with brain chips. Neuralink has more press coverage than every other BCI company combined. And a startup most people have never heard of, built in Shanghai with funding from Tsinghua University and backing from China's National Technology Strategy, just became the first to put a commercially approved brain implant into a patient outside a clinical trial. The pattern isn't that the famous version is wrong, or that the quiet version is always better. The pattern is that fame and leadership aren't the same thing. And in technology, the milestone that actually counts isn't who announced it first, it's who shipped it first. Neo is the first. It will not be the only. China has at least 2 more BCI devices behind Neo in the pipeline. Neuroxess and StairMed are both developing competing implants domestically. The Beijing Brain Institute's BEINA01 system is expected to reach market by 2028. Within the span of roughly 2 years, China could have multiple commercially approved brain implants operating in its healthcare system, each generation learning from the one before it, while the rest of the world is still working through regulatory trials. The advantage this creates isn't just about one device, it's about data. Every patient who receives Neo generates real-world performance data in a commercial healthcare setting. That data, how the implant performs over months and years, which patient profiles respond best, which failure modes appear, and how often, is exactly the kind of evidence that makes second-generation devices better. And it is the kind of evidence that regulators in other countries will eventually require before approving anything. China now has a head start not just in commercial approval, but in the accumulation of long-term, real-world safety and performance data. That compounding lead is far harder to close than a regulatory gap. It's the same dynamic as the glass substrate story, the same dynamic as the diamond chip story. Being first doesn't just mean you got there early, it means every subsequent year of operation makes you harder to catch. For Neuralink specifically, the competitive picture has shifted in a way that doesn't get fully acknowledged. Neuralink's technical ambitions remain larger. Its long-term vision, the idea of a general-purpose brain-computer interface that goes far beyond motor rehabilitation, hasn't changed, but it is now competing in a landscape where a rival has commercial approvals, insurance coverage, real patients, and accumulating real-world data, while Neuralink is still adding participants to a clinical trial. That's a different kind of pressure than it was 12 months ago. Here's what strikes me most about this story, and it's something I keep coming back to. Neuralink had everything: the money, the attention, the most famous founder in technology, a decade of runway. And Neo, a startup from Shanghai with a fraction of the profile, shipped first. Not because Neuralink is more talented than Neuralink's engineers, both teams are world-class, but because Neuralink made a device that was designed to clear regulatory hurdles, rather than one designed to impress a keynote audience. They optimized for approval, not for ambition. And in the market for medical devices, approval is everything. The most powerful chip in the world is useless inside a lab. I think the Neuralink story is far from over. A device that actually penetrates the cortex and accesses finer neural signals will likely enable capabilities that Neo simply can't. But Neuralink now has to develop and prove those capabilities while a competitor is already in hospitals, already covered by insurance, already generating data, and already treating patients. That's a completely different race than the one Neuralink thought it was running. Here's my question for you, and I want your honest answer. Does this change how you think about Neuralink? Because here's the tension. Neo got to market first, but Neuralink's ambitions are larger. Is first to market in medicine the thing that matters most, or does the device with the higher ceiling eventually win regardless? Drop your actual opinion in the comments. This one I'm genuinely curious about. If you want to keep following these stories, the ones that rewrite which country leads in a technology that seems settled, subscribe to Eastern Engine and turn on notifications. Brain chips, diamond chips, glass chips, the substrate layer, the thermal layer, all of it connects. And all of it is moving faster than most people realize. Thanks for watching. See you in the next one. A silicon wafer enters a machine. There is no giant projection lens above it. No deep ultraviolet flash sends a pattern through an optical system. Instead, a patterned template moves downward. The chamber is placed under vacuum. Pressure spreads across the wafer. The template touches a thin layer of specially prepared material, and nanoscale structures are copied directly into it, almost like pressing a seal into soft wax, except the details are measured in billionths of a meter. Then the template lifts away. What remains is the pattern for a photonic chip. On June 5th, Chinese nano-imprint equipment company Prenano said it had worked with Shenzhen Litra Technology to validate this process across full 8-inch wafers. The machine is called the PLAS, and according to the companies involved, it can manufacture photonic chip patterns without a conventional DUV lithography step. The cost claim is even more dramatic. Prenano says the relevant manufacturing cost can be reduced to roughly 1/10 of the traditional DUV route. That does not mean every lithography machine has suddenly become unnecessary. It does not mean this process can print the processor inside your phone. And it definitely does not mean every finished chip becomes 90% cheaper. The real story is narrower, but it may also be more believable and more important, because engineers may have found the exact kind of chip where stamping, not projecting, finally makes commercial sense. Modern chip manufacturing is often described as printing. Traditional photolithography is closer to taking the most precise photograph imaginable, repeatedly, on a surface that cannot tolerate a meaningful mistake. A wafer is coated with a light-sensitive material called photoresist. A circuit pattern is encoded on a mask. Light exposes selected regions of the resist. The pattern is developed, transferred into the layer below, and then the process begins again and again. Different layers build devices, connections, and optical structures. Each new pattern must align with the previous one. A tiny shift can ruin the result. DUV lithography achieves extraordinary precision through advanced optics, motion control, materials, and computational correction. The light source must remain stable. The wafer stage must accelerate, stop, and align with almost unnatural accuracy. Temperature, vibration, and contamination must all be controlled. It is astonishing engineering. It is also expensive and complex. Every additional exposure adds tool time, process steps, and another opportunity for variation. Nano-imprint lithography asks a blunt question. What if the pattern did not need to be projected at all? The basic idea is easy to understand. Engineers first create a master template containing the required nanoscale pattern. That template is placed above a wafer coated with imprint resist. Instead of projecting light through a mask, the machine presses the template into the material. The resist flows into the template's tiny grooves. It is hardened, and the template separates from the wafer, leaving behind a physical copy of its surface. Later etching steps transfer that pattern into the material underneath. One master can, in principle, reproduce the same structure many times. Think about the difference between drawing a detailed map repeatedly and using a printing plate. The first plate may be difficult to create, but once it exists, copying becomes far simpler. At nanoscale dimensions, however, simpler is a dangerous word. Prenano says its equipment can reproduce features below 10 nanometers. At that scale, dust is not dust, it is a boulder. A trapped air bubble becomes an empty neighborhood where the pattern never formed. Slightly uneven pressure can change how deeply the resist fills different regions. A warped template can touch the center while missing the edge. During separation, fresh structures can stretch, tear, or cling to the mold. The concept is elegant. The contact is where elegance meets trouble. Nano-imprint has attracted attention for decades because its advantages are difficult to ignore. It can reproduce extremely small structures without an optical system capable of resolving them, and it may copy a large repeated pattern in one operation, yet it never simply replaced optical lithography. The first obstacle was defects. Because the template physically approaches the wafer, a contaminating particle can damage the pattern or the mold itself. A defect on the template can then be printed repeatedly, like a scratch appearing on every copy from a damaged stamp. The second problem was uniformity. The resist remaining below the pattern must be thin and predictable. Too much material in one region and too little in another can make later etching inconsistent. Then comes separation. Pressing down is only half the process. The template must release cleanly without pulling the structures apart. Alignment is another challenge. Most chips require multiple layers, and each new layer must land precisely over the last. The demands become especially severe for dense logic devices. Finally, there is speed. Contact, curing, and separation take time. In a high-volume factory, seconds matter. Nano-imprint could produce impressive demonstrations. The difficult part was producing reliable copies, wafer after wafer. Pernano's latest claim centers on a machine designed for full wafer imprinting. The PLAS is described as a semiconductor-grade vacuum pneumatic nano-imprint system. Rather than pressing one small field, moving and repeating, it is intended to imprint a large wafer area in one operation. Vacuum matters because removing air can reduce bubbles trapped beneath the template. Pneumatic matters because controlled air pressure can distribute force across the wafer more evenly. Imagine pressing a large decal onto a surface using one hard block. Some areas touch first, others receive too much force. Wrinkles appear. A pressure cushion can conform more evenly across the area. Pernano says its face contact method keeps pressure non-uniformity below 0.5%. It also claims residual layer variation below 2 nanometers and resolution below 10 nanometers. Those are company specifications, not a complete independent production report. But they show what the engineers are targeting: equal contact, equal thickness, and repeatable replication across the wafer. The equipment is only one part of the answer. Pernano and Litra also used a customized 2-layer resist system and matching process. That detail is critical. Nano-imprint is not merely a machine pressing downward. It is a relationship between the mold, resist, pressure, curing, release chemistry, and the etching that follows. Change one element and the others may have to change with it. Here is the distinction that makes this story credible. The wafers described in the announcement are for photonic chips, not cutting-edge CPUs or GPUs. Electronic processors manipulate electrical signals. Photonic chips guide and control light. They can contain waveguides that behave like microscopic optical rods, splitters that divide light, gratings that send it in selected directions, resonators that filter wavelengths, and phased arrays that steer beams. These structures can be extremely precise, but many are also repetitive. A grating may contain rows of similar lines. An optical antenna array may repeat one element hundreds or thousands of times. That repetition is where a physical template becomes attractive. A modern logic processor resembles a dense city whose streets and buildings change from block to block. One particle in the wrong place can destroy a critical intersection. A photonic structure can sometimes resemble a carefully arranged field of rails, mirrors, or fence posts. It is still difficult to make, but its geometry may be more compatible with replication. This does not make photonic chips easy. Optical performance is highly sensitive to roughness, width, and dimensional error. A slightly imperfect waveguide can scatter light or shift the device's behavior. But nano-imprint does not need to conquer every semiconductor process to become valuable. It only needs to outperform existing methods where repeated optical structures make stamping practical. The partner in this announcement provides another clue. Shenzhen Litra Technology develops LiDAR systems and optical phased array chips. LiDAR measures distance by sending light into the environment and analyzing what returns. Traditional systems often steer the beam using rotating assemblies or moving mirrors. Those mechanisms can work, but they add size, cost, and wear. An optical phased array attempts to steer light electronically. The principle resembles phased array radar. Instead of rotating one transmitter, the chip controls the phase of many tiny emitters. Their waves reinforce one another in one direction and cancel in others. Change the phase pattern and the beam points somewhere else. No spinning turret is required. To make that practical, a chip may need large arrays of nanoscale optical elements with consistent geometry. That is a natural test case for imprinting. Pranano says the current cooperation focuses on production for Litra's optical phased array devices aimed at vehicle and intelligent terminal applications. Mass production validation is not the same as millions of finished sensors already shipping, but this is more than a generic lab wafer. There is a product direction. There is a customer partner. And there is a reason this manufacturing method could lower cost. If these optical arrays can be copied over full wafers in fewer steps, solid-state LiDAR may become cheaper to build for vehicles, robots, industrial systems, and compact three-dimensional sensors. An 8-inch wafer is approximately 200 millimeters across. Leading processor factories generally use larger 12-inch wafers, but 8 inches remains a genuine industrial format for specialty semiconductors, sensors, and many photonic products. More importantly, covering a complete wafer is very different from printing one small square in a laboratory. A tiny sample is easier to keep flat. Pressure is easier to control. There is less area in which contamination can appear. Across a full wafer, small errors accumulate. The center and edge may behave differently. Resist may flow unevenly. A template may bend by an amount invisible to the eye but damaging to the device. That is why the 8-inch claim deserves attention. It suggests the process has moved from we can reproduce this pattern toward we can reproduce it across a manufacturing-sized surface. But the word suggests matters. The public announcement did not reveal how many wafers were processed, how many chips worked, how consistently the result was repeated, or what defect density was achieved. A full-size wafer is a milestone. Yield decides whether it becomes a business. Pranano says this route can reduce photonic chip manufacturing costs to 1/10 of a traditional DUV-based process. That is the company's estimate for the process it validated. It is not proof that every design, factory, or product will save exactly 90%. And it does not mean a $1,000 LiDAR sensor will suddenly cost $100. Lithography is only one stage. The master template must still be produced with extreme precision. Wafers require preparation and material deposition. Patterns may need etching. Chips must be tested, separated, packaged, and integrated into a final system. Yield matters too. A cheap patterning step that produces many defective chips can still create an expensive finished device. Template lifetime is another unknown. A mold that wears quickly or becomes contaminated can erase the apparent savings through cleaning, inspection, replacement, and downtime. Still, the possible advantage is understandable. The PLAS avoids the projection optics required by DUV equipment. It may replace several exposure or patterning operations with one replication step. A reusable template can spread its creation cost across many wafers. So the accurate interpretation is not, all photonic chips are now 90% cheaper. It is this. For the process Pranano and Litra say they validated, nano imprint reduced manufacturing costs to roughly 10% of the DUV route. That is still a huge claim. Now it needs equally strong evidence. Pranano has disclosed resolution, pressure uniformity, and residual layer control. It has not publicly provided all the figures that determine commercial success. We do not know the demonstrated wafer throughput. We do not know defect density across repeated production lots. We do not know the percentage of functional chips per wafer. We do not know how many imprint cycles one template survives before its performance changes. We do not have detailed independent comparisons showing optical loss, reliability, and lifetime against the same chip produced with DUV lithography. And we do not know every assumption behind the 1/10 cost estimate. That does not prove the announcement is wrong. It means commercial scrutiny is beginning, not ending. The semiconductor industry is unforgiving because a process can be technically brilliant and economically useless at the same time. A machine that creates perfect wafers slowly may lose to a more expensive machine producing acceptable wafers quickly. A cheaper process may lose if templates fail too often. Beautiful resolution means little if alignment and yield are unstable. Factories do not reward elegance. They reward working devices per hour, per tool, and per dollar. That is the scoreboard Pranano must eventually show. Even with those caveats, the strategy is clever. Instead of trying to replace mature logic chip processes immediately, Pranano is aiming at an application where geometry, wafer size, and cost may favor replication. Alternative technologies often enter established industries this way. They do not attack the strongest product first. They find the edge where their unusual combination of strengths and weaknesses becomes useful. For nano imprint, photonics may be that opening. Demand for light-based components is growing. Data centers need faster optical links. Networks need more transceivers. Robots and vehicles need compact sensing. Displays and augmented reality devices depend on precisely shaped optical structures. Not every one of those products will use this process, but they create a wide field of repeated nanoscale patterns where a physical template can compete. And when a manufacturing platform proves itself in one market, the lessons travel. Better templates, cleaner materials, longer mold life, faster separation, lower defect rates, improved alignment. The first successful product is not the final destination. It is the factory learning how to walk. My view is that this development is interesting precisely because it is not a universal replacement for DUV. A claim that one machine has made optical lithography obsolete would be easy to dismiss. The semiconductor industry is too varied, and different chips require radically different processes. But a machine does not need to replace everything to become disruptive. If the PLAS can reliably manufacture optical phased array chips across full 8-inch wafers, with competitive yield and anything close to the claimed cost reduction, it could change the economics of specific photonic products. The word to watch is reliability. Sub-10 nanometer resolution sounds spectacular. A 90% cost reduction sounds even better. Customers, however, will care about repeatability. The same pattern, the same optical behavior, and the same yield, wafer after wafer. That proof will take time. For now, this is a credible manufacturing direction. A nano-imprint equipment company and a LiDAR chip developer say they have placed full wafer stamping into an 8-inch photonic chip production flow. No giant optical projection system, no conventional DUV exposure step, just a master template, controlled pressure, specialized material, and an action that sounds almost primitive until you understand the scale. Stamp the pattern, cure it, lift the mold, repeat. Sometimes the next step in high technology is not a more complicated machine. Sometimes it is a simpler action performed with impossible precision. So what do you think? Is nano-imprint the future of lower-cost photonic chips, especially for LiDAR and optical communications? Or will defects, template wear, and factory throughput keep DUV lithography ahead when real production volumes arrive? Let me know your view in the comments. And if you want more grounded stories about the machines, materials, and engineering breakthroughs reshaping technology, subscribe to Eastern Engine. Because the next major chip revolution may not be projected with light. It may be pressed into place. China just spent over $1 billion on glass. You read that right. Not on transistors, not on the giant machines that print them, on glass. And that single, strange-sounding bet may have just exposed the one weakness sitting underneath every advanced chip on the planet. A weakness almost nobody outside the industry is talking about. Here's what makes this the most fascinating story in technology right now. It isn't really about what China built. It's about what China understood that the rest of the industry quietly overlooked. While everyone else was fighting over one part of the chip, China looked at a completely different part, the part holding the whole thing together, and realized that's where the real bottleneck was about to appear. By the end of this video, you'll understand exactly what that weakness is, why it's getting worse at the worst possible moment, why glass is the unlikely answer, and why a single billion-dollar bet could reshape who controls the next decade of computing. Let's get into it. For the last several years, the global conversation about chips has revolved around one thing: making transistors smaller. Who can shrink them further? Who can pack more of them onto a piece of silicon? The entire industry, and a huge amount of government policy, has been organized around that single race. At the center of that race is a machine made by a Dutch company called ASML. Its extreme ultraviolet lithography systems are the only tools on Earth capable of printing the most advanced transistors onto silicon. Each machine weighs about as much as 2 fully loaded school buses. Each one costs close to $200 million. Only a tiny handful of suppliers worldwide can build even a single component inside one. These machines are, without exaggeration, among the most complex objects humanity has ever manufactured. So the logic that took hold across much of the industry was simple: control the machine, control the chips. Whoever can't access the most advanced lithography can't make the most advanced transistors, and therefore can't lead in AI. It's a clean argument, and it has one enormous blind spot. It only holds if shrinking transistors is the only path to more powerful computing. China, quietly and very deliberately, decided that it isn't. Think of it like a race where one competitor has locked up the world's only supply of racing tires. Most teams would spend years trying to reverse engineer that tire. China looked at the track instead and built a completely different vehicle, designed for a surface those tires were never made for. That surface is called advanced packaging, and the vehicle is glass. Here's the part most people don't realize. The most powerful AI processors being built today aren't really single chips anymore. They're clusters, dozens of smaller chips, called chiplets, wired together on a shared platform and designed to behave as one unified processor. That shared platform is called the substrate. It's the foundation everything sits on. It connects the chiplets to one another, carries the electrical signals between them, and helps manage the enormous heat they produce. If the chiplets are buildings, the substrate is the ground they're built on. And right now, that ground is made of organic material, essentially a very sophisticated, highly engineered form of plastic. This is the key reframing of the entire story. China isn't trying to outshrink anyone's transistors. China is trying to replace the floor that everyone else's chips are standing on. While the rest of the industry was guarding one door, China simply walked around the building. To understand why that's such a powerful move, you have to understand what's happening to those plastic foundations right now, and why they're starting to fail at the worst possible moment in the history of computing. Here's something the chip industry doesn't put in its marketing. The most powerful AI processors ever made are being held together by what is, at its core, a very advanced form of plastic. Not as a metaphor, literally. The substrate is built from organic resins and fiberglass weaves, materials that have served the industry faithfully for decades. Materials designed for a world where chips were smaller, cooler, and far simpler than what's being built today. That world is gone. The AI chips driving the current boom are enormous. A single advanced AI processor package today can stretch beyond 8,000 square millimeters. To picture that, lay 4 standard playing cards side by side. That's roughly the surface area. And across that entire surface sit billions of microscopic connections, all communicating at once, all generating heat, and all depending on one thing: the substrate beneath them staying perfectly, dimensionally still. Here's the brutal catch. It doesn't stay still. Organic substrates expand and contract with temperature. Every time a chip powers up, heats, and cools back down, the foundation moves. Not visibly, not dramatically. We're talking shifts measured in parts per million. But at the scale of a modern AI package, parts per million isn't a rounding error. It's a slow-motion disaster. Those microscopic connections, some of them finer than a strand of human hair, begin to drift. Slowly at first, then faster, until the clean electrical path between two chiplets becomes inconsistent, then degraded, then broken entirely. Think of a long suspension bridge in a heat wave. The cables don't snap, they just stretch slightly. But if every measurement in the original design assumed they'd never move, that slight stretch is enough to throw the whole structure out of tolerance. That's what's happening inside the most advanced AI chips on Earth right now. Not a dramatic explosion, a slow, invisible drift that engineers can measure but struggle to stop, because the material causing it is baked into 50 years of production lines, supply chains, and manufacturing processes. And here's the detail that puts it all in perspective. This problem was perfectly manageable when chips were small and AI workloads were modest. But the entire trajectory of AI hardware points in one direction: larger packages, denser connections, higher power, more heat. Every single variable that makes organic substrates struggle is getting worse at the same time. So the question was never whether plastic substrates would hit their limit. The question was who would have the replacement ready when they did. That replacement has a name, and what it can do sounds almost impossible. You've probably held the answer in your hand. Not in a chip lab, not in a data center, in your kitchen. A borosilicate glass dish, the kind you bake with, survives dramatic temperature swings without cracking or warping. You pull it from a hot oven, set it on a cool countertop, and it holds its shape. That stability isn't luck. It's a fundamental property of the material. Now scale that principle down to something thinner than a fingernail. Engineer it to tolerances that can only be verified under specialized lab equipment, and you start to understand what semiconductor-grade glass substrates really are. This isn't window glass. It isn't the glass on your phone screen. It's a purpose-built material designed to solve exactly the problems organic substrates can't. Start with stability. Where plastic expands and contracts with every heat cycle, glass holds its dimensional shape with the rigidity of steel. The connections printed onto its surface stay where they were placed, through power-up, through full load, through cool-down, with no drift, no degradation, no invisible creep pulling chiplets out of alignment. Then there's connection density. Today's best organic substrates can only pack so many electrical connections into a given area before signal interference and manufacturing limits make tighter spacing impossible. Glass can support up to 10 times that density. 10 times. And here's what makes it genuinely remarkable. Signal quality improves at the same time. Organic materials absorb and scatter electrical signals as they travel. Glass doesn't. A signal that enters one side arrives at the other, cleaner, faster, and with less interference. which means chiplets can communicate more reliably without the system constantly compensating for a degraded signal. But the real unlock isn't any single property. It's what they make possible together. Once you have a foundation that doesn't warp, that carries 10 times the connections, and that keeps signals clean across large distances, you can build chiplet packages that plastic could never support. Packages stretching far beyond today's limits, where designers stop worrying about the foundation failing and start designing for the limits of physics itself. That's the prize. Not a better chip, a better foundation that makes every chip better. So if glass is this good, the obvious question is, why hasn't everyone switched already? Picture a drinking straw. Now shrink it until it's thinner than a single strand of human hair. Now imagine drilling thousands of those perfectly vertical, perfectly parallel, perfectly spaced through a sheet of glass the thickness of a fingernail, without cracking it and without introducing a single invisible fracture that might only reveal itself months later under operating stress. Now imagine doing that millions of times a day, at a success rate high enough to actually make money. That's the through-glass via problem, and it's the reason glass substrates have been understood in theory for years while remaining out of reach in practice. A via is just a vertical electrical connection, a channel drilled through the substrate so signals can travel between layers. In plastic, vias are punched or laser drilled through forgiving, flexible material. Glass is neither forgiving nor flexible. It's rigid and brittle, and it punishes imprecision with fractures that spread invisibly through the material until the whole substrate fails. Sometimes during manufacturing, sometimes during testing, and sometimes, devastatingly, after the finished chip has already shipped. And drilling is only the first hurdle. Those holes then have to be filled with conductive metal, usually copper, bonded to the glass without creating stress at the interface. Glass and copper expand at different rates under heat. If that interface isn't engineered perfectly, thermal cycling creates microscopic separation between the copper and the glass wall. The via still looks intact. The signal path still measures clean, right up until it doesn't. Then there's the issue engineers don't love discussing publicly: yield, the percentage of substrates that survive the full process without a defect. Early pilot lines produced yields so low that the cost per usable substrate made commercial production impossible. You can't build a global supply chain on a material that fails more often than it succeeds. On top of that, there's flatness. A glass substrate has to stay flat to tolerances measured in single-digit micrometers across its entire surface, and 1 micrometer is roughly 1/70th the width of a human hair. Holding that flatness through the heat, chemicals, and physical handling of a full production line took years of dedicated engineering just to approach. And even after a company solves drilling, filling, yield, and flatness, it still has to qualify the whole process with semiconductor customers, a validation step that can take 2 to 3 years, during which the line earns almost nothing, while the capital sits committed. That combination, brutal process complexity, punishing yields, multi-year qualification, and enormous upfront cost, is exactly why most of the industry treated glass substrates as a long-term research project rather than an urgent priority. China looked at those same barriers and saw something completely different, a moat it could cross before anyone else even arrived at the water's edge. Here's what most people get wrong about China's position. They assume China is starting from scratch, throwing money at a brand new technology and hoping state funding alone can compress decades of learning into a few years. That's not what's happening. China isn't starting from scratch. It's redirecting. There's a company called BOE. Outside the display industry, most people have never heard of it. Inside it, BOE is impossible to ignore. It's one of the largest manufacturers of display glass on Earth, the panels inside televisions, monitors, tablets, and smartphones. Its facilities are so vast that a single BOE campus can cover more floor space than many international airports. And to make display glass at that scale, BOE spent years building exactly the kind of precision, large-format glass handling infrastructure that semiconductor substrate production requires. Think about what that means: precision glass cutting at massive scale, flatness control across large surfaces, high-volume process lines where tolerances are measured in micrometers and yield is tracked obsessively, because a failed panel at the end of a line is a direct hit to profit. The equipment categories are different, the end product is different, but the manufacturing discipline, the process philosophy, and the capital infrastructure are directly transferable. And this is the part that reframes everything. The glass substrate challenge isn't primarily a material science problem anymore. The physics are understood, the engineering principles are established. The real problem is manufacturing, handling precision glass at high volume with the process control and yield management that commercial production demands. And that's the exact category of problem BOE has been solving at scale for years. Not for chips, for screens. But the muscle memory is the same. BOE isn't alone either. Several other Chinese firms have been attacking the through glass via problem directly. The drilling, the filling, the bonding, the yield, with serious capital and real urgency. That only makes sense if the goal isn't a research paper, but production volume. And much of this has been backed by China's national semiconductor investment funds, the same coordinated state machinery that has a track record of turning strategic priorities into industrial reality, however long it takes. Numbers can feel abstract until you give them a shape. So here's the shape of this one. Since 2023, China's national semiconductor funds, combined with direct corporate investment, have directed over $1 billion specifically into glass substrate technology, not into basic research, into production-oriented engineering, yield improvement, process qualification, through glass via scaling, and the supply chain infrastructure needed for commercial volume. And here's what that number tells you, that the figure alone doesn't. Investment at that scale, aimed at that specific problem, with that level of coordination, doesn't happen because someone found an interesting paper at a conference. It happens because a strategic decision was made. A decision that this technology will define the next generation of chip packaging, and that China intends to lead it. That decision appears to have been made around 2022, at roughly the same moment much of the rest of the industry was confident it had the chip race locked up through lithography. And $1 billion isn't the ceiling. It's the foundation. A single glass substrate production line can cost between $500 million and $1 billion to build and qualify. So the money already deployed was enough to seed the process learning. Reaching full volume will require multiples of that, and in China's model, once the strategic value is proven, the capital follows. Here's why this is the most time-sensitive part of the whole story. Semiconductor manufacturing rewards the first mover in a way that compounds and becomes almost impossible for latecomers to undo. It's not just about owning the equipment, it's about the process knowledge that accumulates on a real production line over months and years of running real material through real tools and solving real problems. That knowledge doesn't transfer through patents or papers. It lives in the engineers, in the process recipes, in a team that has seen 10,000 failure modes and learned how to avoid almost all of them. Whoever reaches volume production first accumulates that knowledge first. And the customers who qualify their supply chains against that producer won't switch lightly, because requalifying costs time, money, and risk no chip designer wants to absorb without a very good reason. This is precisely the dynamic that made TSMC nearly untouchable. TSMC didn't win because it had permanently better equipment than everyone else. It won because it reached volume first, learned faster than anyone could catch up, and locked in customers whose own roadmaps became dependent on its process generations. Competitors have spent decades trying to close that gap. China studied that exact dynamic, and is now trying to recreate the conditions that created it, in a part of the market the rest of the industry wasn't defending. Here's what makes this different from earlier chapters in the chip story. Most technology races have a catch-up mechanism. A competitor falls behind, studies the leader, and slowly closes the gap. Painful and expensive, but possible. That's how memory and logic leadership has shifted between countries before. Glass substrates may not work that way, because the advantage being built isn't just a technology lead, it's a compounding knowledge lead. The moment any company reaches volume production, every substrate that runs through the line teaches the process something. Every failure mode solved becomes institutional knowledge that can't simply be bought or copied. The customer who qualifies against that line builds their next chip generation around its specifications, and at that point switching stops being a purchasing decision and becomes a full product redesign. That's not a supply relationship, it's a dependency, the kind that can define an industry for decades. That's exactly why the biggest names in the field, Intel, Samsung, TSMC, and the glass specialist Corning, are now moving on glass substrates at a pace none of them originally planned. Intel has one of the longest track records in the technology and has shifted toward licensing its know-how. Samsung is running an active pilot line. TSMC revived its glass research program. Corning is positioning to supply the raw semiconductor-grade glass itself. The technology that much of the industry once filed under someday is suddenly an urgent priority for everyone. And when you zoom all the way out, here's the real takeaway. The next era of computing may not be decided by who prints the smallest transistor. It may be decided by who owns the foundation those transistors sit on. Every AI model, every data center, every autonomous system built in the next decade will run on chips, and those chips will run on substrates. Whoever owns that foundation and locks in the customers around it holds a position that's extraordinarily hard to dislodge. That's what $1 billion in glass may have actually bought. Not just a product, a position. Here's my honest opinion, for what it's worth. What I find most striking about this story isn't the glass itself, it's the strategic lesson hiding inside it. The entire industry fixated on one highly visible part of the chip and built its whole worldview around controlling it. Meanwhile, a parallel path to more powerful computing was quietly being developed in a completely different layer, using manufacturing skills borrowed from an industry, display screens, that nobody was watching. The decisive move in a technology race is so often not the thing everyone is staring at. I think the hierarchy of the chip industry is going to get reshuffled more than most people expect over the next few years, and the substrate layer is a big reason why. The lead that exists today is real, but it is absolutely not locked in. This is still an open race, and whoever takes it most seriously right now is the one who will shape how it plays out. Here's the question I genuinely want your take on, and be honest, because people get heated about this one. Is it a good thing when one country pulls ahead in a technology this foundational? Because competition drives faster innovation, or does the world work better when no single place controls the infrastructure everything else depends on? There are real arguments on both sides. Where do you land? Tell me in the comments. If you enjoy these deep dives that get underneath the headlines and explain what's really happening before the rest of the world catches on, subscribe to Eastern Engine and turn on notifications. We break down the materials, the supply chains, and the strategic moves that decide who leads the next decade of technology, and there's a lot more coming. Thanks for watching. I'll see you in the next one. For decades, analog computing carried a reputation for being fast but unreliable. Digital computers won because they could repeat the same calculation with predictable precision. Every value became a sequence of zeros and ones. Analog machines worked differently. They represented numbers with continuously changing physical quantities such as voltage, current, pressure, or resistance. That allowed them to solve some equations almost instantly, but tiny errors accumulated. Components drifted. Precision collapsed as problems became larger. Researchers at Peking University now say they have solved much of that problem. Their team built a foundry-made analog matrix solver using resistive random access memory, or RRAM. The system experimentally solved 16 by 16 real-valued matrix inversion problems at 24-bit fixed-point precision, which the researchers describe as comparable to FP32 digital computing. In massive MIMO signal detection, it reached digital-level accuracy after only 3 refinement cycles. And their benchmarking suggests that, with further circuit improvements, this architecture could deliver up to 1,000 times higher throughput and nearly 100 times better energy efficiency than leading digital processors at the same precision. That does not mean this prototype can run every AI model 1,000 times faster than an NVIDIA H100. It cannot replace a general-purpose GPU. The result applies to specialized matrix equation workloads, and the largest advantage is partly projected rather than fully measured in production hardware. Analog computing has always promised extraordinary speed. The missing piece was precision. Why digital computers dominated. A digital computer treats information as discrete values. At the lowest level, a transistor is interpreted as on or off. Software then performs arithmetic through carefully sequenced logic operations. Small electrical fluctuations usually do not change a 0 into a 1. Digital systems can use error correction, repeat operations, and store exact copies of data. Analog systems trade some of that certainty for direct physical computation. Imagine solving a mathematical equation by building an electrical circuit whose voltages naturally settle into the answer. The circuit does not need to execute millions of separate instructions. The physics performs the calculation as the signals move through the hardware. But real components are imperfect. Resistance changes with temperature. Amplifiers introduce noise. Manufacturing creates small differences from one device to another. The answer may be close, but not exact enough for scientific computing, communications, or modern AI. The Peking University team attacked the problem by separating speed from accuracy. One analog circuit produces a fast, approximate answer. A second analog operation measures the remaining error and corrects it. The system repeats this process until the solution reaches the required precision. What RAM actually does. The heart of the design is resistive random access memory. An RRAM cell stores information by changing the electrical resistance of a material between 2 electrodes. A low resistance state may represent one value. A higher resistance state may represent another. In this experiment, each cell supported 8 stable conductance levels, equivalent to 3 bits of information. The researchers used a 1 megabit RRAM chip for high-precision matrix vector multiplication and a smaller 8x8 RRAM array for low-precision matrix inversion. Both were fabricated using a commercial 40-nanometer CMOS platform. This was not a hand-built device assembled from exotic laboratory materials. The chips were produced through a foundry-compatible process, using 1 transistor, 1 resistor memory cells. An RRAM array can behave like a physical matrix. Each cell's conductance represents 1 matrix element. Input voltages represent a vector. When those voltages pass through the array, the resulting currents naturally combine according to Ohm's law and Kirchhoff's current law. The array performs matrix vector multiplication through its physical behavior. A digital processor would normally load data from memory, execute many multiplication and addition instructions, then write the result back. The RRAM array stores the values and performs the calculation in the same location. That reduces data movement and avoids much of the conventional von Neumann bottleneck. The matrix problem. Matrix equations appear almost everywhere in advanced computing. Wireless base stations solve them to separate overlapping signals from many antennas. Some neural network training methods also depend on matrix inversion or related linear system solving. A common form is A times X equals B. The matrix A and vector B are known. Digital methods solve this accurately, but the cost grows quickly as the matrix becomes larger. An analog circuit can produce a solution directly by placing the resistive array inside a closed feedback loop with operational amplifiers. However, the first answer is only approximate. The challenge is improving that result without handing the important calculation back to a digital processor. Earlier hybrid systems often used analog hardware for a rough estimate and digital floating point hardware for the precise correction. The Chinese team kept both major operations in the analog domain. How the two-stage solver works. The first stage performs low-precision analog inversion. Because the RRAM devices and supporting circuits are not perfectly accurate, the result contains an error. The second stage performs high-precision analog matrix vector multiplication. It calculates how far the approximate answer is from satisfying the original equation. That difference is called the residual. The solver then feeds the residual back into the low-precision inversion circuit to produce a correction. Each cycle moves the solution closer to the target. The researchers reported that precision improved by roughly 3 bits during each cycle, reflecting the 3-bit conductance levels in the RRAM cells. A 24-bit 4x4 real-valued matrix reached the maximum target precision after 9 cycles. Larger complex-valued problems generally reach the same precision within about 10 cycles. This is the central idea. The fast analog inversion does not need to be perfect. It only needs to be good enough that repeated analog correction converges toward a precise answer. The design accepts analog error, measures it, and then removes it. That is very different from pretending the hardware is naturally exact. How bit slicing builds precision. One RRAM cell stores only 3 bits, but the complete system reaches 24-bit precision. It does this through bit slicing. A high-precision matrix value is divided into several lower-precision pieces. Each piece represents a different group of bits and is mapped into a separate RRAM array. The arrays perform low-precision calculations in parallel or sequence. Their partial outputs are then shifted according to their significance and added together. It is similar to separating a large decimal number into thousands, hundreds, tens, and units. Each part is easier to represent. Combining the weighted parts reconstructs the original value. Bit slicing was already useful for analog matrix vector multiplication. The harder problem was applying high precision to matrix inversion, where the same simple distributive rules do not transfer cleanly. The researchers solved this by keeping inversion low precision, while using bit-sliced matrix vector multiplication to calculate the correction accurately. Block AMC makes the design scalable. A physical RRAM array cannot grow without limit. Large arrays suffer from wire resistance, routing complexity, stronger currents, parasitic effects, and amplified noise. The team therefore used a block-based algorithm called block AMC. A larger matrix is divided into smaller submatrices. Different RRAM arrays store different blocks. The system performs a sequence of inversion and multiplication operations on those blocks, then combines the intermediate results. Using this approach, the researchers experimentally solved a 16 by 16 real-valued matrix inversion problem with 24-bit fixed-point precision. The relative error reached roughly 1 part in 10 million after 10 cycles. 16 by 16 may sound small compared with giant AI models, But matrix inversion is more difficult to map into analog hardware than ordinary multiplication. The point was to prove that a precise analog solver could scale beyond one tiny hardwired circuit. The block method also allows future systems to use multiple moderate-sized arrays instead of depending on one enormous analog network. The massive MIMO test. The researchers demonstrated the solver on wireless signal detection. Massive MIMO uses many antennas at a base station to communicate with several devices at once. The received signals overlap. The base station must solve matrix equations to separate the different users and recover the transmitted information. The experiment modeled systems using higher-order 256 QAM modulation, which packs 8 bits into each transmitted symbol. That demands far more precision than earlier analog demonstrations limited to simpler modulation. The researchers transmitted a binarized image of the Peking University emblem through the modeled wireless channel. Their analog solver recovered the signal with bit error performance comparable to FP32 digital processing. For a 128 by 8 system, the detector reached comparable accuracy after only 3 iterative cycles. This matters because it connects the architecture to a real workload rather than only random laboratory matrices. Wireless communication, especially future 5G advanced and 6G systems, may require repeated matrix solving with strict limits on latency and energy. Where the 1000x claim comes from. The 1000 times figure needs careful explanation. The prototype did not directly defeat an NVIDIA H100 by 1000 times in a complete application. The researchers benchmarked their analog architecture against state-of-the-art digital processors at comparable precision. Their model considered matrix size, array dimensions, converter overhead, amplifier speed, and block processing requirements. At moderate array sizes, the analog design already showed advantages for specific matrix solving tasks. For larger optimized arrays and faster operational amplifiers, the projected throughput advantage could approach 3 orders of magnitude. Energy efficiency could improve by nearly 2 orders of magnitude. The paper also notes that block AMC reduces the advantage as matrices become larger because more stages and intermediate operations are required. Even then, the architecture remained ahead in the researchers' comparisons. The maximum result depends on better supporting circuits and dedicated integration. So the honest statement is that the demonstrated architecture could reach 1000 times higher throughput for precise matrix equation solving. It is not evidence that an analog chip will make every CUDA workload 1000 times faster. Why this could matter for AI? Modern AI depends heavily on matrix operations, but not every matrix operation is the same. Neural network inference is dominated by matrix multiplication. This chip focuses on matrix inversion and solving linear systems. Those operations appear in optimization, scientific machine learning, signal processing, and some second-order training methods. An analog solver could become a specialist accelerator. A conventional CPU or GPU would manage the overall program. When the workload reaches a suitable matrix equation, the system could send that task to the RAM solver. The analog hardware would produce the answer quickly and efficiently, then return it to the digital processor. This is more realistic than expecting analog computing to replace digital machines completely. Digital hardware remains better for control flow, memory management, software compatibility, and exact general-purpose operations. Analog hardware may win by handling the narrow calculations where physics offers a shortcut. The honest catch. Several engineering challenges remain. The low-precision inversion circuit still uses external components, including operational amplifiers, data converters, switches, and a microcontroller. The larger, high-precision RAM array was integrated, but the complete solver was not one compact commercial chip. Scaling the inversion array beyond the demonstrated size requires dedicated design and fabrication. Larger arrays produce stronger currents and more complicated routing. Noise, wire resistance, device defects, and temperature variation must remain controlled. The system also needs programming and verification procedures to place every RAM cell into the correct conductance state. Converters and amplifiers consume area and energy, and commercial software would need tools that identify suitable equations and map them efficiently onto the hardware. It does not prove that mass production will be easy. My take is that the breakthrough is not simply bringing analog computing back. It is making analog error part of the algorithm. The first circuit is allowed to be imperfect. The second measures that imperfection. Repeated correction turns a rough physical answer into one approaching digital precision. That is a powerful design philosophy. Future computers may not choose between analog and digital. They may combine both. Digital processors will coordinate the system and preserve programmability. Analog accelerators will solve selected equations using currents, resistance, and feedback, instead of long sequences of instructions. The 1,000 times estimate may shrink once complete commercial overhead is included, or better integration may allow the architecture to approach its projected advantage. Either way, this work moves analog matrix solving from a low-precision curiosity toward a credible specialist technology. So what do you think? Will analog accelerators become essential for AI, science, and 6G? Or will manufacturing variation and software complexity keep GPUs in control? Let me know your view in the comments. And subscribe to Eastern Engine for more grounded coverage of the chips, materials, and engineering breakthroughs reshaping computing. Because China has not built a universal NVIDIA replacement, but it may have solved the precision problem that kept analog computing out of the modern chip era. There is a country that most of the world rarely thinks about when the conversation turns to ambitious engineering. And yet, over the past few decades, this country has quietly been building some of the most surprising infrastructure projects on the planet. Projects that, in many cases, barely register in international headlines. We are talking about the largest shopping complex on Earth, a railway network spanning 15,000 kilometers, an underground metro system so visually striking that travelers stop walking just to look at the ceilings, a car manufacturing industry that ranks among the 15 largest in the world, and perhaps the most audacious project of all, an effort to take seawater from the ocean and move it hundreds of kilometers inland to transform desert into livable land. That country is Iran, and whatever your views on its politics, the scale of what its engineers have built is genuinely worth understanding. This video is going to walk through these projects one by one, and some of them get more remarkable the deeper we go. Let's start with the one that sounds most unbelievable. When people think of the world's biggest malls, they usually picture Dubai or the United States. The actual record holder sits next to Chitgar Lake in northwest Tehran. Iran Mall covers nearly 2 million square meters across 7 enormous floors, making it the largest shopping complex in the world by total area, larger even than the famous Dubai Mall. The construction effort required more than 25,000 workers and over 1,000 contractors. At one point during the build, crews poured concrete continuously for 6 straight days, setting a Guinness World Record for the largest continuous concrete pour. But the scale is not really the interesting part. The interesting part is what is inside. The complex houses 12 cinemas, including IMAX screens, a full Olympic-sized ice rink, a 2,000-seat theater, a luxury hotel, a convention center, and rooftop sports courts. It also contains a library holding over 45,000 books and manuscripts, a mirror hall constructed from an estimated 38 million individually crafted mirror pieces, and a traditional bazaar designed to echo the historic markets of Isfahan, Shiraz, and Tabriz. The intention was never to build a simple shopping destination. It was designed to function as a self-contained world, a place where the architecture itself is the attraction. The shopping mall was a concept popularized in America. Iran took that concept and scaled it to a size few people thought was practical. Iran does not only build at scale. Some of its most celebrated work is about beauty and design, and one project in particular became a global architectural sensation, designed by an architect who was only in her 20s when she conceived it. Layla Aragian was a young Iranian architect when she looked at a busy highway cutting between 2 parks in Tehran and asked a deceptively simple question. What if a bridge could become part of the natural landscape rather than just passing over it? The result was the Tabiat Bridge. Tabiat means nature in Persian, and the structure lives up to the name. It stretches 270 meters in length and rises 40 meters above the highway below, with 3 full levels containing walking paths, cafes, seating areas, and open viewing platforms offering panoramic views of Tehran and the snow-capped Alborz Mountains. 3 large supporting columns hold the structure up, deliberately shaped to resemble trees with branches spreading outward to echo the surrounding parks. The engineering is serious. Roughly 2,000 tons of steel and 14,000 individually cut components, designed to withstand earthquakes above magnitude 7 and built to last a century. The bridge has won several of the most prestigious architecture awards in the world, including the Aga Khan Award for Architecture. In its first year alone, around 4 million people visited, and most of them did not come to cross from one park to the other. They came simply to experience the structure itself. Iran's railway story stretches back nearly a century and connects to one of the most impressive engineering legacies in the region. The country operates a railway network spanning roughly 15,000 kilometers, one of the largest in the Middle East. That network moves tens of millions of tons of freight and tens of millions of passengers every year. And its foundations are remarkably old. The original Trans-Iranian Railway was constructed between 1927 and 1938. It crossed 2 mountain ranges and 4 distinct climate zones, requiring 174 major bridges and 224 tunnels to complete. It is now recognized as a UNESCO World Heritage Site, a testament to engineering ambition that predates most modern construction technology. What is striking about Iran's infrastructure culture is the speed of repair when something goes wrong. There are documented cases of major railway bridges being restored to operational status within a matter of days, rather than the months such work typically takes elsewhere. A civilization with thousands of years of building history tends to approach repair and reconstruction with a particular kind of practiced efficiency. Beneath the streets of Tehran sits a transportation system that very few people outside Iran are aware of, and it ranks as the largest metro network in the Middle East. More than 3 million passengers ride the Tehran metro every single day. The system includes over 310 kilometers of track and more than 160 stations, with trains arriving every 3 minutes during peak hours. The expansion plans are ambitious. By 2040, the network is projected to reach 500 kilometers of track and 330 stations across 11 lines. But what makes the system genuinely remarkable is the design of the stations themselves. Many of them feel less like subway platforms and more like underground galleries, featuring Persian mosaics, intricate geometric ceilings, detailed artwork, and grand halls that prompt passengers to pause and look around. The system is also impressively modern in its features: fully accessible stations, smart card and QR code ticketing, dedicated carriages, and comprehensive security infrastructure. In 2022, Iran unveiled its first fully domestically manufactured metro train set, certified to meet European safety standards, with passenger service beginning in 2024. And the fare for a ride of any distance remains remarkably low by international standards. One station in particular drew worldwide attention when it opened in October 2025. The Maryam-e-Moghada station, named in honor of the Virgin Mary, the mother of Jesus in Christian tradition, was built with an architectural style that blends Persian geometric design with church-inspired elements. The station features vaulted arches, a large decorated dome, religious frescoes, and sculptures referencing Christian iconography. It took roughly a decade to complete, and when photographs of the station spread online, they captured global interest precisely because of the cultural blend it represented. A thoughtful piece of architecture, honoring a figure revered across multiple faith traditions. Iran's rail offering extends well beyond commuter transport. One of its premium long-distance services has earned a reputation that rivals luxury hotels. The Fadak Express is often described by Iranians not as a train but as a moving 5-star hotel. It runs at speeds up to 200 kilometers per hour, connecting Tehran with Mashhad, Shiraz, and Qom. Its coaches were comprehensively redesigned under the supervision of a Swiss engineering firm, with upgraded air conditioning, electrical systems, and interiors built around a combination of Iranian aesthetics and high-end comfort. Each private compartment accommodates only 4 passengers and comes fully equipped with an entertainment system, charging outlets, and sound insulation effective enough that the movement of the train is barely audible. Meals are included in the ticket price, with catering quality compared to some of Iran's finest restaurants. The service offers 5 travel classes, ranging from economy to a premium tier that includes dinner and a hotel stay. The result has been a notable shift in traveler behavior. People who previously flew between Iranian cities began choosing the Fadak instead, not because it was cheaper, but because the overall experience was simply more pleasant. While Iran is rarely associated with car manufacturing in global conversation, the country has quietly developed an automotive sector that ranks among the largest in the world. Iran Khodro, commonly known as IKESO, was founded in 1962. Today, Iran ranks as roughly the 13th largest automobile producer globally, manufacturing more than 1.3 million vehicles annually. IKESO sits at the center of that production, and its vehicles are notable for being designed specifically for Iranian conditions rather than simply assembled from foreign designs. The Samand became Iran's national vehicle and was exported to countries including Venezuela, Belarus, and Azerbaijan. The Dena, named after a peak in the Zagros Mountains, featured a turbocharged engine producing around 150 horsepower. The Runa was developed as domestic intellectual property and proved successful enough to be adopted as a national vehicle in Tunisia. And in 2024, Ikeso unveiled the Rira, including a fully electric variant. That last detail is worth pausing on, because Iran was experimenting with electric vehicle development as far back as 2010, well before electric cars became a mainstream topic across much of the region. Beyond passenger vehicles, the Baumann Group, founded in 1952, has built an export business in trucks and vans serving markets across multiple continents. One of Iran's most significant energy infrastructure projects involves a pipeline designed to connect it with neighboring Pakistan. The Iran-Pakistan gas pipeline, sometimes called the Peace Pipeline, was designed to carry natural gas from Iran's South Pars field, one of the largest natural gas fields on Earth, across roughly 2,700 kilometers to Pakistan. Iran completed its 1,100-kilometer section by 2012, on schedule using domestic engineers and technology. Pakistan's portion of the project, however, has faced extended delays for a range of complex political and economic reasons. The Iranian section sits ready, the gas is available, and the two neighboring countries have a clear complementary need, one with abundant gas supply, the other with significant energy demand. Many regional energy analysts have noted that if the obstacles to completion were resolved, the project could become one of the more impactful energy initiatives in the region, potentially supplying gas to millions of homes and supporting industrial activity. For now, the infrastructure on the Iranian side waits, a completed piece of engineering held back primarily by factors outside the realm of construction. Here is where Iran's ambition becomes genuinely remarkable, because the country faces a fundamental geographic challenge. A large majority of its territory is arid desert, and much of its rainfall occurs along coastal regions far from where tens of millions of people actually live. Iran's response has been to engineer its own water security on a massive scale. The country has constructed more than 600 dams, which at one point ranked it among the top 3 dam-building nations in the world. Collectively, these dams store an enormous volume of water, making Iran one of the largest water storage nations in its region. The flagship of this effort is the Karkhe Dam, the largest dam in Iran and one of the largest in the Middle East. It generates electricity, irrigates agricultural land, and manages billions of cubic meters of water, built largely through domestic engineering expertise. But storing water solved only part of the problem. The water existed. It was simply in the wrong place geographically. So Iran undertook one of its most ambitious projects yet, moving water from the sea to the dry interior. At the center of this effort is an interbasin water transfer system anchored by a large desalination network near Bandar Abbas. Built by Iranian engineers using domestic technology, the system draws water from the Persian Gulf and the Sea of Oman, and pumps it through roughly 3,700 kilometers of pipelines to reach drought-affected provinces in the interior. To put that distance in perspective, it is longer than the distance from London to Cairo. The main desalination hub alone can produce around 1.5 million cubic meters of fresh water per day, with longer-term plans to serve tens of millions of people across dozens of facilities. A significant portion of the supporting infrastructure, including a major plant on Chesham Island, was constructed using domestically produced components, in part because importing certain parts was not an option, so Iranian engineers manufactured them locally. This is the project that gives the video its title. The idea of taking ocean water and forcing it hundreds of kilometers inland to make the desert livable sounds almost impossible. Iran is doing it. Moving and processing that much water requires enormous amounts of energy, and Iran's answer included nuclear power. The Bushehr nuclear power plant holds the distinction of being the first civilian nuclear facility in the Middle East. Its history is unusually long and complicated. Construction was initially started by a German firm in 1975, then abandoned after the political changes of 1979, and the site sat incomplete for decades. The plant was eventually completed with Russian assistance and connected to Iran's power grid in 2011, more than 3 decades after work first began. Since then, it has produced tens of billions of kilowatt-hours of electricity. 2 additional units are currently under construction, and Iran has set a long-term goal of significantly expanding its nuclear generation capacity over the coming decades. The story of Bushehr is, in many ways, a microcosm of Iran's broader infrastructure approach. Projects that take a very long time, face repeated setbacks, and get completed anyway. What strikes me most about all of these projects, when you lay them out together, is the underlying pattern. Iran's engineering culture seems to operate on a principle of self-sufficiency that has produced genuinely impressive results, regardless of external constraints. When parts could not be imported, engineers manufactured them domestically. When a needed technology was not available, the country developed its own version. The Tabiat Bridge, the desalination pipelines, the domestically built metro trains, the car industry. Across all of these, there is a consistent theme of building capability internally rather than waiting for external solutions. I find that fascinating from a pure engineering standpoint, because necessity-driven innovation often produces solutions that are more creative and more durable than projects developed under comfortable conditions. Iran has thousands of years of building history behind it, and that long-term perspective shows up in how the country approaches construction, patiently, ambitiously, and with an apparent willingness to attempt things others consider impractical. Whether these projects reach their full potential will depend on many factors that extend well beyond engineering. But the work itself, viewed purely as feats of construction and design, deserves far more recognition than it typically receives. My question for you is this: which of these projects surprised you the most? The world's largest shopping complex, the museum-like metro stations, or the effort to pipe ocean water across the desert? Let me know in the comments, because I genuinely did not expect some of these to exist before researching this, and I am curious whether you felt the same. If you enjoy deep dives into the engineering and infrastructure stories that most media overlooks, please subscribe to Eastern Engine and turn on notifications. We cover the projects reshaping the world with the depth and curiosity they deserve. There is a lot more coming, and you do not want to miss it.
So Apple looking for relief from the chip crunch behind this week's Mac and iPad price hikes. And I'm told by a person briefed on the discussions, that includes asking the administration for more flexibility to work with Chinese memory suppliers. And of course follows CEO Tim Cook telling the Journal just last week that all vendor options are back on the table. Now, the two key names in question are YMTC and CXMT, China's heavily state-backed domestic memory players. YMTC makes NAND flash storage, CXMT makes DRAM, the working memory.
China's largest memory chipmaker has reportedly secured a deal worth nearly $3 billion from Tencent, one of the biggest technology companies in the country. Just days after reports said Apple was asking Washington for political clearance to buy memory from the same Chinese supplier, Changshin Memory Technologies, better known as CXMT, has landed what may be the strongest commercial endorsement in its history. The reported agreement covers more than 20 billion yuan, or roughly $2.94 billion, in DRAM chips for Tencent servers over several years. That memory will support cloud computing, databases, and artificial intelligence workloads. CXMT is no longer being treated only as a protected domestic challenger. It is becoming a supplier that major Chinese technology companies may be willing to depend on at enormous scale. If Tencent is prepared to commit billions of dollars to CXMT, could Apple be next? It is a story about how the global memory shortage, the AI infrastructure boom, and political pressure are rewriting the semiconductor supply chain. For decades, the DRAM market has been dominated by three companies. Samsung Electronics, SK Hynix, and Micron control most global production. That concentration gave them enormous influence over pricing, technology, and supply. When demand rises faster than new factories can respond, there are very few alternative suppliers capable of filling the gap. AI data centers are consuming huge amounts of advanced memory. Large models need memory close to processors so data can move quickly enough to keep expensive computing systems busy. Cloud companies also require conventional server DRAM for databases, virtualization, storage systems, and general computing. High bandwidth memory receives most of the attention because it sits beside advanced AI accelerators. And when the biggest technology companies build infrastructure at the same time, demand spreads across the entire market. According to the latest reporting, DRAM contract prices rose roughly 95% quarter over quarter during the first quarter of 2026.
Used in iPhones, PCs, and servers. Both are young companies compared with Samsung, SK Hynix, and Micron, which built their businesses decades ago. But they are gaining share quickly. Counterpoint says YMTC now has 13% of the global NAND market, while CXMT has 8% of DRAM. CXMT also gaining ground fast, preparing for what could be mainland China's largest IPO in years. And Counterpoint is hearing from stakeholders in the supply chain that these Chinese memory names can
Large cloud companies do not want to enter every quarter uncertain about price, availability, or delivery. And in some cases, they are willing to provide prepayments or commit years in advance to secure supply. The reported CXMT agreement may run for 3 years, while another source suggested it could extend as long as 5. That means Tencent is not simply making a spot purchase to cover a temporary shortage. DRAM is one of the most difficult semiconductor businesses to enter. The product may look simple compared with a central processor or graphics chip, but manufacturing it profitably requires extraordinary precision. A memory producer must create billions of microscopic cells that store data reliably. Those cells must work at high speed, consume little power, survive repeated use, and maintain consistency across huge production volumes. That increases cost and makes it difficult to compete with established companies that have spent decades refining their processes. Its early products were aimed mainly at China's domestic market, and many international customers had little reason to take the company seriously. A company does not need to be the global technology leader to become strategically important. It only needs to offer acceptable products, meaningful capacity, and a willingness to sign contracts when other suppliers are constrained. The company reportedly held about 7.7% of the global DRAM market in 2025, making it the fourth largest producer. In a tight market, even a single-digit share can influence prices and customer negotiations. It currently operates major 12-inch DRAM fabrication plants in Hefei and Beijing, with combined output estimated at around 300,000 wafers per month. New facilities and additional expansion could eventually double that figure to approximately 600,000 wafers per month. The company is also developing operations in Shanghai, including DRAM production and high-bandwidth memory packaging. But Tencent's reported commitment gives CXMT something extremely valuable: demand visibility. It can help a manufacturer plan equipment purchases, staffing, material supply, and future process development. CXMT received approval in May for an initial public offering on Shanghai's Star Market. The company reportedly aims to raise 29.5 billion yuan. Investors want proof that growth is not based only on policy support or optimistic forecasts, and they want evidence that the company's products are important enough for large buyers to sign long-term commitments. Major Chinese technology companies are trying to reduce their exposure to foreign supply restrictions. Tencent, Alibaba, ByteDance, Lenovo, Xiaomi, and other firms all depend on semiconductors produced or controlled by companies outside mainland China. Export controls have already restricted China's access to advanced AI accelerators and semiconductor manufacturing equipment.
Undercut incumbent suppliers by up to 30% depending on the contract. Now, Apple, it's been here before. 4 years ago, the company explored using YMTC chips in China-sold iPhones, then retreated under pressure from Washington. But the shortage is more severe now, and Apple has a lot less leverage with its traditional suppliers. That's why more tech companies are looking for alternatives. HP and Lenovo are both reportedly pursuing Chinese memory as a way to diversify supply. But this is not a quick swap.
A cloud company cannot expand infrastructure if it cannot secure enough components. So Chinese technology firms have strong reasons to support a domestic supplier, even if that supplier remains behind the global leaders. This does not mean they will accept any product at any price. Large data center operators care about performance, failure rates, power consumption, compatibility, and total operating cost. Server memory must run continuously under heavy workloads. A defective module can create outages, corrupted data, or expensive maintenance. Tencent therefore has to believe that CXMT can meet a meaningful standard. That is why the reported agreement is more important than a symbolic government order. Tencent is not buying memory for a demonstration project. It needs chips for real servers supporting real customers. The contract could therefore become one of the strongest tests of CXMT's manufacturing discipline. Success would generate more than revenue. It would create operational data. Every shipment provides information about defect rates, system compatibility, thermal behavior, and long-term reliability. That feedback can help CXMT improve future products. Higher production volumes also allow engineers to identify recurring process problems and improve yield. Semiconductor manufacturing becomes more competitive through repetition. The more wafers a company processes, the more opportunities it has to learn. This is one reason large customers can accelerate a supplier's development. Tencent may be buying memory because it needs supply today, but the partnership could help create a stronger competitor tomorrow. That is where Samsung, SK Hynix, and Micron should pay attention. CXMT is not about to replace them. The established leaders remain ahead in manufacturing technology, scale, customer trust, and advanced products. They also dominate high-bandwidth memory, which currently delivers some of the strongest margins in the industry. CXMT still faces serious challenges. One reported problem is low yield on next-generation DDR5 products. That matters because DDR5 is increasingly important for modern servers and personal computers. A company can announce impressive specifications, but customers ultimately care about how many reliable chips can be produced at acceptable cost. If yield remains weak, expansion alone will not solve the problem. More factory capacity can simply produce more expensive defective wafers. CXMT must therefore improve technology while expanding volume. That is difficult, but the Tencent deal provides time and money. And if CXMT can use this period of high prices to improve yield, the competitive landscape could change. The memory industry is cyclical. Shortages produce high prices and heavy investment. High prices encourage companies to build more capacity. Eventually, supply catches up. Prices fall. Weak producers then struggle because memory becomes a commodity again. CXMT's challenge is to use the current upcycle to become efficient before the market turns. The company's recent financial performance shows how powerful the upcycle has been. Its first quarter revenue reportedly reached 50.8 billion yuan, an increase of about 700% from a year earlier. It also recorded a net profit of 25 billion yuan after reporting a loss in the previous year. Those numbers are extraordinary, but they should be interpreted carefully. A booming memory market can make almost every producer look stronger. The real test comes when prices normalize. Can CXMT still compete when buyers have more options? Can it maintain margins? Can it continue investing? And can it keep customers when Samsung, SK Hynix, and Micron have available capacity again? Tencent's long-term agreement may protect CXMT from some of that uncertainty. Now we come to Apple. Reports say Apple has been lobbying the United States government for clearance to purchase memory chips from CXMT. The request does not mean a contract has been signed. It does not mean CXMT memory is already inside MacBooks or iPads. And it does not mean Apple plans to abandon its current suppliers. Apple still depends on Samsung, SK Hynix, and Micron. But the company recently raised prices on several Mac and iPad models after memory and storage costs rose sharply.
Qualifying a new supplier can take months to as long as 2 years with device testing, reliability checks, factory audits, and technical sharing. And it's especially complicated with YMTC. It's been on the Commerce Entity List since 2022, meaning that U.S. companies need approval to share their blueprints and other proprietary details with them.
That makes another supplier extremely attractive. Apple does not need CXMT to replace the market leaders. It only needs CXMT to provide qualified products at meaningful volume. Even a limited supply agreement could strengthen Apple's negotiating position. It could reduce dependence on 3 dominant producers. And it could help Apple avoid even larger price increases if the shortage continues. The Tencent agreement may make CXMT easier for Apple to evaluate. A multi-billion-dollar server contract gives the company commercial credibility. It shows that another major technology buyer is willing to make a long-term commitment. But Apple's standards are different. For laptops and tablets, power consumption is critical. Memory affects battery life, heat, system stability, and product reliability. Apple also demands consistency across millions of devices. A supplier must deliver the same quality from one production batch to the next. It must support product launches, regional demand changes, and strict delivery schedules. So Tencent's approval would not automatically lead to Apple qualification. Server DRAM and low-power mobile memory serve different needs. Apple would still need extensive testing, audits, traceability, and supply guarantees. The political barrier may be even harder. CXMT is included on a Pentagon list of companies alleged to have links to China's military. That listing does not create a simple universal ban on every commercial transaction, but it creates serious political and reputational risk. American lawmakers may argue that allowing Apple to purchase from CXMT would strengthen a strategic Chinese semiconductor producer. They may also warn that Apple could become dependent on a supplier that Washington later restricts. Apple wants confidence before spending months qualifying products and redesigning logistics. A deal that is legal today could become impossible tomorrow. That uncertainty explains why Apple reportedly approached the government before moving forward. The White House has not publicly approved the request. Apple has not announced a supply agreement. And CXMT has not confirmed that it will supply Apple. So the title, Apple may be next, must remain a possibility, not a conclusion. Still, the Tencent deal changes the context. Before this agreement, CXMT could be described as a rising Chinese memory producer, seeking credibility. After a $3 billion commitment, it begins to look like a strategic supplier with major customers, rapid growth, expanding capacity, and access to capital. That does not guarantee Apple will follow, but it makes the possibility more believable. My take is that the most important part of this story is not the dollar amount. It is the speed at which CXMT's position is changing. A global shortage has turned capacity into leverage. AI demand has pushed memory from a commodity component into a strategic resource. Chinese technology companies are locking in domestic supply, and Apple is reportedly considering a supplier that would have seemed politically unrealistic only a short time ago. The old memory market was built around three dominant companies and predictable customer relationships. The new market is becoming more fragmented, more political, and more expensive. Tencent wants supply security. CXMT wants scale and validation. China wants semiconductor independence. Apple wants lower costs and another negotiating option. Washington wants to limit the growth of strategic Chinese technology. Those goals are now colliding inside one of the most basic components in modern computing. A small memory chip has become part of a much larger contest over AI, industrial power, and national security. The Tencent contract may prove that CXMT can serve China's largest technology companies. The Apple decision could determine whether it can cross into the supply chain of one of America's most influential corporations. So what do you think? Should Apple be allowed to buy memory from CXMT if the chips meet its technical standards? Or would that strengthen a Chinese semiconductor company at the expense of long-term American supply chain security? Let me know your view in the comments. And subscribe to Eastern Engine for more grounded coverage of the chips, factories, and engineering decisions reshaping the global economy. Because CXMT did not just win a $3 billion order. It may have won the credibility needed to compete for something even bigger. China's largest electric vehicle company has spent years proving that it can build batteries, motors, power electronics, and complete cars at enormous scale. Now BYD is moving deeper into the part of the vehicle that may matter most next decade, the computer that controls intelligent driving. The company has unveiled its Xuanji A3 processor. BYD describes it as China's first domestically designed 4nm chip built specifically for advanced driving systems. One chip delivers around 700 trillion operations per second. A 3-chip configuration exceeds 2,100 TOPS, and BYD says the processor has already entered chip-level mass production. A Chinese automaker is no longer satisfied with buying batteries, sensors, software, and processors from separate suppliers. BYD wants to control the complete stack. But the headline needs an important qualification. The Xuanji A3 has not yet been independently proven to beat NVIDIA's best automotive platform. Mass production of the chip does not mean millions of BYD vehicles are already using it. And a 4nm design does not prove that the processor is fabricated entirely with Chinese manufacturing equipment. Still, BYD is clearly trying to turn the vehicle into a vertically integrated platform, with the processor, software, sensors, battery, motors, and architecture developed around one system. The question is whether BYD can use its scale to make those chips an industry standard. Why BYD built its own car brain? Modern vehicles are becoming computers on wheels. Cameras, radar, LiDAR, ultrasonic sensors, navigation systems, battery controls, entertainment displays, and driver assistance software all generate enormous amounts of data. That information must be processed quickly enough for the vehicle to recognize lanes, detect pedestrians, predict nearby traffic, and decide when to brake or change direction. Traditional vehicles divided these tasks among many separate control units. Advanced driving requires tighter coordination, larger neural networks, millisecond decisions, and safe operation even when one component fails. This is why automotive computing is moving towards centralized platforms. Instead of dozens of isolated control units, more functions are combined inside a smaller number of powerful computers. The Xuanji A3 is designed for that transition. It is the centerpiece of a compact central computing platform, intended to connect intelligent driving, the digital cockpit, and core vehicle control functions. That gives BYD more control over how information moves through the car. It also allows the company to optimize the processor around its own vehicles, instead of adapting every design to a general-purpose chip from another supplier. What 700 TOPS really means. The number attached to the Xuanji A3 is 700 TOPS. TOPS means trillions of operations per second. It is commonly used to describe the peak performance of artificial intelligence accelerators. A higher number can support more camera feeds, larger neural networks, or several models at once. But TOPS should not be treated like horsepower. Two chips with the same advertised number may deliver very different real-world performance. The result depends on numerical precision, memory bandwidth, software efficiency, thermal limits, and how much of the processor can actually be used by the workload. BYD says the Xuanji A3 includes a 16-core CPU and around 273 gigabytes per second of memory bandwidth. One chip provides roughly 700 TOPS, while three working together exceed 2,100 TOPS. That is an enormous figure for a passenger vehicle. However, three chips do not automatically behave like one perfectly unified processor. The system must distribute work efficiently, move data between chips, avoid duplication, and manage power and heat. The important question is not only how much peak performance exists, it is how much useful performance the software can extract in real traffic. BYD says combining the chip with its own algorithms improves computing utilization. That is one reason vertical integration matters. The company can design models around the exact structure of the processor, then adjust the hardware around the software's needs. Why three chips? Most vehicles will not require 2,100 TOPS. A basic assisted driving system can operate with far less. Premium vehicles, however, may run cameras, LiDAR, radar, perception models, parking, driver monitoring, and cockpit intelligence simultaneously. Three chips give BYD room to divide workloads and create redundancy, with separate processors potentially handling perception, planning, cockpit functions, or backup capacity. Level 3 and Level 4 systems require more than speed. Level 3 automation can allow the vehicle to control itself under limited conditions, but the human driver may still need to take over. Level 4 systems are designed to operate without human control inside defined areas or situations. Supporting those levels requires fail operational design. If one component stops working, the system must remain safe. Extra processors, independent power paths, redundant sensors, and multiple communication networks can all contribute. BYD says the Xuanji A3 is designed to support future Level 3 and Level 4 systems. That does not mean every vehicle carrying the chip will immediately become autonomous. Regulation, software validation, sensors, mapping, and road conditions still determine what the car is legally and technically allowed to do. The NVIDIA comparison. NVIDIA has spent years building one of the strongest automotive computing ecosystems in the world. Its drive platform combines processors, networking, development tools, simulation software, and artificial intelligence models. Automakers do not simply purchase a chip. They purchase access to an established software platform with global engineering support. That is hard to replace. BYD's advantage is different. It does not need to sell the Xuanji A3 to every automaker in the world to make the project successful. BYD can deploy the chip across its own enormous vehicle portfolio. That creates a guaranteed internal customer. Each vehicle can generate data, receive software improvements, and reuse parts of the same architecture. NVIDIA must support many brands, while BYD can optimize around its own sensors, batteries, motors, networks, and factories. This does not prove BYD has beaten NVIDIA. NVIDIA still has deeper experience in AI software, simulation, developer tools, and advanced computing. But BYD may not need to win a direct benchmark battle. It may only need a processor that is powerful, efficient, reliable, and cheap enough for its own cars. The mass production claim. BYD says the Xuanji A3 has entered mass production. That claim must be interpreted carefully. Chip-level mass production means the processor has moved beyond a small laboratory sample. It suggests that the design has completed major validation steps and is being manufactured in meaningful quantities. But it does not necessarily mean the chip is already installed across BYD's current vehicle range. Automotive deployment moves slowly because chips must survive vibration, humidity, voltage changes, extreme temperatures, and long service periods. The full system also needs software validation, sensor integration, cybersecurity testing, and safety approval. Reports indicate that the first major vehicle deployments may arrive later, potentially beginning with premium BYD brands before spreading into higher volume models. So the breakthrough is real, but the rollout should not be exaggerated. The Xuanji A3 is entering the production phase. Its true impact will become visible when BYD reveals which vehicles use it, how many chips are installed, and what driving functions are activated. Who actually manufactures it? Another major question is fabrication. BYD designed the Xuanji A3, but designing a chip and manufacturing it are different businesses. A 4-nanometer processor requires advanced lithography, materials, process control, packaging, and testing. BYD has extensive semiconductor operations, especially in automotive power electronics and mature node components. But there is no clear evidence that BYD manufactures this particular processor entirely inside its own factories. Chinese automakers and chip designers still depend heavily on outside foundries for leading-edge production, including manufacturers in Taiwan and South Korea. That means the Xuanji A3 is a major step toward design independence, but not necessarily complete supply chain independence. A company can control the architecture, software, and roadmap while still relying on foreign fabrication. That is strategically valuable, but trade restrictions or supply disruptions could still affect production. BYD's long-term challenge is larger than designing one successful chip. It must secure fabrication capacity, advanced packaging, memory, and automotive-grade testing at the scale required for millions of vehicles. BYD's vertical integration advantage. BYD began as a battery company. It later expanded into vehicles, electric motors, power electronics, semiconductors, energy storage, and manufacturing equipment. This vertical integration has helped BYD lower costs and react when supply chains become unstable. The Xuanji A3 extends that strategy into advanced computing, connecting its batteries, electric drive systems, vehicle platforms, and assisted driving software. The driving system could share information more directly with braking, steering, suspension, battery management, navigation, and the cockpit. That could reduce latency and simplify software updates. It may also lower cost. A processor designed for BYD's exact requirements may avoid features the company does not need. Once production reaches sufficient scale, BYD can spread development costs across a very large number of vehicles. This is where BYD may have an advantage over smaller automakers. Designing an advanced chip costs an enormous amount of money. The investment only makes sense if the company can deploy enough units to recover the expense. BYD has the scale to use the same architecture across several brands, vehicle classes, and price categories. The Chinese chip race. BD is not alone. Chinese automakers are rapidly developing their own intelligent driving processors or working with domestic semiconductor companies. NIO has introduced its own driving chip. XPeng has developed the Turing processor. Li Auto is working on its Mach series hardware. Geely, Huawei, Horizon Robotics, and other companies are also building automotive computing platforms. This competition shows how important the car chip has become. Automakers once differentiated themselves through engines, transmissions, and chassis tuning. In the electric vehicle era, batteries and manufacturing became central. The next competitive layer may be computing. A company that controls the processor can decide how quickly features are added, how data is handled, and how dependent the vehicle remains on suppliers. But fragmentation creates risk. Separate tools and operating systems increase costs and make every platform harder to support. Some automakers may eventually discover that designing chips is too expensive. BYD is better positioned than most because of its scale and its ability to connect the chip directly to its own vehicles. The real economic impact. The biggest opportunity may not be the most expensive autonomous vehicle. It may be bringing advanced computing into affordable cars. BYD has already pushed driver assistance features deeper into mass market segments. If the company controls the processor, it can reduce the amount paid to foreign suppliers and decide how aggressively to spread intelligent driving hardware across its lineup. That could pressure competitors. A feature that begins in a premium vehicle can move into mid-range models once production scales, just as Chinese automakers did with batteries, fast charging, displays, and electric drivetrains. If BYD installs its own chip across hundreds of thousands of vehicles, it gains an enormous data and software advantage. More vehicles create more data, better models, more useful hardware, and a stronger platform. That feedback loop matters far beyond the TOPS number. What remains unproven? Several important questions remain unanswered. We do not yet have independent benchmarks showing how the Xuanji A3 performs against NVIDIA Drive Thor, Huawei's automotive platforms, or rival Chinese chips under identical conditions. We do not know the final production cost, real-world power use, manufacturing yield, or volume of secure foundry capacity available to BYD. And we do not know how quickly the chip will move from premium vehicles into mass-market models. The real test will happen on the road. Can the system recognize unusual objects? Can it handle rain, glare, construction zones, and unpredictable drivers? Can it fail safely? Can BYD maintain the software for years? A large TOPS number cannot answer those questions. My take is that the Xuanji A3 is not important because BYD has already defeated NVIDIA. It is important because BYD is removing another external dependency from the vehicle. The company already controls batteries, motors, power electronics, and much of its manufacturing. Now it is attempting to control the computing architecture that will define intelligent cars. A single chip delivering around 700 TOPS is significant. A 3-chip system exceeding 2,100 TOPS is visually impressive, but the real advantage is integration. BYD can design the processor, algorithms, sensors, vehicle controls, and production process as one system. That is difficult for a traditional automaker coordinating outside suppliers. Limits remain. The chip may rely on foreign fabrication. Mass production does not equal mass deployment. Level 3 and Level 4 support does not mean fully autonomous. BYD cars are already operating everywhere, and NVIDIA remains a much stronger global computing platform. But BYD does not need to replace NVIDIA worldwide. It needs to make outside processors less necessary inside its own vehicles. If it succeeds, the company will not simply be an electric car manufacturer. It will become a large-scale automotive computing company with millions of vehicles serving as the deployment platform. That could reshape global competition. So what do you think? Can BYD turn the Xuanji A3 into a genuine alternative to NVIDIA's automotive processors? Or will manufacturing limits and software complexity prevent the chip from reaching its full potential? Let me know your view in the comments. And subscribe to Eastern Engine for more grounded coverage of the chips, factories, and engineering decisions reshaping the global economy. Because BYD built its rise on batteries, but its next advantage may come from the computer controlling the car.
Chinese electric vehicles like BYD are flooding the globe, offering sci-fi technology at half the price of Western brands. But everyone is focusing on the wrong thing. The multi-trillion-dollar question is, why did the EV revolution happen in China and not the West? Today, I'm going to break down the greatest industrial master plan of the 21st century. For 100 years, the global automotive hierarchy was built on one thing, the internal combustion engine. China spent decades trying to catch up.
There is a number that automotive engineers have been chasing for over 100 years. Not a speed record, not a horsepower figure, a percentage. A simple, brutal measure of how much energy your engine actually uses versus how much it wastes. For most of automotive history, that number sat stubbornly around 30% for the average production car, meaning 70% of every drop of fuel you ever paid for simply vanished, absorbed into hot metal, pushed out the exhaust pipe, lost to friction before a single wheel ever turned. The industry accepted this. Engineers called it the nature of combustion. Textbooks framed it as a fundamental constraint of physics. Then on April 13, 2026, a company called Geely stood in front of the world, put a single number on a screen, and quietly ended that conversation. 48.41%. Certified. Officially measured. Recognized by Guinness as a world record for a production vehicle engine. That number is not just impressive. It is the kind of number that makes engineers at Toyota, BMW, and Volkswagen go very quiet in meetings. To understand why, you need to understand what it actually took to get there, and why everyone else said it was impossible. Let's go back to basics for a moment, because the context here matters enormously. When a combustion engine burns fuel, it is essentially harnessing a controlled explosion and converting that energy into rotation. Simple in concept, brutally inefficient in practice. The explosion generates enormous heat, and heat is stubborn. It does not wait patiently to be converted into useful work. It spreads immediately into every surface it touches: the cylinder walls, the piston tops, the exhaust valves, the surrounding metal structure of the engine itself.
But they couldn't beat the Western patents, so they redefined what a car is. Traditional auto giants failed to dominate EVs because they tried to build an electric version of a car. China succeeded because they built a smartphone on wheels. Reason number 1, overtaking on a curve. China realized an EV is a giant battery driven by software. By abandoning the gas engine entirely, China shifted the battlefield to electrochemistry.
Physics has a name for the theoretical ceiling on how efficient any heat-based engine can ever be: the Carnot limit. Without getting lost in the math, what it essentially says is this: the larger the temperature gap between your combustion event and your exhaust output, the more work you can theoretically extract. But that gap has real-world boundaries on both ends. Push combustion temperatures too high and your engine destroys itself. Keep exhaust temperatures too low and your emission systems stop functioning. Every production engine ever built has been threading that needle. For decades, the practical ceiling for a mass-produced car engine sat at roughly 38 to 40%. Getting past 40 required extraordinary engineering effort. Toyota, one of the most respected powertrain engineering organizations on the planet, spent years and billions of dollars developing their 2.5-liter dynamic force engine. They used a technique called the Atkinson cycle, which slightly extends the intake valve timing to reduce pumping losses and recover a bit more energy from each combustion event. Their result was 41% thermal efficiency. The industry applauded. Engineers wrote papers. The consensus formed that this was, for all practical purposes, the ceiling for production engines at any reasonable cost. The reasoning made sense on paper. The laws of thermodynamics are not negotiable. The materials available for engine construction have hard temperature limits. The fuel being burned has fixed energy content. 41% was framed not as a plateau but as a finish line. What happened next is one of the more interesting stories in modern industrial history. Before Geely's record, another Chinese company had already shaken the assumptions loose. BYD, Build Your Dreams, looked at the hybrid vehicle architecture that the rest of the world had settled on and concluded that the fundamental design was the problem. In a conventional hybrid, the combustion engine drives the wheels directly, with an electric motor assisting during acceleration and recovering energy during braking. It sounds efficient in theory. In practice, it means the engine is constantly changing speeds, revving hard uphill, idling at traffic lights, spinning at a dozen different RPM points throughout a journey. And here is the critical issue. Every combustion engine has one narrow band of RPM where it operates most efficiently. Force it to operate anywhere else and efficiency drops. A conventional hybrid engine spends the majority of its life operating outside that sweet spot. BYD's solution was radical in its simplicity. Remove the engine from the drivetrain entirely for most driving conditions. Let electric motors handle the wheels full-time. Assign the combustion engine exactly one job. Run at its optimal RPM and generate electricity. Nothing more. No gear changes, no speed variations, no compromises. Just one engine, one speed, one purpose. Because the engine was no longer chasing the road, BYD's engineers could tune it obsessively around that single operating point. The result was their fifth-generation DMI platform, delivering 46.06% thermal efficiency, a number that genuinely stunned the global automotive press. To appreciate how significant that jump was, Toyota's journey from roughly 36% to 41% took the better part of 2 decades and required sustained investment most automakers could not match. BYD moved the needle by 5 percentage points in a fraction of that time by simply rethinking the architecture from scratch. Western automakers had a difficult internal conversation. Most of them concluded it was a regional story, a niche, something that mattered in China but would not translate to global markets. They underestimated what was already being built in the background. While the industry was processing BYD's achievement, Geely's engineers had already been working for 2 years on a completely different approach. They were not iterating on existing engine designs. They were not refining valve timing or adjusting compression ratios by small increments. They were asking a more fundamental question: what actually limits combustion efficiency at the most basic physical level, and what would it take to attack those limits directly? The answers they came up with touched every stage of the combustion process, from the moment air enters the engine to the moment power reaches the wheels. Each solution was unconventional. Several of them contradicted standard engineering assumptions. Together, they produced something that sits well outside what anyone projected was achievable. The first major breakthrough addresses something so fundamental it is easy to overlook: what actually happens inside the cylinder when fuel burns. In a standard engine, air and fuel enter the cylinder and mix as best they can in the brief window available before the spark plug fires. The mixing is never perfect. Some areas of the cylinder are fuel-rich. Others are fuel-lean. When ignition happens, the flame front does not detonate simultaneously across the whole chamber. It propagates outward from the spark plug like a slow ripple, combustion spreading unevenly through a non-uniform mixture. That uneven burn has consequences. The first regions to ignite release heat immediately, and that heat starts bleeding into the cylinder walls before the rest of the mixture has even caught. By the time combustion is complete, a meaningful portion of the energy has already transferred into the engine structure, rather than pushing the piston down. It is one of the primary mechanisms driving inefficiency in traditional combustion engines. Geely's engineering team redesigned the intake port geometry and valve angles from the ground up. The result is what they call the Yufeng tornado combustion system. When the intake valve opens, incoming air is not simply drawn into the cylinder passively. The port shape forces it into a high-velocity rotating vortex, a controlled, sustained spin that continues to accelerate as the cylinder fills. By the time the intake valve closes, the air-fuel mixture is spinning rapidly and blending continuously throughout the chamber. When ignition occurs into that spinning mixture, the flame front does not creep, It propagates outward simultaneously in all directions because the fuel is uniformly distributed throughout. The entire charge burns in a fraction of the time a conventional cylinder requires. Less time burning means less time for heat to conduct into the surrounding walls. More energy stays with the expanding gases and pushes down on the piston where it belongs. The efficiency gain from this single change is substantial, but it introduced a new problem. More complete, faster combustion raises cylinder pressure rapidly. Exactly the conditions that cause engine knock, where fuel ignites prematurely before the spark plug fires, causing destructive, uncontrolled detonation. Knock is one of the main reasons engineers have historically been cautious about pushing compression ratios higher. Solving knock without sacrificing the benefits of the tornado combustion system required a second breakthrough, one that looks impossible until you understand how it actually works. Every engineering student learns early that you cannot run a combustion engine extremely hot and extremely cool at the same time. Hot combustion means better efficiency. Cool metal means less knock risk. These goals directly oppose each other, and the standard solution has always been to find a compromise temperature that accepts some loss on both ends. Geely rejected the compromise. Their thermal management system splits the engine into two completely independent cooling zones with separate coolant circuits, each managed independently by an electronically controlled pump that reads operating conditions many times per second. The cylinder head, the upper section of the engine where combustion actually occurs, is kept aggressively cold. Coolant flows through this zone rapidly, pulling heat away almost as fast as it is generated. Keeping the combustion chamber walls cold means the incoming air charge stays dense right up to the moment of ignition, which dramatically reduces the risk of premature detonation. This allows the engine to operate at a significantly higher compression ratio than would be safe in a conventionally cooled engine. Higher compression extracts more energy from each combustion event. The lower engine block, where the pistons travel up and down in their bores, is kept deliberately warm. Warmer oil is thinner oil. Thinner oil means the pistons experience dramatically less friction as they move. Friction is simply wasted energy converted to heat, so every reduction in friction is efficiency directly recovered. Cold at the top for maximum safe compression. Warm at the bottom for minimum friction losses. Two objectives that traditional design treated as mutually exclusive, running simultaneously in different zones of the same engine. The electronic management system continuously adjusts coolant flow rates based on load, speed, and temperature readings to maintain both conditions simultaneously. The conventional wisdom said this was pointless complexity. The dyno results said otherwise. Even a record-breaking engine is only useful if you can get its output to the wheels without bleeding the gains away in a heavy mechanical transmission. Traditional automatic gearboxes are engineering achievements in their own right, but they are also heavy, complex, and consume a percentage of the power they transmit simply through the friction of their own operation. Geely's solution is their 11-in-1 EHT intelligent drive system. The name refers to how many separate components have been integrated into a single compact housing. The engine, the generator, two electric drive motors, the high-voltage inverters, and the thermal management hardware, all packaged together. Total powertrain weight dropped 13.5% compared to conventional hybrid setups, and the mechanical complexity of a multi-speed gearbox is eliminated entirely. For around 90% of typical driving, the combustion engine has no physical connection to the wheels. It runs at its efficiency sweet spot, drives a generator, and that electricity either charges the battery or powers the motor spinning the wheels directly. From the driver's perspective, the car behaves like a pure electric vehicle, smooth, silent, and immediate in response. Only at sustained highway speeds does the system engage a direct mechanical connection between engine and wheels, because at that specific condition, routing power electrically actually loses more than the direct path gains. An AI power management system oversees all of this, recalculating the optimal energy routing 50 times every second. It reads the navigation map ahead, anticipates gradients and speed changes, and pre-positions the battery's state of charge to be exactly where it needs to be at each stage of your journey. It is not reacting to the road, it is planning ahead of it. The combined result of all four innovations, tornado combustion, split thermal zones, the 11-in-1 integration, and AI routing, is a certified fuel consumption figure of 2.22 liters per 100 kilometers, with a total range exceeding 2,000 kilometers on a full tank. There's an honest conversation worth having about what this technology means beyond the record itself. Pure electric vehicles have real strengths: zero tailpipe emissions, low running costs, exceptional driving refinement. But they also carry genuine practical limitations that hundreds of millions of potential buyers are not yet ready to work around. Battery weight. charging infrastructure gaps, and long refueling times are not hypothetical concerns. They are daily realities in enormous portions of the world. What Geely's iHEV system offers is something different. The driving character of an electric vehicle for everyday use, combined with the refueling simplicity of a conventional car and a range figure that makes long-distance travel completely straightforward. No charging network dependency, no range calculation anxiety. Fill up anywhere on the planet. The vehicle delivering these numbers is not a lightweight city car optimized for fuel economy testing. It is a full-size SUV operating in real-world conditions. For the established automotive industry, this is a genuinely difficult moment. Combustion engine technology, invented in Europe, refined to apparent perfection in Japan, has now reached its highest ever efficiency milestone under a Chinese company that barely existed on the global automotive stage 15 years ago. That kind of lead is not closed quickly. It requires years of engineering work, institutional rethinking, and a willingness to abandon assumptions that have guided the industry for decades. For consumers, the competition this creates is straightforwardly good news. Engineering ambition at this level historically drives prices down and capability up across the entire market. Honestly, what strikes me most about this story is not the 48% figure itself, it is what it represents about where innovation is actually happening right now. The assumption in Western automotive culture has been that the future of the car is fully electric, full stop, and that combustion technology was essentially done evolving. Geely just demonstrated that assumption was wrong in a very public way. I think the most interesting question for the next 5 years is not whether legacy automakers can match this efficiency number. It is whether they can match the pace of development behind it. Geely and BYD are not slowing down. They are not iterating on old platforms. They are building new ones from blank sheets of paper, faster than the traditional industry timeline allows for. What do you think? Does a 2,000-kilometer range hybrid with this kind of efficiency change your mind about electric vehicles? Or are you still holding out for full electric? Drop your answer in the comments below. I read every single one. If you found this breakdown useful, consider subscribing to Eastern Engine. We cover exactly these kinds of engineering stories the moment they break, with the depth they actually deserve. Hit the subscribe button and turn on notifications so you never miss what comes next. The industry is moving fast right now, and the next story is already in the works. China has demonstrated a new way to turn seawater into drinking water using sunlight instead of electricity from the grid. Researchers built an outdoor system covering less than 1 square meter. Under natural sunlight, the prototype reportedly produced just over 20 liters of fresh water per day. That is enough to cover the basic daily drinking water needs of roughly 10 people. The collected water met international drinking water standards, and the researchers even used it to irrigate a small test field through complete crop growing cycles. But the most important part is not simply that sunlight can evaporate seawater. Humans have known that for thousands of years. The breakthrough is the material inside the device. Chinese researchers created a three-dimensional photothermal structure designed to absorb sunlight, concentrate heat at the water's surface, accelerate evaporation, and operate without being connected to the electrical grid. In laboratory testing, the material reached an evaporation rate of 38.14 kilograms of water per square meter every hour. That was more than 8 times the performance of the researchers' earlier flat design. The system also absorbed more than 90% of incoming sunlight and reportedly reduced the energy needed for evaporation by nearly 46%. If the technology can be scaled reliably, it could provide drinking water to islands, coastal villages, farms, and disaster zones where large desalination plants are too expensive or where electricity is unreliable. But can a small solar prototype really compete with industrial desalination? Or is this another impressive laboratory result that becomes far more difficult once engineers try to build it at useful scale? To answer that, we need to understand why turning seawater into drinking water remains so expensive. Why desalination needs so much energy. The ocean contains an almost unlimited supply of water. But seawater also contains salt, minerals, microorganisms, and other contaminants that humans cannot safely drink in large quantities. Removing those substances takes energy. The most common modern method is reverse osmosis. A desalination plant uses powerful pumps to force seawater through membranes containing extremely small pores. Water molecules pass through, while most dissolved salts are blocked. The process works well and is used in large facilities around the world, but it requires high pressure. Creating that pressure consumes electricity, and the plant also needs pre-treatment equipment, filters, pumps, membranes, monitoring systems, and maintenance. Another approach uses heat. Seawater is evaporated, leaving salt behind. and the water vapor is then condensed into clean liquid. This resembles the natural water cycle. The sun evaporates ocean water, clouds form, and fresh water returns as rain. Industrial thermal desalination can produce large amounts of water, but heating that much seawater consumes enormous quantities of energy. That is why researchers are interested in solar evaporation. Instead of heating an entire tank of water, a photothermal material absorbs sunlight and concentrates the heat only where evaporation happens. The goal is to generate water vapor while wasting as little energy as possible. How the Chinese material works. The new system uses a three-dimensional photothermal structure. Photothermal simply means that the material converts light into heat. A flat, dark surface can already do this. Leave a black object in direct sunlight and it becomes hot because it absorbs more light than a reflective surface. But a high-performance solar evaporator needs to do much more. It must absorb a wide range of sunlight. It must transfer heat into a thin layer of water instead of heating the entire reservoir. It must continuously pull fresh seawater toward the evaporation surface. It must allow water vapor to escape. And it must prevent salt from blocking the structure. The Chinese team developed a three-dimensional design with a much larger active surface than a conventional flat absorber. That extra surface area allows more water to interact with the heated material at the same time. The structure also helps confine heat near the evaporation zone. Instead of allowing thermal energy to spread into the bulk seawater, more of the captured sunlight is used directly to change liquid water into vapor. The researchers reported solar absorption of up to 90.2%. They also said the design reduced the effective energy required for evaporation by 45.7%. That does not violate physics or create energy from nothing. Water molecules still need energy to escape the liquid. The material changes how efficiently heat is delivered and may also alter the local interaction between water and the internal surfaces. The result is faster evaporation from the same amount of sunlight. The 38.14 kilogram result. The headline laboratory number was 38.14 kilograms per square meter per hour. Because 1 kilogram of water is approximately 1 liter, that sounds like the device could produce more than 38 liters of drinking water every hour from 1 square meter. But that interpretation would be misleading. The figure describes the measured evaporation rate under controlled test conditions. Evaporated water is not automatically collected drinking water. A complete system must capture the vapor, move it toward a cooler surface, condense it into liquid, and store it without contamination. Every step introduces losses. Laboratory illumination may also differ from changing outdoor sunlight. Clouds, wind, temperature, humidity, and the angle of the sun all affect real-world output. That is why the outdoor prototype is more important than the laboratory record. The real outdoor prototype. The researchers constructed a system with an active area of approximately 0.75 square meters. It was tested outside using natural sunlight rather than a controlled indoor lamp. The complete device produced 20.16 liters of fresh water in 1 day. That is far lower than multiplying the peak laboratory evaporation rate across 24 hours. But it is a much more meaningful figure because it represents water actually collected by a working outdoor system. 20 liters is not enough for the complete daily water use of 10 people. Cooking, washing, sanitation, and agriculture require far more, but it may cover basic drinking needs. That could matter in remote places where fresh water must currently be transported by truck or boat. A small village could use several modules. A disaster relief team could deploy portable systems where the power grid has failed. Coastal farms might use larger arrays to supplement irrigation water. The system would still depend on weather and sunlight, but it could operate without the continuous electricity demand of a conventional reverse osmosis plant. What no grid power really means. The device is sometimes described as electricity-free. That wording needs context. The system does not operate without energy. Its energy comes from sunlight. The photothermal material absorbs solar radiation and converts it into heat. The correct claim is that the prototype can produce water without being connected to an external electrical grid. That is an important difference. A reverse osmosis plant may require continuous electricity for pumps. A solar evaporator can operate passively during daylight. However, a larger commercial system might still use small pumps, sensors, fans, or automated controls. Electricity could also be useful for moving seawater, collecting water, cleaning equipment, or operating at night. The central advantage is not that electricity becomes forbidden. It is that the main energy-intensive step, evaporation, is driven directly by the sun. The salt problem. Salt is one of the biggest obstacles facing solar desalination. When water evaporates, dissolved salt remains behind. As evaporation continues, the water near the surface becomes increasingly concentrated. Eventually, salt crystals can form on the photothermal material. Those crystals block sunlight, restrict water movement, and damage performance. A laboratory device may work well for several hours and then become far less effective after days of salt accumulation. Any practical solar evaporator needs a way to manage concentrated brine. Some designs allow salt to diffuse back into the larger seawater reservoir. Others use channels that continuously circulate water through the structure. Some devices are periodically flushed, while others are designed so that salt crystallizes in a separate location where it can be removed. Long-term durability will be one of the most important tests for the Chinese system. The prototype must prove that it can operate through repeated wetting, drying, heating, and salt exposure without losing performance. Coastal seawater also contains biological material and minerals that may clog surfaces over time. Producing water for one successful demonstration is different from operating every day for several years. The farming test. The researchers did not stop after measuring the water in a container. They used the fresh water to irrigate a test field covering approximately 5 square meters. The system reportedly supported complete crop growing cycles. That experiment matters because agriculture is the world's largest user of fresh water. Many water-stressed regions are located near oceans, but seawater cannot be applied directly to most crops. Salt builds up in soil, damages roots, and eventually makes farmland unproductive. A modular solar desalination system could provide small quantities of fresh water for greenhouses, seedlings, or high-value crops. It would not immediately replace the enormous irrigation networks used for rice, wheat, or corn. Those systems move thousands or millions of liters. But it could be valuable for remote islands, desert communities, or small coastal farms where every liter of clean water is expensive. The cost claim. The researchers estimate that after roughly 2 years of operation, the cost of the produced water could fall below the price of commercial bottled water. That is a projection, not a confirmed market price. Bottled water is also an easier benchmark to beat than municipal tap water. Bottled water includes packaging, transport, storage, and retail profit. A large reverse osmosis plant may produce water at a much lower cost per liter than bottled water, especially when operated at enormous scale. The true economics will depend on the cost of the photothermal material, the condenser, supporting structure, maintenance, cleaning, lifetime, and installation. If the device needs frequent replacement, the water will be expensive. If it survives for years with little maintenance, the economics become much stronger. Local conditions will also matter. In a city with an established water network, the system may not compete with tap water. On an isolated island where bottled water arrives by boat, it could be far more attractive. Can it scale? Scaling is the central question. A 0.75 square meter prototype can be carefully assembled and monitored by researchers. A commercial system may need hundreds or thousands of square meters. Every module must distribute seawater evenly. Vapor must be collected efficiently. Condensation surfaces must remain cool enough to turn vapor back into liquid. Strong winds, storms, dust, salt spray, and biological growth must not destroy the equipment. The system must also dispose of concentrated brine responsibly. Large desalination plants return salty waste to the ocean, where it can damage local ecosystems if it is not properly diluted. A solar system produces less water per unit, but a large field of modules could still create a significant waste stream. Manufacturing is another challenge. The photothermal structure must be cheap enough to produce in large quantities. A material with excellent laboratory performance may rely on complicated fabrication steps that make commercial production too expensive. Engineers will need to simplify the design without losing the properties that created the high evaporation rate. Where it could be used first. The technology is most likely to succeed first in places where water is valuable and electricity is limited. Small islands are one obvious market. Many islands have abundant sunlight and seawater, but depend on imported fuel or bottled water. Remote coastal villages could use modular units for drinking and cooking. Disaster zones are another possibility. Earthquakes, floods, and storms can damage power lines and contaminate freshwater supplies. Portable solar desalination equipment could begin producing water without waiting for the electrical grid to be restored. Military bases, research stations, ships, and offshore facilities may also value systems that reduce dependence on transported water. Agriculture could become another market if the device is combined with water storage and efficient drip irrigation. But the technology is unlikely to replace giant municipal desalination plants immediately. Cities need reliable water every hour of the day, regardless of weather. Large reverse osmosis facilities already produce hundreds of millions of liters daily. Solar evaporation will probably begin as a supplement rather than a complete replacement. My take. My take is that this is a promising water technology, but the 20-liter outdoor result matters more than the spectacular laboratory number. The researchers have shown that the material can move beyond a small indoor sample and produce usable fresh water under natural sunlight. That is an important step. The system could be especially valuable where transporting water is expensive and grid electricity is unavailable. But it is not yet proof that China has solved global water scarcity. The prototype is small. Long-term salt resistance still needs to be demonstrated. The manufacturing cost must fall, and larger systems must show that they can collect and condense vapor efficiently in real weather. Still, the concept attacks one of desalination's biggest problems directly. Instead of spending large amounts of electricity pushing seawater through membranes or heating enormous tanks, the system uses a carefully designed material to place solar heat exactly where evaporation occurs. The ocean provides the water. The sun provides the energy. The material connects the two. If China can turn that laboratory efficiency into durable mass-produced equipment, the technology could give remote communities a new source of drinking water without waiting for a power plant or a massive pipeline. So what do you think? Could sunlight-powered desalination become a practical solution for water-stressed coastal regions? Or will scaling, salt, and maintenance keep it limited to small installations? Let me know your view in the comments. And subscribe to Eastern Engine for more grounded coverage of the technologies, factories, and engineering decisions reshaping the global economy. Because China has not eliminated the cost of desalination, but it may have found a way to replace part of that cost with sunlight.
Okay, so let me ask you, you said something recently that was quite provocative. You said that China was winning the AI race, the AI competition. I know that you've got a powerful, competitor in Huawei, and Huawei has a lot of advantages you don't have. Why don't you describe this?
In March 2026, an engineer walked onto a stage in Shenzhen and held up a single card, small enough to fit in one hand. Then he said the number out loud, 1.56 petaflops. If that means nothing to you, here's the translation. That is roughly 1.5 quadrillion AI calculations every second, about the muscle of 150 high-end laptops, compressed into a slab of hardware the size of a paperback book. And according to Huawei, that single card is close to 3 times more powerful than the best AI chip the company was previously able to get its hands on for the Chinese market. But the performance number, as wild as it sounds, is not actually the story.
Competition. Are we really losing?
It was a very good headline.
It was a great headline, yeah.
And it apparently caught a lot of attention. As you know, with headlines, the disclaimer part, the foundation part, was left out of the headline.
The story is what's hiding underneath that chip, and why it just exposed a weakness in the most dominant company in artificial intelligence that almost nobody was talking about out loud. Because for years, one company has effectively owned AI. Not most of it, almost all of it. And the assumption everyone made was that its position was untouchable, that there was simply no way around it. This chip is the first real crack in that assumption. By the end of this video, you'll understand exactly what it does, how it was built when every rule said it couldn't be, and why the part that should make NVIDIA nervous isn't the speed at all. Let's get into it. To understand why this matters, you first have to understand the chip this thing was designed to kill. When export restrictions tightened on advanced semiconductors heading into China, NVIDIA, the company that supplies the overwhelming majority of the world's AI chips, was put in an awkward position. It couldn't sell its best hardware into one of its biggest markets, so it built a special, deliberately weakened version specifically for China, a chip known as the H20. The whole point of the H20 was to be a ceiling, powerful enough for everyday tasks, but intentionally held back so it couldn't be used to train the largest, most ambitious AI models. It was a compromise, enough to keep selling into China, but not enough to let Chinese companies reach the frontier. And the expectation was that this ceiling would hold for years. Huawei's new chip didn't just bump against that ceiling. According to the specs Huawei presented, it blew straight through it. The company claims its single card delivers nearly 3 times the throughput of that limited H20, carries a massive pool of high-speed memory, and, here's the part that made executives sit up, sits at roughly the same price point Chinese companies were already budgeting for the American chip it's now meant to replace. Same price, far more power, no restrictions. You can already guess what happened next. Within weeks, China's biggest technology companies, the Alibabas, Tencents, and ByteDances of the world, reportedly started placing bulk orders. Huawei's AI chip business, which was already growing fast, is now projected to balloon further in 2026. That alone would be a big story, a new challenger, undercutting the dominant player in its own backyard. But it's not the story, because the truly remarkable thing isn't how fast this chip is. It's that by every conventional rule of how advanced chips get made, it should not exist at all. Here's something most people never think about when they hear the word chip. A modern AI accelerator isn't made by one company in one place. It's the end product of a global supply chain so specialized that only a tiny handful of companies on Earth can even participate in it. Picture an assembly line that stretches across multiple continents. The most advanced processors are manufactured in Taiwan, using almost unimaginably complex machines built by a single company in the Netherlands. Machines that cost hundreds of millions of dollars each and that nobody else on the planet knows how to build. The ultra-fast memory that feeds those chips comes from two companies in South Korea. Pull out any single link in that chain, and the conventional wisdom has always been simple. You cannot build a competitive AI chip without it. China was cut off from essentially all of those links at once. No access to the most advanced manufacturing machines. So Huawei's manufacturing partner had to use older equipment, a generation behind, with lower yields and bigger chips for the same performance. By every spreadsheet in every Western tech company, the conclusion was identical and confident. You cannot get there from here. And then Huawei did something that genuinely wasn't supposed to be on the table. They didn't just work around the manufacturing problem, they tackled the memory problem too, by building their own from scratch. This is the detail that deserves a second of your attention. That fast memory I mentioned, the kind that comes from those two South Korean companies, Huawei says it developed its own version, in-house from the ground up. Not licensed, not borrowed, not a copy of someone else's design. A proprietary memory standard, engineered inside China, tuned specifically for the messy, irregular data patterns that large AI models throw at hardware. Think about what that means. Practically every AI chip, in practically every data center, in practically every country, relies on memory from those same two suppliers. According to Huawei, this one doesn't. The processor, the memory, the connective fabric that ties it all together. For the first time, the whole thing is sourced domestically. The closest comparison I can think of is this. Imagine someone confiscates every machine shop, every specialized supplier, and every blueprint you'd need to build a jet engine. And then you build the jet engine anyway, out of parts you had to invent yourself, and it actually flies. That's roughly the scale of what's being claimed here. But even the hardware isn't the most important part of this story. The thing that should genuinely worry NVIDIA is something you can't hold in your hand at all. Here's what most people get completely wrong about NVIDIA's dominance. They think it's about the chips. It isn't, or at least not only. NVIDIA's deepest, strongest, most defensible advantage is something called CUDA. Let me explain why that's the real story. Because this is the actual weakness in the title, and it cuts both ways. CUDA is NVIDIA's software layer. It's the bridge that sits between the physical chip and the AI models that run on top of it. And over more than a decade, virtually every major AI model in existence, the famous chatbots and assistants you've heard of, was written to run on CUDA. The entire ecosystem of AI development grew up speaking CUDA's language. That's NVIDIA's true moat. It was never just that the chips were fast. It was that switching away from them was almost unthinkable. Moving your AI work off CUDA isn't like swapping out a part. It's like deciding to rewire an entire building while people are still working inside it. The cost, the risk, the time. For years, that was enough to keep everyone locked in. Most analysts assumed that lock would hold China back on the software side for years, even if the hardware caught up. This is the weakness the title is talking about. NVIDIA's greatest strength, that everything depends on its software, is also its single biggest vulnerability. Because a dependency that's strong is exactly the kind of thing a determined competitor will spend everything to break. And in 2026, someone tried. A Chinese AI company released a new frontier-class model and made a striking claim about it, that it was built with no NVIDIA dependency anywhere in its stack, not trained on NVIDIA chips, not optimized for CUDA. Instead, its engineers reportedly spent months rewriting the deepest, most technical layers of their software to run natively on Huawei's hardware, using Huawei's own alternative to CUDA. If that holds up the way it's described, it's genuinely significant, because it means the unthinkable rewiring job, the one everyone assumed was too painful to ever attempt, somebody just attempted it. And the building still had the lights on at the end. Now step back and look at the whole picture, because this is where it stops being about a single product. Stack it up. The chip is domestically made. The memory is domestically developed. The software framework that runs it is domestically built. And now a frontier AI model has reportedly been trained and deployed on top of all of it. For the first time, you have a complete AI system, from the raw silicon all the way up to the finished model, built without relying on the usual handful of irreplaceable suppliers. That's the thing that's actually new here. Not a chip, a whole parallel ecosystem. And the numbers around NVIDIA's position in China tell the other half of the story. The company's chief executive himself has acknowledged that its sales into China effectively collapsed, going from dominating the market to almost nothing in a remarkably short window. That's not a rumor or a projection. That's the company's own leadership, describing a market worth tens of billions of dollars largely slipping away, and being candid that it may not come back. Here's the irony at the center of all this, and it's worth sitting with. The restrictions were designed to do one specific thing: slow China's AI progress by cutting off the tools, the memory, and the chips. The logic seemed airtight: no advanced hardware, no advanced AI. What appears to have happened is closer to the opposite. In a span of roughly 18 months, the world's largest AI chip market went from near total reliance on NVIDIA to building a homegrown alternative across the entire stack. Not because any restriction was lifted, but precisely because it wasn't. Every barrier that was meant to be a wall ended up functioning more like a blueprint. It told Chinese companies exactly which capabilities they had to develop themselves, and gave them an enormous guaranteed domestic market to sell into once they did. That's a pattern worth recognizing, because it shows up again and again in the history of technology. When you cut a determined, well-funded player off from something, you don't always stop them. Sometimes you just force them to build their own version, and once they do, they never need yours again. Now, I want to be straight with you here, because I'd rather give you the real picture than pure hype. And there's a temptation with a story like this to overstate it. This does not mean NVIDIA has been beaten. It hasn't. Globally, NVIDIA is still the dominant force in AI by an enormous margin, and its newest chips are still, by most measures, ahead of what Huawei can currently produce. Huawei's approach involves real trade-offs. Older manufacturing means bigger, hotter, less efficient chips and lower production yields, which makes scaling up genuinely hard. Many of the most eye-popping specifications here come from Huawei's own announcements, not from independent testing. So a healthy amount of "let's see it proven at scale" is warranted. So the accurate framing isn't "China crushed NVIDIA." It's something more interesting and, honestly, more important. China demonstrated that NVIDIA's position is not unbreakable. The moat everyone assumed was permanent turned out to have a crossing point. That's the weakness that got exposed. Not that NVIDIA is weak today, but that its single greatest advantage, total dependency, can be escaped if someone wants it badly enough and is willing to spend years and billions to do it. And that's a different world than the one we were in 2 years ago. 2 years ago, there was one AI hardware ecosystem, and everyone lived in it. Now there appear to be two, one centered on NVIDIA, one centered on Huawei, developing in parallel on opposite sides of the Pacific. And the gap between them, which was supposed to be widening, looks like it might actually be narrowing. Zoom all the way out, and here's why this matters beyond the corporate scoreboard. AI is rapidly becoming the foundation that everything else runs on. The models behind search, software, medicine, science, defense, and the tools millions of people now use every day. And the hardware those models run on is the foundation beneath that foundation. Whoever controls the chips and the software ecosystem effectively sets the terms for the entire industry built on top. For the last decade, that control was concentrated in one place, with one company. A single ecosystem, a single set of rules, a single point of dependency for the whole world. What this chip represents, whatever you think of the politics around it, is the emergence of a genuine second option. And in technology, a second option changes everything. It drives competition. It pushes prices down. It forces the incumbent to move faster. And it means no single company gets to dictate the future entirely on its own terms. That's the real headline. Not that one chip is fast, but that the most locked-in, most dependent corner of the entire tech world just proved it has an exit, and somebody walked through it. Here's my honest opinion, for what it's worth. What I find most fascinating about this isn't the hardware specs, which we'll all be debating for months as real-world tests roll in. It's the strategic lesson buried inside it. The whole effort to contain China's AI ambitions rested on one assumption: that certain pieces of technology were simply too hard to replicate, that the supply chain was too specialized to ever be rebuilt from scratch. This chip is a direct challenge to that assumption, and whether or not every claim about it holds up perfectly, the bigger trend is undeniable. A second, fully independent AI ecosystem is taking shape. and that genuinely reshapes the next decade of computing. I think the people who dismiss this as just propaganda and the people who treat it as NVIDIA is finished are both wrong. The truth is in the uncomfortable middle. NVIDIA is still ahead, but its position is no longer guaranteed, and that single fact changes the entire game. Here's the question I genuinely want your take on, and be honest, because people get heated about this one. Is it a good thing that the AI world is splitting into two competing ecosystems, because competition makes everyone build better and cheaper? Or is it dangerous to have the most powerful technology on Earth fragmenting into two separate camps that don't depend on each other at all? There are real arguments on both sides. Where do you land? Drop it in the comments. If you enjoy these deep dives that get underneath the headlines and explain what's really happening before the rest of the world catches on, subscribe to Eastern Engine and turn on notifications. We break down the chips, the breakthroughs, and the strategic moves that decide who leads the next decade of technology. And there's a lot more coming. Thanks for watching. I'll see you in the next one. It is the largest power station ever built. A wall of concrete stretching more than 2 kilometers across the Yangtze River, holding back a reservoir that runs for hundreds of kilometers behind it. It can generate more electricity than any other single structure on Earth, and its construction required relocating well over 1 million people. The Three Gorges Dam is, by almost any measure, one of the most ambitious engineering projects in human history. But for years, it has also been the subject of persistent questions about the quality of its construction, about its effect on the region's environment, about sediment piling up behind it, and about whether the enormous benefits it provides come with risks that have never been fully accounted for. Critics have even given it a nickname that is stuck, a tofu dread project, a Chinese phrase used for construction work that looks solid on the surface but is allegedly poorly built underneath. So how much of this is genuine concern, and how much is exaggeration? Today we are going to walk through the real debate around the Three Gorges Dam, the documented concerns, the official responses, what has been verified, and what hasn't. Because the truth here is more complicated and more interesting than either side usually admits. Let's start with the scale of what we're actually talking about. The Three Gorges Dam sits on the Yangtze, China's longest river and one of the largest in the world. Construction officially began in 1994, and the project came online in stages over the following years, with full power generation reached around 2012. The total cost is generally estimated in the range of tens of billions of dollars, with figures around the 28 to 32 billion mark commonly cited. The dam was built with 3 primary goals. The first was flood control. The Yangtze has a long and devastating history of flooding, with major floods in the 20th century alone killing enormous numbers of people. The dam's reservoir was designed to absorb floodwaters and release them in a controlled way, protecting cities downstream. The second goal was power generation. The dam's turbines produce a massive amount of clean electricity, displacing what would otherwise be generated by burning coal. And the third was improved navigation, allowing larger ships to travel further up the river through a system of locks. On those headline goals, the dam has delivered real results. It generates an enormous quantity of carbon-free electricity every year, and it has been credited with moderating several flood events on the Yangtze. These are genuine achievements that any fair assessment has to acknowledge. But the scale that makes the dam impressive is also exactly what makes its critics nervous. When a structure is this large and holds back this much water, the consequences of anything going wrong are correspondingly enormous. And that is where the controversy begins. The most attention-grabbing criticism of the dam concerns the quality of its concrete. During construction, the project poured concrete at a record-setting pace. In one peak year around 2000, the volume of concrete placed was several times what the famous Hoover Dam required across its entire construction. Pouring concrete that fast creates a genuine engineering challenge, because as concrete cures it generates heat, and if that heat isn't managed carefully, the material can develop internal stresses, cracks, or voids as it expands and contracts. The Hoover Dam famously solved this problem by mixing its concrete with chilled water and running cooling pipes through the structure to control the temperature as it set. Critics of the Three Gorges project have alleged that, in the rush to set records and meet deadlines, similar temperature control measures were not applied as rigorously as they should have been, and that this led to cracking and voids in parts of the structure. These concerns are not purely the invention of outside critics. Some of the people involved in the project's own quality inspection process raised flags during construction. There are documented references to inspection teams finding surface defects, cracks, and seepage in certain areas, particularly around the ship lock system, where teams reportedly found voids in the concrete during the early 2000s. Internal correspondence from quality reviewers described the overall quality at the time using cautious, hedged language rather than glowing approval. Here's the crucial context that often gets left out, though. According to the same engineering records, those defects were identified and then remediated. Reports document that water-seeping cracks in the lock system, totaling thousands of meters in length across hundreds of instances based on mid-2000s surveys, were subsequently repaired to meet design requirements. In other words, the concerns were real, but they were also addressed through ongoing maintenance and repair, which is, to be fair, a normal part of operating any massive piece of infrastructure. So the honest picture is this. There were genuine quality concerns during construction, some raised by insiders, and there has been ongoing repair work since. Whether that represents a structure that is fundamentally sound but high maintenance, or one with deeper problems, is the heart of the dispute, and reasonable engineers have landed on different sides of it. In July 2019, a story exploded across the internet. Someone posted satellite images appearing to show the dam visibly warping and bending out of shape, sparking a wave of panic that the structure was deforming and at risk of failure. This is worth examining closely, because it became one of the most widely shared claims about the dam, and it turned out to be misleading. The apparent warping in those images was not real structural deformation. It was an artifact of how certain satellite mapping services process images, automatically stretching and distorting flat imagery to drape it over three-dimensional terrain models. When you look at a long, straight structure laid over uneven terrain in those systems, it can appear to curve even when it is perfectly straight in reality. Other satellite images of the same dam, processed differently, showed no such bending. Chinese authorities responded by stating the dam was operating normally and within its safety parameters, and independent observers who examined the imagery agreed that the viral deformation was an image processing illusion rather than evidence of a failing structure. This episode is important for two reasons. First, it shows how quickly alarming claims about the dam can spread regardless of whether they hold up. And second, it's a useful reminder to treat dramatic claims in either direction with some caution. The dam has genuine, documented issues worth discussing. The 2019 It's Bending panic was not one of them. Beyond the structure itself, some of the most substantial debate concerns the dam's effect on the surrounding environment. And here, the science is genuinely complex and still debated. One area of concern is local climate. After the reservoir filled, the surface area of standing water in the region expanded enormously, by some estimates more than doubling. Some researchers, including geologists who have studied the area, have argued that this large new body of water altered local weather patterns, contributing to increased evaporation, shifts in temperature, and changes in rainfall in parts of the surrounding region. They point to a series of extreme weather events in nearby provinces in the years after the reservoir filled, including severe flooding in areas that had historically been prone to drought. A NASA-affiliated study using satellite data did examine the reservoir's potential influence on regional precipitation and surface temperatures, and found measurable effects on rainfall in certain areas near the reservoir. However, it's important to be precise here. Attributing specific weather disasters to the dam is scientifically difficult. The same years saw broader climate variability across China and the wider world, and separating the dam's local influence from larger regional and global climate trends is genuinely hard. So while the idea that a reservoir of this size affects its immediate microclimate is plausible and supported by some research, sweeping claims that the dam caused every flood or heat wave in the broader region go well beyond what the evidence can support. Other documented environmental concerns are more clear-cut. Sediment management is a real and ongoing engineering challenge. The Yangtze carries a heavy load of silt, and dams interrupt that natural flow, causing sediment to build up in the reservoir over time. Water quality changes in slow-moving reservoir water are a recognized issue, and there are well-studied concerns about reservoir-induced geological activity, where the immense weight of stored water and fluctuating water levels can increase the frequency of small landslides and seismic events near large reservoirs. These are not unique to the Three Gorges Dam. They are known challenges for major dams worldwide, but the sheer scale here amplifies them. One of the more thought-provoking concerns raised by critics involves not the Three Gorges Dam alone, but the entire system of dams now operating on the Upper Yangtze and its tributaries. Over the years, China has built a series of additional large hydropower stations upstream on the Jinsha River, which feeds into the Yangtze. On one level, this makes engineering sense. Upstream dams can hold back floodwater and trap sediment before it reaches the Three Gorges Reservoir, easing pressure on the main dam. But critics point out a less comfortable implication. Stringing many massive dams along the same river system creates a chain. The concern is that if any single dam in that chain were to fail catastrophically, the sudden release of its stored water could threaten the dams downstream of it in a cascading sequence. It's a low probability but high consequence scenario, and it's the kind of systemic risk that's genuinely worth engineers thinking carefully about. Not because failure is likely, but because the stakes are so high. It's worth stressing that this is a hypothetical risk, not a prediction. Modern dams are built with significant safety margins, and a cascading failure would require an extraordinary chain of events. But the more dams you build on one system, the more the individual structures become interdependent, and that interdependence is a legitimate subject for ongoing safety analysis. Part of what fuels skepticism about the dam is the series of expensive follow-on projects that have been built around it over the years. Projects that critics argue exist partly to manage problems the dam itself created. One example is the bypass system for shipping. Because traffic through the dam's locks can back up significantly, with ships sometimes waiting days to pass, authorities built an over-dam transport route. Goods are unloaded from ships on one side, trucked overland along a dedicated highway, and reloaded onto ships on the other side, bypassing the lock bottleneck. The highway portion alone reportedly cost hundreds of millions of dollars, and that's before adding the upstream and downstream port facilities. Another major project is a large water diversion tunnel, begun in 2022, designed to carry water from the Three Gorges Reservoir area through a nearly 200-kilometer tunnel to the Han River. Officially, this is framed as a follow-up to China's broader water diversion programs, aimed at maintaining water levels downstream. But analysts have noted it also serves another function, giving the dam an additional channel to discharge water during flood conditions, helping relieve the difficult balancing act the dam operators face. When a major flood hits, releasing too much water risks flooding cities downstream, while holding too much back risks flooding cities upstream. An extra outlet gives operators more flexibility in that trade-off. Supporters would frame all of this as sensible infrastructure that maximizes the value of a major asset. Critics frame it as evidence that the original project created cascading problems requiring ever more expensive fixes. Both interpretations describe the same facts, which is often how these debates work. Underlying all of these specific concerns is a deeper debate that goes back to before the dam was ever built. During the project's planning and evaluation in the late 20th century, it was not universally supported, even within China's own expert community. The environmental impact assessment process was genuinely contentious. Some experts argued that the ecological and environmental downsides of the project were serious enough to warrant reconsidering whether it should proceed at all. And there were disagreements about how the official conclusions were ultimately framed. This internal debate is part of the historical record, and it reflects something true about megaprojects everywhere. Enormous infrastructure decisions involve real trade-offs, and reasonable experts can disagree about whether the benefits justify the costs. That tension has never fully gone away. Supporters point to the clean electricity, the flood control, and the navigation improvements as transformative benefits for a country of over 1 billion people. Critics point to the displaced communities, the environmental disruption, the sediment and water quality challenges, and the ongoing maintenance burden, and argue the full costs were understated from the beginning. The most honest assessment is probably that both things are true at once. The Three Gorges Dam is a genuine engineering achievement that delivers real, measurable benefits. It is also a project with real, documented downsides and ongoing challenges that its operators have to manage continuously. Whether the balance comes out positive or negative depends heavily on which costs and benefits you weigh most heavily, and that's ultimately a question of values as much as engineering. Let's come back to the question in the title. Is the Three Gorges Dam facing a new crisis? The responsible answer is, not in the dramatic, imminent collapse sense that sometimes circulates online. The dam has now operated for roughly 2 decades. It has weathered major floods. The viral claims about it physically bending were debunked. There is no credible evidence that the structure is on the verge of failure. What the dam does face is a set of ongoing chronic challenges that don't make for dramatic headlines, but are genuinely significant. Sediment accumulation that worsens over time, environmental effects on the surrounding region, the maintenance burden of a structure built at record-breaking speed, and the systemic questions raised by an entire chain of dams on one river system. These are real engineering and environmental issues that will require attention for as long as the dam exists. So rather than a single sudden crisis, the more accurate picture is a massive piece of infrastructure that delivers enormous benefits while carrying a long tail of complicated, slow-moving problems. Exactly the kind of trade-off that comes with building at this scale. What do you think? Do the flood control and clean energy benefits justify the environmental and engineering trade-offs? Or do you think projects on this scale create more problems than they solve? Let me know your honest take in the comments. This is one of those topics where thoughtful people genuinely land on different sides. And if you found this balanced breakdown useful, consider subscribing so you don't miss the next deep dive into the engineering megaprojects shaping our world.
The semiconductor industry is truly the engine room of the global economy. Chips go into everything from your smartphone to your car to massive data centers. And the web of global connections is enormous. ASML in the Netherlands producing the lithography machines that are shipped to TSMC here in Taiwan that manufactures the actual chips using designs from ARM in the UK, Nvidia and Apple. China, the biggest consumer of semiconductors.
Right now, TSMC, Samsung, and Intel are focused on something unexpected, not just smaller transistors or global trade limits, but glass. A super thin sheet of engineered glass is becoming one of the biggest changes the chip industry has seen in years. China has already invested more than $1 billion into this technology as companies race to shape the future of advanced chips. It may sound strange at first. Glass is everywhere, from phone screens to windows. But this new type of glass could completely change how powerful chips are built. That is why major tech companies and governments are paying close attention and investing heavily in it. For decades, the tech world followed one simple rule: make transistors smaller, and devices become faster and smarter. That idea helped create smartphones, cloud computing, AI systems, and modern technology as we know it. But now, in 2026, the industry is running into new limits. Today's advanced AI chips use so much power that even the best current designs are struggling to keep up. Engineers have started running into a major problem, and surprisingly, the issue is not inside the chip itself, it is underneath it. That is where advanced glass technology comes in, and once you see why companies are focusing on it so early, the whole situation makes a lot more sense. Think about a skyscraper. No matter how impressive the design looks, everything depends on the foundation underneath. If the base is weak, the entire building can run into problems. Computer chips work the same way. Every chip sits on something called a substrate, which acts like the foundation that supports everything above it.
On the planet. Just think of all the electronics that China produces, and a country that's also trying to build out its own chip industry, so it's less reliant on the West. And that has put the broader industry in the crosshairs of Washington. They have imposed export controls and tariffs to try to contain China's chip industry. They've also spent heavily to try to ensure there's production and more of it on US soil. Tariffs can only go so far. No company builds chips from the start to finish.
For years, these substrates were made from special plastic and resin materials that help move electrical signals and control heat. They have done the job well for decades, but today's powerful AI chips are pushing those older materials close to their limits. That is why companies are now turning to ultra-thin glass as a possible next step in chip design. Older substrate materials worked well when computer chips were smaller and less demanding, but today's AI processors are far more advanced. Modern AI systems now combine multiple smaller chips called chiplets into one powerful package that handles memory, processing, and communication all at the same time. This design helps companies push performance even further, but it also creates new engineering challenges. These chip packages are becoming much larger and more complex, with billions of tiny connections working at extremely high speeds while producing a huge amount of heat. That is where the substrate becomes a major factor. Traditional organic materials can bend and expand as temperatures rise during operation. As AI systems grow more powerful, keeping everything stable and efficient is becoming much harder, which is why advanced glass substrates are getting so much attention right now. As chips heat up and cool down over time, traditional substrate materials can slightly expand and shrink. These tiny changes may not seem important, but in advanced AI systems, even small shifts can affect performance. Connections can slowly move out of alignment, signals may become less efficient, and reliability can suffer over time. Engineers have spent years trying to reduce these problems with smarter designs and tighter manufacturing controls. But as AI chips become more powerful and complex, older materials are reaching their limits. That is why the industry started searching for a completely different solution, something more stable, precise, and reliable under extreme conditions. The surprising answer turned out to be advanced glass substrates. Unlike older materials, glass can stay much more stable during temperature changes, making it a strong candidate for the next generation of high-performance AI chips. At first, glass sounded like a strange choice for advanced computer chips. Many engineers thought it would be too fragile, too expensive, and too difficult to manufacture at scale. But the glass used in next-generation chip packaging is very different from everyday glass. It is a specially engineered material designed for the extreme demands of modern computing. Traditional substrate materials react to heat by expanding and shrinking over time, which can make large AI chip systems harder to keep stable. That was manageable with smaller chips, but today's powerful AI processors need much higher precision. Advanced glass substrates offer a big advantage because they stay far more stable under changing temperatures. That stability helps engineers maintain better performance, reliability, and efficiency as AI chip designs continue to grow larger and more complex. Advanced glass substrates can handle heat and mechanical stress with far greater stability than traditional materials. Even during constant heating and cooling cycles, they keep their shape with impressive precision. That allows engineers to place electrical connections much closer together without worrying about long-term alignment issues. The improvement is huge. Glass substrates may support far higher connection density than current organic materials, creating faster communication between chip components while using energy more efficiently. For AI systems, that could mean major performance gains without relying only on smaller transistors. Glass also helps with heat management, which is one of the biggest challenges in modern computing. Better cooling and thermal control allow powerful AI processors to run more efficiently for longer periods, especially inside massive data centers, where performance and energy use are critical factors. Glass substrates could help future AI chips run at higher performance levels for longer periods without slowing down from heat buildup. They also improve signal quality, allowing data to move with less interference compared to traditional materials. At the extreme speeds modern AI systems operate, those improvements can make a major difference in overall performance. But there is a challenge. Manufacturing these advanced glass substrates is incredibly difficult. The material must be perfectly flat, and tiny pathways inside the glass have to be created with extreme precision. Even microscopic imperfections can affect reliability. Producing this technology at large scale requires years of advanced engineering and highly specialized equipment. That difficulty is one of the biggest reasons only a small number of companies are capable of competing in this space right now. That manufacturing barrier is exactly why the recent moves by China, Intel, Samsung, and TSMC are getting so much attention. While most headlines focused on advanced lithography machines, another major technology race was quietly building in the background. For years, many experts believed the future of powerful chips depended mostly on access to cutting-edge lithography systems. The idea was simple: control the most advanced manufacturing tools, and you control the future of chip production. But China and several major tech companies also focused heavily on another strategy: advanced chip packaging and substrate technology. Instead of relying only on smaller transistors, companies began investing in new ways to connect chip components together more efficiently. That includes advanced glass substrates, precision manufacturing, and material science breakthroughs that can improve performance without depending entirely on next-generation lithography tools. China has spent years investing heavily in these areas, building factories, research programs, and supply chains focused on advanced packaging technology. Now, as AI systems demand more power and efficiency, those investments are starting to attract serious global attention. BOE is one of the clearest examples of why China's strategy around glass substrates makes sense. The company is already one of the world's biggest makers of display technology, producing precision glass for smartphones, TVs, and monitors on a massive scale every year. That experience gives BOE a strong advantage, because many of the same skills used in display glass manufacturing also apply to advanced semiconductor glass substrates. The equipment, engineering knowledge, and supply chains are closely connected, making the move into chip packaging technology a natural expansion rather than a completely new business. Other Chinese companies have also been investing heavily in solving one of the toughest challenges in this field: creating tiny electrical pathways inside the glass with extremely high precision. Over the past few years, research programs, patent activity, and production plans have all shown growing momentum in this area. Several companies are now aiming for larger-scale glass substrate production between 2026 and 2027 as demand for advanced AI chip packaging continues to rise worldwide. What connects all of these efforts is the massive level of investment going into advanced chip packaging technology. Since 2023, China has directed major funding toward factories, research programs, equipment, patents, and engineering talent focused on next-generation semiconductor packaging. Much of this activity received less global attention because most headlines were centered on the race for smaller transistors and advanced lithography systems. Meanwhile, companies and government-backed programs were steadily building capabilities in packaging technology, especially around advanced glass substrates and precision manufacturing. One reason this strategy stands out is that it builds on skills China already developed through industries like display manufacturing and materials engineering. With long-term investment and large-scale production experience, the country positioned itself to compete strongly in a growing part of the semiconductor supply chain. Now, as demand for powerful AI systems keeps rising, companies in the United States, Taiwan, South Korea, and Europe are accelerating their own investments in advanced packaging and glass substrate technology to stay competitive in the next phase of the chip industry. Intel, Samsung, TSMC, and several major American materials companies have all increased their focus on glass substrate technology over the past few years. The decisions being made now could shape the future of the global semiconductor supply chain for years to come. Intel has one of the longest histories in this area, spending more than a decade researching and developing advanced glass substrate solutions. During that time, the company built a large patent portfolio and gained valuable manufacturing experience that gives it a strong position in the industry. Intel has also started working closely with partners and suppliers to expand the overall ecosystem around this technology. Samsung is also moving quickly. The company has been developing pilot production lines and investing heavily in engineers with expertise in advanced packaging and glass materials. It has also formed partnerships with materials suppliers to help secure the specialized components needed for future production. As AI systems continue growing more powerful, major semiconductor companies are racing to improve packaging technology, and glass substrates are becoming one of the most important areas of competition. Samsung's long-term plans reportedly aim for large-scale glass substrate production around 2028, which could make the company one of the first major suppliers for advanced AI chip systems. Because Samsung already plays a huge role in the global tech supply chain, its progress in this area is getting a lot of industry attention. TSMC has also increased its focus on glass substrate research in recent years. As one of the biggest leaders in advanced AI chip packaging, the company understands that future performance gains may depend just as much on packaging technology as on transistor design itself. Expanding its work on glass substrates helps TSMC stay competitive as the industry evolves. Corning is another important player in the space. The company has decades of experience producing highly specialized glass for telecommunications, displays, and scientific applications. That expertise could make Corning a key supplier as demand for advanced semiconductor glass materials continues to grow worldwide. Investments in semiconductor-grade glass production show that the supply chain for advanced glass substrates is starting to grow in the United States. That is important because future chip manufacturing depends not only on technology, but also on having strong materials suppliers and production networks in place. Right now, the race for leadership in glass substrate technology is wide open. Companies across the United States, Asia, and Europe are investing heavily as they compete to build the next generation of AI chip packaging. Over the next few years, major AI chip designers and large cloud computing companies are expected to begin selecting long-term suppliers, which could shape the market for years to come. Big technology shifts often seem small at first. They usually begin with highly technical changes that receive little public attention, then later become recognized as major turning points for an entire industry. Many experts believe advanced glass substrates could become one of those key moments for the future of computing. Of course, that was the moment everything changed. Honestly, glass substrates are starting to feel exactly like that kind of turning point. While most people focused on export rules, advanced chips, and transistor technology, a quieter race has been happening underneath it all, the race to reinvent chip packaging. The companies and countries leading this shift are not just developing a new material. They are building the foundation that could power the next generation of AI systems. Faster AI training, more efficient data centers, and stronger computing performance could all come from improvements in this hidden layer of technology. The stakes are massive because building advanced glass substrate production lines can cost hundreds of millions, sometimes even billions of dollars. The companies that scale production first could gain a huge long-term advantage through better manufacturing experience, lower costs, and stronger partnerships. In my opinion, this may end up being one of the biggest technology shifts people overlooked at first. The transistor race still matters, but the future of AI could depend just as much on packaging and materials innovation as raw chip power itself. What do you think? Will glass substrates become the next major breakthrough in AI computing, or is the industry moving too fast to predict? Drop your thoughts in the comments. And if you enjoyed this breakdown and want more deep dives into the future of AI and technology, make sure to subscribe to the channel and turn on notifications so you do not miss the next video. Just 6 months ago, the global AI industry was forced to confront an uncomfortable reality. A relatively unknown Chinese startup called DeepSeek released an open-source reasoning model that stunned Silicon Valley. Investors suddenly realized that building world-class artificial intelligence might not require endless billions of dollars or the most expensive hardware in the world. Nvidia shares plunged, semiconductor stocks sold off, and one simple question echoed across Wall Street. What if China was catching up much faster than anyone expected? Many people assumed that moment was a one-time surprise. They believed American companies would quickly regain their lead, push even further ahead, and restore confidence in the AI race. But now, it has happened again. This time, the company isn't DeepSeek, it's Moonshot AI. And instead of releasing another incremental chatbot, Moonshot has unveiled what it calls the world's largest open-weight artificial intelligence model ever created. Its name is Kimi K3, and almost immediately after its announcement, investors around the world began asking whether another major shift in the AI race had just begun. The timing couldn't have been more dramatic. This past week, semiconductor stocks suffered one of their worst performances in more than a year. The Philadelphia Semiconductor Index fell sharply, while companies like Nvidia, AMD, and Broadcom all finished the week lower. Across Asia, technology shares also came under pressure as investors tried to understand what China's latest AI breakthrough could mean for the future of the industry. Of course, markets never move because of one single event. There were already concerns about high AI valuations, massive spending by technology giants, and broader geopolitical uncertainty. But Moonshot's announcement added fuel to an already nervous market because it reminded investors of something they had hoped was behind them. The DeepSeek surprise. For the second time this year, a Chinese AI company appeared seemingly out of nowhere with technology that demanded attention from the entire world. So what exactly is Kimi K3? Why are AI researchers taking it seriously? Why did Wall Street react so quickly? And perhaps most importantly, is this another DeepSeek moment? Or is it something even bigger? To understand why this announcement matters, we first need to understand the company behind it. Unlike OpenAI, Google, or Anthropic, Moonshot AI isn't a household name outside China. In fact, many people in the United States had probably never even heard of the company before this week. Yet inside China's technology industry, Moonshot has been quietly building for years. Founded by a team of AI researchers and entrepreneurs, the company quickly became one of China's most valuable artificial intelligence startups. It attracted backing from some of the country's largest technology investors, including Alibaba, giving it access to enormous computing resources, engineering talent, and one of the fastest-growing AI ecosystems anywhere in the world. Instead of chasing headlines, Moonshot focused on building large language models capable of handling extremely long documents, complex reasoning tasks, software development, and enterprise applications. Its previous Kimi chatbot gained popularity inside China because it could process enormous amounts of text at once, far more than many competing systems at the time. But Kimi K3 is an entirely different level. According to Moonshot, the new model contains a staggering 2.8 trillion parameters, making it the largest open-weight AI model ever announced. Instead of functioning like a traditional dense neural network where every parameter is activated for every request, Kimi K3 uses what's known as a mixture of experts, or MoE, architecture. That distinction is incredibly important. Rather than activating all 2.8 trillion parameters every time someone asks a question, the model intelligently selects only the most relevant expert networks needed for each task. This dramatically reduces the amount of computing power required while still allowing the overall system to benefit from an enormous knowledge base. In simple terms, it's a bit like having thousands of specialists available inside one giant company. Instead of asking every employee to solve every problem, only the few experts who are actually needed join the conversation. The result is a system that can be both extremely large and surprisingly efficient. That efficiency is becoming one of the defining themes of China's AI industry. Rather than trying to simply build the biggest data centers or purchase the largest number of GPUs, many Chinese companies are increasingly focused on getting more performance from every unit of compute they already have. This strategy has become even more important as US export controls continue limiting China's access to Nvidia's most advanced AI chips. Instead of slowing down innovation, those restrictions may have encouraged Chinese companies to rethink how modern AI systems should be designed in the first place. And that brings us to the most interesting part of the story. Because Kimi K3 isn't attracting attention simply because it's large, it's attracting attention because of how well it performs. In independent benchmark testing released alongside the announcement, Kimi K3 demonstrated results that immediately caught the attention of AI researchers around the world. On several demanding software engineering and coding evaluations, the model ranked among the strongest systems available, competing directly with leading American models, and even outperforming them in certain specialized tests. That doesn't mean Kimi K3 is suddenly the undisputed best AI model on Earth. Different benchmarks measure different abilities, and several leading US systems still perform exceptionally well across a wide range of tasks. But that's not really the point. The point is that another Chinese company has once again produced an AI system capable of competing at the highest levels of the industry. And for investors, that's becoming increasingly difficult to ignore. But here's where the story becomes much more interesting. When most people hear that an AI model has 2.8 trillion parameters, they naturally assume bigger automatically means better. In reality, that's not how modern artificial intelligence works anymore. Over the past few years, the AI industry has undergone a quiet but significant shift. Companies are no longer competing simply to build the largest model possible. They're competing to build the smartest, fastest, and most efficient model. And that's exactly where Kimi K3 enters the conversation. Unlike earlier generations of large language models that attempted to activate every parameter for every request, Kimi K3 uses what's called a mixture of experts, or MoE architecture. Think of it like this. Imagine you own a company with 10,000 employees. If every employee attended every meeting, the company would become painfully slow and incredibly expensive to operate. Instead, businesses assign specialists to specific problems. The legal team handles contracts, engineers solve technical issues, finance manages budgets, marketing focuses on customers. Only the people actually needed join the discussion. Modern AI is beginning to work the same way. Instead of waking up all 2.8 trillion parameters every time someone asks a question, Kimi K3 activates only a relatively small portion of the network depending on the task being performed. That means the model can deliver much of the capability of an enormous system without paying the full computational cost every single time. And that's becoming increasingly important. Training frontier AI models now costs billions of dollars. Running them can cost millions more every month. The biggest challenge in artificial intelligence is no longer simply creating smarter models. It's figuring out how to make those models affordable enough for millions of people to actually use. This is exactly why researchers across the industry are paying attention to architectures like mixture of experts. They represent one possible path toward making next-generation AI dramatically cheaper to operate. For China, this strategy carries even greater importance. Because of US export restrictions on advanced AI hardware, Chinese companies have spent the past several years learning how to squeeze every ounce of performance from the computing resources they already possess. Instead of assuming they can always buy more cutting-edge chips, many Chinese AI companies have focused on software optimization, distributed computing, model compression, and efficient architectures. In many ways, necessity has become a powerful driver of innovation. That doesn't mean China has solved every hardware challenge. Far from it. Companies like NVIDIA still produce many of the world's most advanced AI accelerators, and access to high-end computing remains one of the industry's biggest competitive advantages. But Kimi K3 demonstrates that algorithm design can sometimes narrow the gap faster than people expect. And that's exactly what has captured Wall Street's attention. Because investors aren't simply asking whether Moonshot built another chatbot, they're asking whether the economics of AI are beginning to change. For the past 2 years, the dominant assumption across financial markets has been relatively simple. The more advanced AI becomes, the more GPUs everyone will need. That assumption helped drive NVIDIA's extraordinary rise into one of the world's most valuable companies. Every major AI company, from OpenAI and Anthropic to Google, Meta, Microsoft, Amazon, and xAI, announced plans to spend tens or even hundreds of billions of dollars building larger data centers packed with increasingly powerful graphics processors. The belief was straightforward. More intelligence required more hardware. More hardware meant more NVIDIA chips. More NVIDIA chips meant higher revenues. But Chinese companies like DeepSeek, and now Moonshot, have introduced an uncomfortable question. What if software improvements begin arriving faster than hardware improvements? What if smarter algorithms reduce the amount of computing needed for many AI tasks? Suddenly, investors are no longer evaluating only who has the biggest GPU cluster. They're also asking who has the most efficient software. That subtle shift can have enormous financial consequences. It doesn't necessarily mean NVIDIA loses. In fact, Many experts believe better AI models could ultimately increase demand for computing because cheaper intelligence encourages wider adoption across businesses, governments, healthcare, manufacturing, robotics, education, and countless other industries. History has shown this pattern many times before. When computers became cheaper, people didn't buy fewer computers, they bought more. When internet access became faster, people didn't use less bandwidth, they used dramatically more. Efficiency often expands markets rather than shrinking them. The same could eventually happen with artificial intelligence. But markets don't always think about the long term. Investors often react first and analyze later. That's one reason semiconductor shares experienced heavy volatility after Moonshot's announcement. The immediate question wasn't whether Kimi K3 would destroy Nvidia's business. The question was whether Wall Street had underestimated how quickly Chinese AI companies were closing the gap. And this wasn't happening in isolation. Over the past year alone, China has produced a steady stream of AI announcements that have challenged long-standing assumptions. Huawei continued expanding its AI computing ecosystem despite export restrictions. DeepSeek demonstrated that frontier-level reasoning could be achieved with surprisingly efficient training methods. Alibaba introduced increasingly competitive enterprise AI systems. Baidu continued pushing foundation models into commercial deployment. Tencent accelerated AI integration across its enormous software ecosystem. Now Moonshot has added another headline. Viewed individually, each announcement may seem manageable. Viewed together, they begin telling a much larger story. Not that China has overtaken the United States, but that China's AI ecosystem is becoming far deeper, broader, and more competitive than many analysts predicted just a year ago. And that's exactly why Kimi K3 has generated headlines around the world. Because this isn't just another product launch. It's another data point suggesting that the global AI race is becoming far more competitive than anyone expected. But there's another reason Kimi K3 is making headlines, and it has nothing to do with parameter counts. It's the word open. That single word could end up being more important than all 2.8 trillion parameters combined. To understand why, imagine there are two incredibly powerful AI models. One can only be used through a company's website or paid subscription. The other can be downloaded, modified, improved, and integrated into almost any application. Which one spreads faster? History has already given us the answer. Open technologies have repeatedly transformed entire industries. Linux became the backbone of cloud computing. Android became the world's largest mobile operating system. Python became one of the most widely used programming languages on Earth. When developers are allowed to build on top of a technology instead of simply renting access to it, innovation often accelerates dramatically. That's exactly why the AI industry has become divided into two very different philosophies. On one side are companies that keep their frontier models largely closed. On the other are companies increasingly embracing open-weight systems that researchers, startups, universities, and businesses can run themselves. Moonshot has clearly chosen the second path. The company announced that Kimi K3's weights will be publicly available, allowing developers around the world to experiment with the model instead of relying exclusively on Moonshot's own servers. That decision immediately expands the potential audience far beyond China. A software company in Germany could fine-tune it for manufacturing. A university in Canada could study its architecture. A startup in Brazil could build an entirely new product on top of it. A robotics company in Japan could integrate it directly into industrial automation systems. Instead of one company creating every application, thousands of developers suddenly gain the ability to build their own. That's one reason many analysts believe open-weight models can spread much faster than traditional closed platforms. And that's exactly what happened with DeepSeek. When DeepSeek released its reasoning model earlier this year, it wasn't simply another chatbot entering the market. Developers immediately began creating optimized versions, local deployments, research projects, and enterprise applications around it. Within weeks, DeepSeek had become part of conversations taking place far beyond China's borders. Now Moonshot appears to be following a remarkably similar strategy. But this time, the model is even larger, even more capable, and arriving at a moment when businesses around the world are actively searching for alternatives in the rapidly evolving AI market. That combination explains why many observers have started calling Kimi K3 another DeepSeek moment. Not because it's identical, but because it represents another unexpected challenge to assumptions that have become deeply embedded across the technology industry. For years, many people believed only a handful of American companies could consistently build frontier AI models. OpenAI, Google, Anthropic, Meta, Microsoft, those names largely defined the conversation. Now the list is expanding. DeepSeek, Moonshot, Huawei, Alibaba, Baidu, Tencent. Each company contributes something different. Some specialize in enterprise AI, others focus on consumer applications. Some build hardware, others build foundation models. Together, however, they form something much larger than any individual announcement: an ecosystem. And ecosystems are often much harder to compete against than individual companies. Silicon Valley understands this better than anyone. Apple didn't become dominant because of the iPhone alone. It built an ecosystem. Google didn't become a trillion-dollar company simply because of search. It built an ecosystem. Amazon didn't transform global commerce by creating one successful product. It built an ecosystem. China appears to be applying the same lesson to artificial intelligence. Instead of relying on one national champion, multiple companies are advancing simultaneously. Some compete against each other, others collaborate. Universities continue producing AI research. Cloud providers expand computing infrastructure. Chip manufacturers improve domestic hardware. Software companies integrate AI into existing products. Each piece strengthens the others. That's why focusing only on one model risks missing the bigger picture. Kimi K3 isn't important solely because of what it can do today. It's important because it shows another major Chinese company reaching the frontier of AI development. And every time another company reaches that frontier, the competitive landscape becomes more crowded. For American technology companies, that doesn't necessarily represent an immediate crisis. The United States still leads in many critical areas, including semiconductor design, advanced AI hardware, venture capital, cloud infrastructure, and several of the world's most influential AI research organizations. But leadership is no longer measured simply by who arrives first. It's increasingly measured by who can continue innovating while others rapidly close the gap. That's the challenge now facing the global AI industry. Because once multiple countries begin producing world-class foundation models, competition shifts away from simply proving technical capability. It becomes a race for developers, for enterprise customers, for cloud platforms, for software ecosystems, for robotics, for manufacturing, and ultimately for global influence. Which brings us back to Wall Street, because investors aren't just pricing today's technology, they're trying to predict who will dominate the next decade. And every announcement like Kimi K3 makes that prediction a little more complicated. Whether Kimi K3 ultimately becomes the world's leading AI model is almost beside the point. The bigger story is that China has now produced yet another frontier-level AI system capable of competing with some of the industry's biggest names. Just a few months after DeepSeek surprised the world, Moonshot AI has shown that China's AI momentum wasn't a one-off event. It may be part of a much larger trend. For investors, developers, and governments alike, that's becoming impossible to ignore. The AI race is no longer about a handful of companies in Silicon Valley. It's becoming a truly global competition, with multiple Chinese firms now pushing the boundaries of what's possible. Every new breakthrough raises the stakes, accelerates innovation, and forces competitors to respond even faster. Of course, there are still plenty of questions. Can Moonshot build a thriving developer ecosystem? Will businesses around the world adopt Kimi K3? Can China continue advancing despite restrictions on advanced AI chips? And perhaps the biggest question of all, who will release the next breakthrough that changes the conversation yet again? One thing is certain, the pace of AI development isn't slowing down. If anything, it's accelerating. And if this really is another DeepSeek moment, then the next chapter of the AI race may arrive much sooner than anyone expects. If you enjoyed this video, don't forget to like, subscribe, and turn on notifications so you never miss our latest updates on China's biggest technology breakthroughs and the global AI race. Thanks for watching, and we'll see you in the next one. For the last 3 years, one company has held the entire world of artificial intelligence in the palm of its hand. Not Google, not OpenAI, not Microsoft. A chip company, NVIDIA. Because every major AI model you've ever heard of, every chatbot, every image generator, every breakthrough that made headlines was trained and run on NVIDIA's chips. The company became so essential, so unavoidable, that it briefly became the most valuable company on planet Earth. If you wanted to build serious AI, you went through NVIDIA. There was no other door. And it wasn't just the chips. NVIDIA's real fortress was something most people have never heard of. A piece of software called CUDA, the invisible layer that every AI developer on Earth has been building on for over a decade. People in the industry have a name for this trap. They call it the CUDA moat. A castle wall so wide and so deep that even if a rival built a faster chip tomorrow, no one could use it, because the entire world's AI software was written for NVIDIA and NVIDIA alone. That was the situation. That was the lock on the door. And a few weeks ago, a Chinese AI company called DeepSeek did something that was supposed to be nearly impossible. It built a brand new frontier-class AI model that runs from top to bottom without a single piece of NVIDIA software anywhere in its stack. No CUDA, running instead on chips made by Huawei, a company the United States sanctioned years ago specifically to keep it away from this exact moment. Now, and you know this is coming, there's crucial nuance here, and parts of this story cut against the hype in ways that are genuinely fascinating. I'm going to give you all of it, honestly. But by the end of this video, you'll understand what just happened, why NVIDIA's own CEO publicly admitted he's losing China, why the CUDA moat suddenly looks less like a wall and more like a dam with a crack in it, and why this might be remembered as one of the most important moments in the AI race. Let's get into it. To understand why this is such a big deal, you have to understand how complete NVIDIA's grip really was. And it came down to two things working together. The first is the chips themselves. Training a modern AI model requires a staggering amount of raw mathematical horsepower, and NVIDIA's chips, originally designed to render video game graphics, turned out to be almost perfectly suited to the kind of massively parallel math that AI demands. For years, they were simply the best on Earth at it, by a wide margin. If you wanted to train a serious model, you needed NVIDIA silicon. Full stop. But the chips were only half the fortress. The other half, the part that really locked everyone in, was the software. CUDA is NVIDIA's programming platform, the bridge that lets AI code actually talk to the chips. And here's the thing, the entire global AI community has been building on CUDA for more than a decade. Every framework, every tool, every tutorial, every trick built for CUDA. An entire generation of engineers grew up speaking it. That's the moat. Imagine a country where every road, every gas station, every mechanic, and every driving school was built for exactly one brand of car. Even if a competitor released a better vehicle, who would buy it? You couldn't fuel it, fix it, or find anyone trained to drive it. That's what NVIDIA built. Not just a better car, but the entire road system everyone else was forced to drive on. Switching away wasn't just hard. For most companies, it was unthinkable because it meant abandoning every tool and rebuilding from scratch. So when the United States wanted to slow China's AI progress, the strategy seemed obvious and airtight. Cut China off from NVIDIA's most powerful chips. No advanced NVIDIA silicon, no frontier AI. The leash was the chip, and the lock was the software. And for a while, that logic held, until a cornered company decided the only way out was to build its own road system from scratch. The company at the center of this is DeepSeek, a Chinese AI lab that already shocked the world once. Back in early 2025, when its earlier model launched, it was so unexpectedly capable and so cheap to run that it wiped out hundreds of billions of dollars from NVIDIA's market value in a single day. Investors suddenly panicking that maybe the future of AI wouldn't need quite so many expensive NVIDIA chips after all. Now DeepSeek is back with its new generation, V4, a genuinely frontier-class model, a colossal system with 1.6 trillion parameters, competitive on serious benchmarks with the best models from American labs. On certain coding and reasoning tests, it ranks at or near the very top, trading blows with the flagship models from the biggest names in Western AI. But the benchmarks aren't the real story. The real story is what's underneath. According to multiple reports, V4 is the first DeepSeek model with no NVIDIA CUDA dependency anywhere in its core stack. Instead, it was natively built to run on Huawei's Ascend chips, using Huawei's own software framework, called CNN, as the replacement for CUDA. Think of CNN as Huawei's homegrown version of that road system, its own bridge between AI code and its own chips. And the engineering effort this took is staggering, which is actually why V4 was so delayed. For months, the model kept slipping past its expected release dates, and there was a single reason. Migrating a system this enormous off of CUDA and onto Huawei's completely different software framework, essentially from scratch, is brutally hard. There's even a detail that perfectly captures the difficulty. The team developed its own specialized programming language, called Tilelang, so the model's core operations wouldn't be permanently chained to any one company's chips. Months of delay weren't a failure, they were the price of independence. Here's the detail that drives the point home like nothing else. DeepSeek reportedly gave Huawei weeks of exclusive early access to optimize the model for its chips, a courtesy it pointedly refused to give NVIDIA and AMD. The Chinese company put its own domestic chip maker first and made the American giants wait. A few years ago, that would have been unthinkable. If you want a single piece of evidence for how serious this is, you don't have to take China's word for it. You can take NVIDIA's. NVIDIA's CEO, Jensen Huang, one of the most powerful figures in all of technology, publicly admitted that his company has largely conceded China's advanced AI chip market to Huawei. Let that sink in. The head of the most dominant chip company on Earth, openly acknowledging that in the world's second-largest economy, he's handing the field to his Chinese rival. CEOs do not say things like that lightly. That is not spin. That is a man reading the board and admitting he's losing a piece of it. And the market is moving on exactly that belief. Reports indicate that China's three internet giants, Alibaba, ByteDance, and Tencent, have collectively pre-ordered hundreds of thousands of Huawei's new AI chips, positioning themselves to run models like V4 at massive scale. Pre-orders on that scale don't happen on a hunch. They happen when the biggest players in a market have decided which way the wind is blowing. Huawei is now bracing for something like $12 billion in AI chip revenue, with reports that Chinese fabs can barely keep up with demand, while NVIDIA's share of that same market quietly craters. The picture is unmistakable. A model the world's developers actually want to use, running on Chinese chips, bought in enormous volume by China's biggest companies, with NVIDIA's own CEO conceding the territory. The lock on the door didn't just loosen. Someone built an entirely new door. But, and this is where I have to be honest with you, because the truth here is more interesting than the clean headline. The door isn't quite as wide open as it first appears. Here's the nuance that separates this channel from the breathless headlines. Because there are three big caveats, and you deserve every one of them. First, and most important, V4 was still trained mostly on NVIDIA. Building an AI model has two phases: training, the immensely expensive process of creating the model's intelligence, and inference, the cheaper process of actually running it for users. The NVIDIA free achievement is strongest on the inference side. For the hardest part, frontier training, Chinese firms, including DeepSeek, have still largely leaned on NVIDIA hardware because Huawei's chips and software aren't yet reliable enough for that brutal workload. In fact, DeepSeek reportedly couldn't complete a clean training run for an earlier model on Huawei chips even with Huawei's own engineers on site. So cut NVIDIA out completely is true for running the model, but the deepest, hardest layer of AI still has NVIDIA footprint. Second, DeepSeek deliberately kept V4 compatible with NVIDIA too. Buried in the technical details, V4 was validated on both Huawei and NVIDIA platforms. Why? Because if the model only ran on Huawei chips, the global community of developers, who overwhelmingly own NVIDIA hardware, couldn't use it. And an open-source model that nobody outside China can run is just a political statement, not a living technology. So DeepSeek is playing a clever double game. Prove independence is possible, while keeping global compatibility so the model stays relevant everywhere. That's not weakness, it's strategy. But it means the total break is more nuanced than it sounds. Third, Huawei's K&A software still trails NVIDIA's CUDA by a wide margin, by something like an order of magnitude in ecosystem maturity. A decade of global development doesn't get matched in a year. KN works because DeepSeek controls its own full stack and tuned everything by hand. For the average developer worldwide, CUDA is still the default and will be for a long time. So here's the fair summary, the one the hype skips. China has not matched NVIDIA. Huawei has not caught up. KN has not equaled CUDA. What actually happened is subtler and honestly more important than any of those simple claims. For the first time, a frontier-class AI model exists that was built from chip to model, with no American software at its core. Proving the thing everyone said was years away is possible right now. The wall isn't gone, but everyone just watched someone climb over it. So if China hasn't fully caught up, why is this such a big deal? Because of what it starts, not what it finishes. The real significance is something experts call a learning loop, and it's the thing NVIDIA should actually fear. Here's how it works. DeepSeek optimizes its model for Huawei's chips. Huawei gets a serious, real-world, world-class workload to learn from. Its canned software gets battle-tested and improves. Cloud providers gain experience running it. Other Chinese AI labs see it working and start building for Huawei too. And the next model becomes easier to run on Chinese chips than the last one. Round and round, each loop making the domestic alternative a little stronger. That's how an ecosystem is born. Not in one dramatic leap, but through exactly this kind of repeated, workload-driven improvement. NVIDIA's moat was never really just the chips. It was the ecosystem, the decade of everyone building on CUDA. And the only way to challenge an ecosystem is to start a rival one and let it compound. V4 is the starting gun for precisely that. It gives the Chinese stack its first true frontier-class workload to organize around. And the strategic ripple effects are already spreading. Because V4 is open source and dramatically cheaper to run than Western alternatives, reportedly by a huge margin, it becomes attractive far beyond China. Governments and institutions in countries that can't or won't rely on American cloud infrastructure can now run a top-tier AI model entirely on a non-American stack. That's a genuinely new option in the world, and it didn't exist a year ago. Step back and the pattern is the one we keep seeing on this channel. A restriction was designed to lock China out. Instead, it forced China to build the one thing the restriction was meant to prevent: a complete, independent, domestic alternative. The export controls didn't stop the parallel ecosystem. They may have been the very thing that created it. Cut off from the road system everyone else uses, China started paving its own. Here's my honest opinion. I think the two loudest reactions to this are both wrong, and the truth is more interesting than either. The people shouting China just destroyed Nvidia and won the AI war are flatly ahead of the facts. Frontier training still leans on Nvidia, Cana still trails CUDA badly, and DeepSeek itself kept Nvidia compatibility on purpose. Anyone selling you Nvidia is finished is selling a fantasy. But the people waving this away, it's nothing, they still need Nvidia, ignore it, are making the bigger mistake, the same one that's been made at every stage of this story, because they're fixated on the fact that the wall still stands, and missing that someone just proved it can be climbed. The single most important word in this entire story is not chip or model, it's possible. For 3 years, the iron assumption was that you simply could not build frontier AI without the American stack. That assumption is now dead. Not weakened, dead. And once something is proven possible, it almost always gets better, cheaper, and more common from there. What strikes me most is that Nvidia's own CEO seems to understand this better than the cheerleaders on either side. He didn't dismiss it, he conceded ground. That tells you the person with the most to lose and the best view of the board is taking it seriously. Maybe the rest of us should too. The CUDA moat was the widest, deepest competitive wall in modern technology. It still stands, but for the first time, there's a crack in the dam, and water has a way of finding every crack and slowly, relentlessly making it bigger. So here's my question for you, and I genuinely want your honest answer. Did the chip restrictions backfire? By forcing China to build a complete, independent AI ecosystem it might never have bothered to build otherwise? Or were they still worth it, because they've kept China a step behind and burning enormous resources to catch up? Did cutting the cord set China free, or just slow it down? Drop your real take in the comments. I read every single one, and this is exactly the debate I love seeing down there. If you want to keep following this, the breakthroughs, the workarounds, the shifts the rest of the world keeps underestimating until they can't, subscribe to Eastern Engine and hit the notification bell. Chips, AI, computing, the entire foundation of the modern world is being rewritten right now, and we break it all down clearly and honestly before the mainstream catches on. Thanks for watching. I'll see you in the next one. China's memory crisis is spreading into a part of the semiconductor industry most people barely notice. A Chinese supplier called Giantech Semiconductor has reportedly told distributors that prices across its entire NOR flash product portfolio will rise by 25% beginning July 6th. The increase applies not only to newly signed orders, but also to outstanding orders that have not yet been delivered. That is a major move for a component that usually receives far less attention than RAM, high-bandwidth memory, or solid-state drives. NOR flash is the small, reliable memory that stores firmware, boot code, configuration data, and essential instructions inside cars, routers, industrial machines, communications equipment, and countless connected devices. Without it, many electronic systems cannot even start. Contract prices for mature memory products have already surged sharply during the first half of 2026. Artificial intelligence infrastructure is absorbing investment, factory space, and customer attention. Automotive and edge AI systems are demanding larger amounts of dependable embedded memory. And now one Chinese supplier is adding another 25% to its price list. The question is whether this is a temporary adjustment from one company, or whether the global memory shortage is moving into the overlooked chips that keep the world's electronics running. What NOR flash actually does. NOR flash is not the same as the DDR5 memory inside a gaming computer. It is also different from the NAND flash used inside an SSD or smartphone storage drive. The easiest way to understand NOR flash is to think of it as instruction memory. When a device powers on, it needs a trusted place to find the first code it will execute. That code may initialize the processor, check connected hardware, load safety settings, verify security keys, and prepare the operating system. NOR Flash is well suited to that job because it keeps data when power is removed and allows fast, direct access to stored instructions. A vehicle may use NOR Flash inside electronic control units, infotainment systems, driver assistance computers, cameras, radar modules, telematic systems, and digital instrument clusters. A network switch may use it to store boot firmware and configuration code. An industrial robot may depend on it for control software that must survive vibration, heat, and years of continuous operation. A product containing powerful processors and expensive sensors can still become unusable if its boot memory is missing, unreliable, or delayed. Why prices are rising now? Mature memory products such as NOR Flash and SLC NAND are often manufactured on older process technologies. Those production lines remain useful, but they do not generate the same excitement or margins as advanced AI memory. Large semiconductor manufacturers are investing heavily in high-bandwidth memory, enterprise SSDs, advanced DRAM, and newer NAND products. Those categories are being purchased in enormous quantities by cloud companies building AI infrastructure. Factory equipment, engineering teams, capital budgets, and wafer capacity